It began with a motion so subtle that at first it was indistinguishable from the millions of small, wandering objects astronomers track each night. A faint point of light, a whisper of reflected sunlight on a cold surface drifting against the backdrop of fixed stars. Nothing unusual, not at first glance. The sky is filled with such travelers. Comets slipping along long ellipses, asteroids pivoting in the gravitational fields of planets, fragments chipped from larger worlds by ancient collisions. The solar system is a dynamic, restless place, and its inhabitants sometimes behave unpredictable. But this object was different. It carried itself with a kind of defiance, as though it owed nothing to the sun, nothing to the planets, nothing to the gravitational expectations that had shaped all known celestial wanderers for billions of years. Before anyone understood what they were looking at, before the measurements stacked up into something undeniable, the object's presence felt like a disturbance. Its speed was wrong, its path was wrong. Its attitude seemed almost dismissive of the architecture of the solar system. As it approached from the darkness beyond Neptune, it did not curve gently like a comet falling inward. It did not loop back around the sun like an object that had been sculpted by the slow tug of gravity over eons. Instead, it cut across the outer solar system like a blade, slicing through a space that had always been assumed closed, controlled, predictable. The solar system, after all, is supposed to be a family of worlds that share a common story. Every planet, every comet, every dust grain once belonged to a single swirling disk of gas and rock that wrapped itself around a forming sun. From that disk emerged the Earth, the gas giants, the icy realms on the edges of the Kuiper Belt, and the vast invisible halo of the Oort cloud. Everything here is related. Everything carries the imprint of that long-ago beginning. And for as long as science has studied it, this system has appeared beautifully isolated, a place shaped internally, evolving internally, operating under its own gravitational logic. Comets descend and retreat. Asteroids break and wander. The sun keeps everything where it belongs. So when an object comes in from the darkness beyond that boundary, when it arrives steeped in a cold older than the solar system itself, its very existence challenges that sense of isolation. It forces astronomers to confront a truth the universe has known all along. This is not a sealed habitat. This is a crossroads in a galaxy full of restless, drifting bodies. A place where the sun's influence dissolves into the broader forces of the Milky Way. A place where strangers can appear without warning, shaped by the gravity of other suns, molded by dust orbiting stars we may never detect, and sent on journeys that last longer than humanity has existed. The object's speed alone told a story. It moved far too fast to be bound to the sun. Even from its first recorded position, before its orbit had been fully calculated, astronomers sensed its rebellion. It didn't bow as it approached. It didn't slow in any familiar way. Instead, it plunged inward with the momentum of something that had been traveling for millions, perhaps billions of years. Its path traced not an ellipse, but a hyperbola, a mathematical curve that screams one message: this object is not from here. It fell inward like a stone skipping across the gravitational field, touching the domain of the sun for a brief moment before continuing on its way, never to return. At first, there was no reason to assign it special status. Space surveys capture countless transient points of light every night. Telescopes designed to monitor the sky for hazardous asteroids catalog thousands of potential threats. But as the observations accumulated, an unease grew. Astronomers plotted its positions on graphs. They recalculated, they corrected, they ran models. And each iteration told them the same unsettling truth: its trajectory was not compatible with the architecture of the solar system. They could not integrate its orbit backward in time and make it match the sun's gravitational family. It refused to be part of any known dynamic group. It wandered alone. This realization carried weight because it echoed earlier surprises. In recent years, other interstellar objects had passed through, shattering long-held assumptions about the rarity of such events. First came Oumuamua, a visitor so strange that even today scientists argue passionately about what it was. Then came Borisov, a cometary visitor with unmistakable characteristics of a distant stellar nursery. Each arrival felt like the first crack in a window that had been shut for billions of years. And now there was a third, another messenger from beyond the sun's reach. Another reminder that the Milky Way is filled with drifting relics cast out from planetary systems that may have lived and died before our star was even born. To understand the significance of this newcomer, one must imagine the galaxy not as a serene spiral, but as a place of turbulence. Stars form in clusters, where gravity wrestles with angular momentum. Planets collide, orbits shift, giant worlds migrate. Comets are flung outward in monumental gravitational encounters. This chaos does not end once a system stabilizes. Over billions of years, stars perturb one another, passing close enough to kick loose trillions of icy fragments and rocky shards. These fragments drift in uncountable numbers, invisible, silent, ancient. They populate the galaxy like dust in a sunbeam. This stranger in the solar system was one of them, a speck of material forged elsewhere, a relic chipped from a distant world, or thrown from a foreign cometary belt, a witness to the history of another star. Its surface could hold the chemical imprint of environments our telescopes cannot yet see. It might carry isotopes untouched since the early galaxy. It might be older than Earth, older than the Sun, older than the planets that now study it with telescopes and curiosity. And so it arrived, unexpected and unbound, reminding us that the solar system is not a closed room, but a threshold, a place where the galaxy occasionally sends a messenger, a piece of evidence that even the boundaries we rely on are porous, a reminder that the cosmic wilderness is alive with motion, and from time to time, it reaches out a hand. This is the story of that stranger, where it came from, what it means, and why its brief, bright appearance changed our understanding of the galaxy itself. Before the first interstellar object was ever detected, the scientific community lived with an assumption that shaped both thought and imagination. The space between stars was an ocean too empty for anything but dust and gas. Astronomers knew that interstellar space contained material. After all, stars are born from swirling clouds of gas, and planets grow from disks of debris. But the popular idea was that solid objects, especially kilometer-scale bodies, were extraordinarily rare in that vast emptiness. They might exist, yes, but the chances of one finding its way into our solar system seemed negligible. Textbooks mentioned the possibility with academic caution. Lectures treated interstellar wanderers as interesting but unlikely. It was a thought experiment more than an expectation, a curiosity tucked between the chapters on cometary origins and stellar dynamics. But this assumption was not born from evidence. It grew instead from the absence of evidence. For centuries, humans had watched the skies without ever seeing such an object. Telescopes improved, surveys expanded, catalogs ballooned. Still, nothing. No rock from another star. No comet whose orbit defied membership in the Sun's gravitational family. With each year that passed without an interstellar detection, the silence seemed to confirm the belief. And so the idea ossified. Perhaps the emptiness between stars was just that, empty. Yet the galaxy had been telling a different story all along. Scientifically, it was understood that planetary systems are messy places. They form violently, with collisions so intense they melt rock. Giant planets migrate inward and outward, destabilizing everything in their path. Whole belts of icy objects get thrown into space. At the same time, stars are born in clusters, where mutual gravitational interactions push debris outward in wild trajectories. As time stretches, stars drift apart, carrying their expelled fragments into the broader galaxy. Over billions of years, this process repeats across hundreds of billions of systems. The Milky Way becomes seeded with untold trillions of rocky and icy bodies that no longer have homes. If one paused to think about it, the conclusion was obvious. Interstellar space should be full of wandering remnants. But no one had seen one, and so the concept remained more theoretical than real. That all changed the moment the first interstellar visitor sliced through the solar system, a thin, tumbling shard named Oumuamua. Its arrival was a cosmic jolt. It moved with a speed and trajectory impossible for a solar system object. Its elongated shape and strange acceleration deepened the mystery. It triggered debates, arguments, papers, and counterpapers. It became the most unexpected discovery in planetary science for decades, not because of what it was, but because it existed at all. Suddenly, the emptiness between stars looked very different. It looked populated. And before the shock could fully settle, another arrived. 2I Borisov, a comet with a long tail and unmistakable signs of classic cometary activity. Unlike Oumuamua, which behaved so oddly that it bordered on unnerving, Borisov fit expectations. It was dusty, icy, reactive to sunlight. Its chemistry was not exotic, but familiar. It resembled comets from our own solar system, but its orbit made clear it did not belong here. It had crossed interstellar space for ages, frozen solid, drifting in silence until the sun's heat finally awakened its gases. And as soon as astronomers analyzed it, they realized something monumental. If one interstellar comet could arrive so soon after the first confirmed visitor, then interstellar objects must be common, very common. Their arrival was like hearing 2 knocks at the door after believing the house was abandoned. It suggested that the galaxy was full of travelers, and we had simply lacked the tools to detect them. The wilderness between stars was no longer theoretical. It was populated by ancient refugees from distant systems, drifting through the galaxy with stories etched into their minerals and volatiles. That revelation reshaped the field, and as detection methods improved, the expectation shifted. Instead of wondering when another interstellar visitor would appear in our lifetimes, astronomers began asking when. They monitored the sky with new anticipation. Modern surveys scanned wider regions, faster than ever before. Algorithms processed faint, rapidly moving points of light with unprecedented sensitivity. The solar system suddenly felt less secluded, more like a port on the edge of a grand celestial trade route, where wanderers occasionally glide through the harbor before vanishing into the dark again. Within this new era of awareness, 3I Atlas arrived. It did not have the dramatic shape of Oumuamua or the bright sweeping tail of Borisov, but it carried the same badge of origin, an orbit no solar system object could possibly possess. It was another messenger from the galactic wilderness, another fragment expelled from its birth system long before complex life had evolved on Earth. With its arrival, the pattern became undeniable. These visitors were not rare. They had always been there, slipping past unnoticed, too faint to detect. But now humanity had eyes sharp enough to see them. To understand these wanderers is to understand the galaxy itself. Each one is a piece of a puzzle far larger than the solar system. They reveal how stars form, how planets flourish and fail, how gravitational chaos sculpts the architecture of worlds. They serve as nature's interstellar sampling program, delivering chemical signatures from places we can't yet reach. They whisper stories of collisions, migrations, ejections, and long, quiet drifts through ancient space. In truth, the galactic wilderness has always been lively. We merely lacked the ability to hear its footsteps. And with each new visitor, we learn to listen better. For decades, astronomers scanned the sky with an almost ritual predictability, mapping out the familiar dance of objects that circled the sun. The solar system was a place of patterns, of cycles, of orbits that could be charted with comforting certainty. Comets returned on schedule. Asteroids tumbled along well-behaved paths. Even the distant bodies of the Kuiper belt followed motions that felt like the echoes of the solar system's earliest days. Nothing out there seemed truly alien. Everything bore the unmistakable fingerprint of our sun's gravity. Every object belonged to this system, shaped by the same ancient disk of dust that once surrounded the newborn star we now rely on for life. But sometimes a discovery arrives with such force that it resets the imagination. Sometimes a point of light on a telescope screen becomes the catalyst for a shift so dramatic it feels like the universe is revealing a secret it had been holding back for billions of years. The moment 3I Atlas entered the data stream was one of those moments. At first, it appeared as all objects do, a faint light that moved slightly from one image to the next, a candidate for follow-up observation, a blip that might have been an asteroid, or a distant comet, or even a glitch in detection software. But within hours, something about it felt off. It didn't fit. Astronomers are trained to doubt their instincts until the data speaks clearly. And at first, the data was simply strange. Not unprecedented, but strange enough to warrant attention. It moved too quickly for its faintness. Its direction was pointed at an angle few known objects approached from. Its brightness changed subtly, in ways that hinted at an active surface reacting to sunlight. All of these quirks could still be explained within the usual categories of objects. But the more tracking data came in, the more every explanation crumbled. It didn't behave like a long-period comet. Its velocity was too high for an object falling in from the Oort cloud. Its approach vector seemed disconnected from any family of known solar system populations. When orbit calculations were performed, the truth illuminated itself with an almost startling clarity. This was not an object bound to the sun. Its orbit had an eccentricity greater than 1, a number that in celestial mechanics carries profound meaning. Anything with an eccentricity below 1 is an ellipse, the shape of a closed path. Anything at exactly 1 is a parabola, the boundary between a bound orbit and escape. But anything above 1 is a hyperbola, a path that never loops back. An object on such a trajectory is not tied to the sun in any way. It has arrived from the outside and will leave again untouched. This is the signature of something born beyond the solar system. Suddenly, what had been a faint point of light became a cosmic messenger, a fragment of unknown origin, a piece of some distant world or disk or collision that happened far beyond the sun's reach. It was not like the first interstellar object, whose elongated shape had baffled scientists and stirred speculation both serious and sensational. Nor like the second, whose icy coma and tail declared it a comet in the classical sense. This new visitor was quieter, subtler, but its origin was no less extraordinary. Its hyperbolic orbit was undeniable. It did not belong here. It had never belonged here. And still, here it was, slipping into the solar system like a letter that had finally found the right mailbox after drifting through an impossible network of corridors. This moment changed everything, because it provided yet another confirmation that interstellar objects are not rare exceptions. They are common enough that the universe seems eager to send them. It also showed that modern surveys, particularly the Atlas system, had matured into tools capable of catching even faint, fast-moving wanderers. Suddenly, the solar system felt less like an isolated bubble and more like a crossroads. It became clear that with the right instruments, humanity could finally see the tide of interstellar debris flowing past us. The presence of 3I Atlas brought with it a wave of questions. Where did it come from? What star once warmed its surface? What kind of planetary system had produced it? Was it ejected early in its birth system through chaotic gravitational interactions? Was it thrown outward by a giant planet migrating inward, the way Jupiter may have scattered primordial material in our own system? Or was it the remnant of a collision in a distant disk, blasted free and left to drift through the galaxy for eons? Unlike a local comet, whose history might be traced through its orbit or composition, an interstellar object carries a history that reaches beyond the boundaries of everything we can directly observe. Its story begins in a solar system we may never see. Its chemistry is shaped by a star whose light will never fall upon Earth. Its age might stretch back to a time before our sun ignited, before Earth cooled, before life existed. It is an artifact of someone else's cosmic past. Astronomers know that when these objects enter the solar system, they lose some of their original identity. The sun's heat alters their ices. Outgassing shaves away layers of material that have been preserved since the object first formed. Every hour spent near the sun's warmth erases a little more of its history. The challenge is to decipher the clues that remain while the object is still visible, and to understand how much has been changed by its brief encounter with our star. 3I Atlas became a touchstone in this unfolding field, not because it was the first, nor the brightest, nor the most dramatic, but because it arrived at a moment when astronomers were prepared. The previous visitors had rewritten expectations. By the time this third interstellar object appeared, the community was ready to study it with a combination of insight, urgency, and refined tools. It was as if the universe had whispered twice before finally speaking loudly. These visitors are not rare. They have always been here. You simply had not yet learned to listen. The moment everything changed was not a dramatic explosion of knowledge, but a quiet realization. A shift in perspective, a widening of the cosmic lens. And in that widening, the solar system transformed from a self-contained world into a place woven into the broader fabric of the galaxy. A place where strangers can arrive at any time. A place where the boundaries between here and elsewhere dissolve into a flow of ancient matter drifting through the Milky Way. This is what 3I Atlas signified. That the doors of the solar system were never truly closed. They were simply waiting for us to notice who walked through them. Long before 3I Atlas captured the attention of astronomers, a different visitor had already shattered the illusion that the solar system stood alone. Its name was Oumuamua, a Hawaiian word that roughly translates to scout or messenger from afar. And that name, chosen with poetic precision, still resonates like a whisper across scientific discussions today. Oumuamua was the signal flare in the darkness, the first unmistakable echo that something from the galactic wilderness had found its way into our orderly system of planets and dust. It was the crack in the cosmic curtain, the proof that the vast space between stars is not empty but alive with drifting fragments of unknown worlds. Before its discovery, models of the galaxy predicted that interstellar debris must exist in extraordinary quantities. Planetary systems, ours included, are messy in their youth. They eject massive amounts of material during their formative periods. Giant planets perturb smaller bodies, flinging them into deep space. Collisions expel rubble in all directions. Stellar encounters disrupt outer belts and comet clouds. These processes unfold billions of times across billions of systems. The math demanded a galaxy littered with relics. But despite the models, no one had ever seen one. The absence of observational confirmation made the idea feel abstract and speculative. Then Oumuamua arrived, and suddenly the speculative became real. Its discovery was almost accidental. Astronomers using the Pan-STARRS telescope system in Hawaii detected a faint object displaying motion inconsistent with a typical asteroid. As follow-up observations poured in, everything about it seemed to violate expectations. Its speed was extraordinary, well above the escape velocity needed to break free from the sun's gravity. Its orbit was hyperbolic, marking it as an unbound traveler. But what truly baffled scientists were its physical characteristics. Oumuamua did not behave like any known comet or asteroid. It showed no detectable coma or tail despite passing relatively close to the Sun. Its brightness fluctuated rapidly, suggesting a shape so elongated it bordered on unbelievable, perhaps 10 times longer than it was wide, like a shard of stone or a splinter of cosmic glass. Some speculated it might be flat, like a pancake, tumbling erratically as it reflected sunlight. Whatever its shape, it was unlike anything observed before. And then came the greatest mystery. As it drifted away from the Sun, its trajectory changed slightly, as though it were being pushed by a gentle, unseen force. Normally, such non-gravitational acceleration is caused by outgassing, the release of vapor from a comet warmed by sunlight. But Oumuamua produced no visible gas or dust. Not even the most sensitive instruments could detect a trace of cometary activity. It was as if the object was whispering secrets but refusing to speak them clearly. This strangeness led to an explosion of theories. Some scientists argued it was indeed a comet, just an unusual one. Others suggested exotic ideas. Perhaps it was a fragment of a tidally disrupted planet, or a shard of nitrogen ice from a distant Pluto-like world, or even a naturally occurring iceberg of hydrogen ice. A minority entertained the possibility of artificial origin, not as a serious conclusion, but as an acknowledgement of how unprecedented the data appeared. That debate revealed more about human imagination than about the object itself, but it underscored the impact Oumuamua had on the field. It forced astronomers to confront the unknown with humility. What mattered most was not the object's shape or acceleration, but the fact that it existed at all. For the first time, humanity had observed an object that formed around another star and wandered into our solar system. It had likely been drifting through space for millions or billions of years, untouched, cold, silent. It had seen stars rise and fall across the galaxy as it drifted among them. And now it had brushed past the Sun, offering a fleeting look at material from another system. Oumuamua set a precedent. It proved beyond doubt that interstellar objects were real and potentially abundant. It opened the door for future discoveries. It challenged astronomers to improve their detection methods, refine their models, and expand their expectations. After Oumuamua, no one could claim ignorance of the galaxy's wandering debris. Its existence also reframed the detection of every subsequent object. When 3I Atlas appeared, it carried traces of that earlier shockwave. Scientists recognized the signs sooner. They analyzed it more quickly. They approached it with a framework that had not existed before Oumuamua rewrote the rules. Oumuamua was the early echo that awakened the field, the first true interstellar scout. Its passage through the solar system lasted only weeks in terms of valuable observation time, but its impact will resonate for decades, perhaps centuries. It changed the questions scientists asked, and it sharpened their eyes to the sky. It was the message the galaxy sent before we even realized we were listening. Before the astronomical world could absorb the shock of Oumuamua's arrival, the universe decided that one anomaly was not enough. A second visitor appeared, a comet so undeniably interstellar that it erased every lingering doubt left by the first. It was named 2I Borisov, after the amateur astronomer Gennady Borisov, who discovered it from his personal observatory in Crimea. His sighting was not just a scientific triumph, it was a cosmic announcement, a declaration that interstellar visitors were not isolated miracles, but recurring messengers drifting through the galaxy. If Oumuamua was the mysterious whisper, Borisov was the shouted confirmation. This second traveler behaved in ways that felt almost comforting. It did not hide behind strange shapes or ambiguous acceleration. Instead, it announced itself with familiar cometary traits that astronomers had seen hundreds of times before. An icy nucleus shedding gas, a visible coma forming as it warmed, a bright tail stretching away from the Sun. Borisov was a comet, in every recognizable sense, except for one monumental detail. It did not belong to our solar system. Its orbit was unmistakably hyperbolic, its speed too great to be bound by the sun's gravity, and its approach direction inconsistent with any population of local comets. This combination meant it had traveled from beyond the sun's influence, drifting between stars for ages before arriving. Scientists were prepared this time. Unlike with Oumuamua, they knew exactly what to look for and how urgent the task was. Observatories around the world pivoted their instruments. Spectrographs were trained on the newcomer. Telescopes observed it through every wavelength available. The brief window during which interstellar visitors remain bright enough to study is unforgiving, and the field had learned not to waste a second. Borisov offered an opportunity that could not be allowed to slip away. The first question was simple: what was it made of? If Borisov truly came from another star, then its chemistry could carry fingerprints of that foreign origin. Spectroscopic analyses began pouring in. Water vapor was detected, along with carbon-based molecules common in solar system comets. But there was a twist. The ratios of certain substances were different, similar in broad strokes but distinct in details. Some analyses revealed unusually high concentrations of carbon monoxide, far more than typically found in comets from our own system. This suggested that Borisov formed in an extremely cold region around its parent star, perhaps even farther out than where our own comets originate. Its home system could have been cooler, or younger, or shaped by processes that left different chemical imprints on its icy bodies. In those differences lay the first concrete evidence that planetary systems across the galaxy produce comets broadly similar to our own, yet uniquely flavored by their environment. It was proof that the diversity of planetary systems extends not only to their planets and stars, but down to the smallest icy fragments that wander away into the dark. Borisov became the first object whose composition offered direct insight into the chemistry of another solar system. It was like tasting the water of an alien ocean or holding a grain of sand from a distant beach. Beyond chemistry, Borisov's structure revealed remarkable information. Its stability under heating suggested that it was unaltered by significant collisions or processes that might have compacted it. Some scientists argued it was surprisingly pristine, a relic unchanged for billions of years. Others proposed that its fragility, its tendency to break apart later in its journey, showed that it was a loosely bound aggregate of ices and dust. The truth may never be fully known, but both interpretations contain wonder. Either Borisov was a nearly untouched survivor from the dawn of another system, or it was a delicate structure shaped by forces unfamiliar to our solar system. Both answers hint at how diverse the galaxy's planetary nurseries may be. One of the most compelling aspects of Borisov's arrival was how ordinary it made the extraordinary seem. With Oumuamua, there was doubt. With Borisov, there was certainty. The presence of a classic comet from another star, visible with familiar signatures, cemented the idea that the galaxy constantly ejects material into interstellar space. It also meant that countless comets like Borisov must be drifting quietly, invisible except when fate sends one close enough to the sun to awaken. Scientists realized that the solar system had probably encountered dozens or hundreds of such visitors in the past, long before humans existed to see them. Borisov also reshaped theories about how planetary systems evolve. Its presence suggested that the processes that shape such systems, especially the gravitational interactions that fling material outward, are not rare quirks but universal stages of planetary development. Whenever a giant planet forms, whenever a disk of dust thickens, whenever orbital resonances stir chaos, debris gets thrown out. If this happens in most systems, then every star becomes a factory that contributes to the galactic supply of drifting cometary fragments. This realization turns the Milky Way into a vast exchange of material. Over billions of years, planets and comets from one system may drift across the galaxy and occasionally pass through others. It is a cosmic version of cross-pollination, a mingling of materials on unimaginable timescales. The idea that fragments of ancient alien worlds might occasionally pass close to Earth without us ever noticing adds a layer of deep connection to the cosmos. The universe is not a collection of isolated islands, but a network of shared history and exchanged matter. The scientific impact was profound, but the emotional impact was equally significant. Borisov reminded humanity that the universe is active, dynamic, and far more interconnected than early models suggested. It reinforced the idea that interstellar space is not a clean void, but a river filled with ancient shards of cosmic creation. Every drifting fragment carries stories older than Earth itself, written in molecules and minerals rather than words. The arrival of such a fragment is a gift, a fleeting chance to read a page from a book that normally remains closed. And then, just as quickly as it came, Borisov began to fade. Its closest approach to the Sun energized it, but it also stressed its fragile structure. As astronomers watched, Borisov started to break apart. Its nucleus fractured, its brightness changed, its tail stretched irregularly. It was not unusual for comets to crumble under the fierce heat of the Sun, but observing an interstellar comet disintegrate in real time was a reminder of how fragile these wanderers are. They survive for millions or billions of years in the cold, only to fall apart in days or weeks when exposed to sunlight. By the time Borisov left the inner solar system, it had become a diffuse cloud of debris. It faded back into the blackness, continuing its journey outward, never to return. Its existence had lasted far longer than its visible chapter. It came from the stars, passed briefly near our own, and returned to the galactic darkness that shaped it. Yet its legacy remained. Because of Borisov, astronomers no longer hesitated when a strange new object appeared. They knew what it could be. They knew the signs. They knew the possibilities. And when 3I Atlas approached, they recognized its origin almost immediately. Borisov did not just blow the door open, it tore it from its hinges. After the revelations sparked by Oumuamua and Borisov, astronomers found themselves standing in a new reality. The once unthinkable idea that interstellar objects could regularly traverse the solar system was now an accepted part of the cosmic landscape. The universe had spoken twice, clearly, decisively, and the scientific community was listening. With improved surveys scanning the sky, researchers were prepared. They waited with a sense of expectation, knowing that another visitor would eventually appear. The only unanswered question was when. The answer came sooner than expected. Modern sky surveys like ATLAS, designed to identify potentially hazardous asteroids, capture enormous quantities of data every night. They patrol the sky systematically, comparing fresh observations with earlier ones, searching for objects that move against the fixed background of stars. It was within this relentless flow of images that the third interstellar visitor first emerged. At first, it seemed unremarkable, just another faint dot recorded across successive exposures. But the universe often hides its most extraordinary secrets behind the simplest appearances. Astronomers responsible for processing the ATLAS detections ran standard analyses. They calculated the object's trajectory, corrected for observational errors, and refined the orbital parameters. Most objects identified this way end up belonging to well-known populations: near-Earth asteroids, main-belt asteroids, long-period comets from the Oort cloud, or trans-Neptunian objects displaced by gravitational nudges. But this particular object resisted classification from the beginning. Its speed stood out first. It moved a little too quickly for its distance from the Sun. Objects bound to the solar system obey predictable velocity patterns. speeding up as they fall inward or slowing as they climb outward. But this traveler's behavior deviated from those norms. The more observations astronomers collected, the more it became clear that the usual gravitational models could not account for its motion. Then its orbit was computed, and the result was startling. The eccentricity was unmistakably hyperbolic, significantly greater than 1, well beyond the margin of measurement uncertainty. This was the cosmic signature that separated it from the solar system's native population. It was the unmistakable mark of something born around a different star, something flung away in a distant system's youth or upheaval, something that had been drifting for an unimaginable span of time. It was officially designated 3I Atlas, the third recognized interstellar object and the first to be discovered primarily through fully automated sky survey algorithms. This alone signified a remarkable shift in the field. Humanity had reached a point where its digital eyes no longer relied solely on human intuition or serendipity. Instead, machines had learned to catch faint visitors slipping silently through the solar system. Artificial intelligence and rapid imaging pipelines were beginning to weave themselves into astronomy, ensuring that no significant traveler would pass unseen. Unlike Oumuamua, whose shape sparked endless debate, and unlike Borisov, whose bright coma made it unmistakably cometary, 3I Atlas was a subtler visitor. Its brightness suggested activity, perhaps a faint coma or weak outgassing, but it did not exhibit dramatic tails or unusual shapes. It was not a flamboyant messenger, it was a quiet one, a traveler that carried its story within a modest glow of reflected sunlight and gas. Yet its subtlety made it no less significant. In some ways, it made the object more scientifically valuable. By lacking the extreme irregularities of Oumuamua or the cometary exuberance of Borisov, it provided a data point somewhere in between. It hinted at the diversity of interstellar objects, showing that they exist along a spectrum rather than in two distinct categories. There may be rocky shards, icy aggregates, hybrid bodies with patchy activity, and countless other varieties drifting unseen in the galactic sea. The discovery of 3I Atlas ignited a fresh wave of observational urgency. Telescopes pivoted toward it. Observing proposals were rearranged. Astronomers gathered whatever photometric and spectroscopic data they could. But as with all interstellar visitors, time was limited. These objects approach the Sun quickly, brighten for a short period, then fade into darkness almost as fast. Their trajectories perpendicular to the solar system's main plane often make them difficult to observe for long stretches. Even the best instruments can only steal a brief glimpse before the visitor escapes back into the void. Despite the challenges, the early data revealed tantalizing insights. The brightness curve suggested 3I Atlas was likely releasing gas and dust, making it a weakly active comet. This activity allowed scientists to infer some of the materials on its surface. The composition appeared broadly similar to that of comets from our own solar system, which reinforced a growing realization. Planetary systems across the galaxy seem to produce similar kinds of icy bodies. The processes that form comets here might be common everywhere. Dust grains, molecular ices, and primordial compounds appear to be universal building blocks, shaped by cosmic chemistry that plays out the same way around many stars. Yet its orbit hinted at something deeper. By projecting its path backward through space, astronomers discovered that the object likely came from the Milky Way's thin disk, or perhaps even the thick disk, a much older region of the galaxy populated by stars far more ancient than the Sun. If 3I Atlas did originate from the thick disk, then it could be a relic older than our entire solar system. It could have formed in a young stellar nursery more than 10 billion years ago, long before Earth existed. To hold such an object in our telescopes, even briefly, is to touch a remnant of the galaxy's early years, a page torn from a chapter of cosmic history that predates everything familiar to us. This is what made the third visitor extraordinary. Its discovery was not just another curiosity, but the start of a pattern. If 3 interstellar objects had been detected within a span of just a few years, when humanity had only recently developed the tools sensitive enough to find them, then the galaxy must be teeming with such wanderers. Their arrival was beginning to feel inevitable, almost routine. What once seemed impossible was becoming part of the astronomical landscape. The arrival of 3I Atlas represented a turning point not only in our understanding of planetary systems, but in our understanding of our place within the galaxy. We are no longer passive observers of a closed system. We are inhabitants of a dynamic, interconnected cosmic neighborhood, where ancient objects wander freely, carrying the histories of stars that have long since dimmed or transformed. They pass us silently, each one bearing lessons waiting to be deciphered. And when 3I Atlas appeared, it did more than confirm the existence of interstellar visitors. It foreshadowed what was coming, a future in which such discoveries become commonplace, where the solar system is recognized not as an isolated bubble, but as a port along a galactic highway. It was a quiet visitor, perhaps, but its message was anything but quiet. It began, as so many astronomical revelations do, with a modest alert buried in a stream of nightly detection reports. Atlas, the Asteroid Terrestrial Impact Last Alert System, had registered yet another faint object drifting across the sky. Its coordinates were plotted, its preliminary brightness measured, and its motion compared to known objects. Nothing about it screamed for attention. Nothing announced its significance. It was just another point of light recorded by a survey whose primary mission was planetary defense, to find anything that might threaten Earth. But the universe often hides its most extraordinary stories in the mundane. The discovery of 3I Atlas was not heralded by drama, nor by a sudden spike in brightness, nor even by an unusually rapid motion on the detection images. Instead, it emerged through patient, methodical analysis. Atlas watched the skies through 2 telescopes, one on Helicala, the other on Mauna Loa, constantly scanning for moving objects. These robotic eyes gather data at a rate far beyond what any team of human observers could process manually. Every night, thousands of potential objects are flagged, most of them known or quickly identifiable. But in this endless churn of data, occasionally something refuses to fit. The first flagged observations of 3I Atlas were unremarkable. A faint magnitude, a clear shift between frames, a calculated trajectory suggesting a new object. It entered the Minor Planet Center's processing pipeline like any other candidate. Astronomers accustomed to seeing countless detections of transients had no reason to suspect that this dim point of light carried a secret that would ripple through the field. The turning point came when more data arrived. Atlas re-observed the object during subsequent nights. Additional observatories contributed follow-up detections. Each new position sharpened the orbit calculation, and with each refinement came a growing sense of unease. Something was off. The speed of the object did not align with expectations. The motion perpendicular to the ecliptic plane, a direction rarely used by solar system objects, seemed too steep. The distance and the brightness didn't perfectly match any known population of distant comets. Most objects found by Atlas fall into well-studied categories. Some are near-Earth objects, small asteroids whose orbits occasionally cross Earth's path. Others belong to the main asteroid belt between Mars and Jupiter. Still others are long-period comets from the Oort cloud, diving in from the distant reaches of the Sun's gravitational influence. Each category comes with predictable orbital traits, but this new object didn't match any. It behaved like a foreigner trying to blend in, its disguise thinning under scrutiny. When the first orbital solution arrived, the numbers were startling. The eccentricity was not merely high, it was unambiguously hyperbolic. Not borderline, not uncertain, firmly above the limit that defines a binding orbit. This single data point elevated the faint Atlas detection from a routine discovery to an interstellar event. The solar system's gravitational architecture only produces hyperbolic trajectories in rare circumstances, usually involving strong planetary encounters or close interactions. But nothing in the preliminary orbital path suggested a recent planetary flyby. The object was already inbound when first detected, far beyond the realm where planets could significantly alter its momentum. This meant the hyperbolic trajectory was not temporary or induced. It was inherent. It was a fingerprint from its origin. Almost immediately, the Atlas team and collaborating astronomers around the world began running backward propagating orbital simulations through galactic models. These simulations track how an object would have moved through space before entering the heliosphere. Even with early uncertainties, the backward projections showed that 3I Atlas had approached the solar system with a velocity exceeding what could be accounted for by solar gravity. It was drifting freely in interstellar space before its path crossed ours. It became clear this was an interstellar visitor. Once that realization spread, the object was given its new designation. 3I signified the third recognized interstellar object in human history. The I classification had only recently been created after the discoveries of Oumuamua and Borisov. Before then, astronomers had no need for a category dedicated to visitors from beyond the solar system. Now it had become essential. The formal designation was more than a label. It was an acknowledgement that the expanding frontier of astronomy had widened yet again. Humanity was learning to recognize members of a population it had long suspected but never fully observed. 3I Atlas joined an exclusive list. But the list had begun to grow at a pace hinting at something profound. These visitors were not rare. They were common enough that surveys like Atlas, which had only been fully operational for a few years, could detect multiple interstellar objects within a short span. Once the object's identity became known, attention flooded toward it. Observatories of all sizes, from backyard telescopes to large professional instruments, attempted to capture images. Time on major telescopes is always in high demand, requiring proposals and approvals. But exceptions are often made for rare, time-sensitive cosmic events. And an interstellar visitor is undoubtedly one of those events. The object brightened as it approached the Sun, allowing more detailed observations. It displayed signs of faint activity, perhaps a subtle coma or low-level gas release. This activity indicated the presence of volatile ices on its surface, reacting to the growing warmth of the Sun. But unlike Borisov, which exploded into flamboyant cometary behavior, 3I Atlas remained modest. Its visibility improved, but it did not become a spectacle. This subtlety made it harder to study, but no less important. The faint tail-like structure was difficult to distinguish from background noise. Still, several analyses showed that the object's surface was active enough to release dust and gas, confirming its identity as a cometary body. The question that immediately followed, what kind of comet? Was it icy like typical comets from our solar system? Or was it composed of exotic compounds rarely seen locally? Did it contain dust from a disk around a star unlike our Sun? In its faint glow lay answers not merely about the object itself, but about the environment it came from. But before those questions could be tackled, astronomers needed something more fundamental: certainty of its origin. They needed to know whether this hyperbolic orbit was truly due to an interstellar origin, or whether it might be a solar system object kicked outward by a planetary encounter. They ran simulations involving Jupiter, Saturn, the giant planets, checking scenarios in which a body might be accelerated to interstellar speeds. But in all models, the object would have been detected far earlier if such an encounter had occurred. It simply didn't add up. The hyperbolic path was genuine. This confirmed discovery reshaped the next steps in the field. The astronomy community began to take interstellar detection not as a novelty, but as an emerging discipline. Each object brought different insights. Oumuamua showed the unexpected. Borisov showed the familiar. And now 3I Atlas showed the subtle. an object that resembled a comet but belonged to none of the known families. Its presence raised questions about what lies between the extremes of interstellar objects. It also revealed how much we still do not know about the galaxy's reservoir of drifting debris. If this visitor was faint enough to nearly slip past detection, and yet was discovered anyway, how many others had passed unseen? How many more would come in the coming years as sky surveys grew more sensitive? The answer was clear: countless. But each detection, no matter how faint, carries meaning. Each one expands our understanding of the galaxy's forgotten stories. 3I Atlas, discovered quietly and almost anonymously, was one such story, written across millions of years and delivered to our solar system for a fleeting moment of recognition before slipping again into the void. The night sky is vast, but the tools humanity has built to study it have grown remarkably powerful. Among them, the Atlas survey stands out as a sentinel, a pair of telescopes tirelessly scanning the heavens for anything that moves where it shouldn't. Though its purpose was originally conceived as a shield for Earth, designed to detect incoming asteroid threats before they could strike, Atlas has become something more: a gateway for discovering objects that defy the gravitational logic of the solar system. It was through this gate that 3I Atlas entered human awareness. To understand how remarkable this discovery was, one must understand the nature of Atlas itself. Unlike giant observatories perched on mountaintops, armed with enormous mirrors and state-of-the-art instruments, Atlas uses relatively modest optics, 50-centimeter telescopes that might seem unremarkable compared to mammoth facilities like Keck or the Very Large Telescope. Yet Atlas's power comes not from size, but from its purpose and its strategy. It surveys the entire visible sky several times each night, using rapid exposure cycles and automated detection systems to identify anything that moves. It is not an instrument of precision, but of vigilance. The system was created with planetary defense in mind. The Earth, after all, resides in a cosmic shooting gallery. Small objects impact the planet regularly, and larger objects, though rare, pose catastrophic potential. Early detection can mean the difference between preparedness and disaster. Atlas was built to spot asteroids days or weeks before potential impact. Its wide-field design captures enormous swaths of the sky. Its software analyzes images in real time, identifying transient objects that shift against the unmoving stars. But the beauty of such a system is that it doesn't discriminate between the dangerous and the extraordinary. It detects both. Atlas operates from 2 locations in Hawaii, Haleakala and Mauna Loa. Each telescope provides panoramic views of the sky, scanning from horizon to horizon. They work in tandem, covering vast areas so quickly that the entire visible sky can be imaged multiple times per night. This repetition is crucial. By comparing images taken hours apart, Atlas identifies objects that move: asteroids, comets, satellites, even space debris. The software flags these moving points, sending alerts for human astronomers to review. The advantage of such an approach is simple: Atlas sees things others miss. Giant telescopes, though powerful, cannot monitor wide regions of the sky frequently. Their strength lies in detail, not coverage. Atlas sacrifices detail to gain surveillance capability. And it is surveillance that brings interstellar objects to light. When 3I Atlas first appeared in its images, it was faint, barely above the threshold of detection. The initial frames showed only a small shift, subtle enough that it could have been overlooked had the system not been built for relentless scanning. But Atlas caught it. The automated pipeline measured its motion, compared it to parallax effects, ruled out noise, and flagged the object as something worthy of follow-up. Next came the crucial step: multiple observations over multiple nights. Atlas returned to the same region, capturing new positions. Other observatories, alerted by the Minor Planet Center reports, began contributing data. With each observation, the orbital solution sharpened. It became increasingly clear that the object's motion could not be explained by any known solar system population. The telescopes themselves performed without fanfare. They simply did what they were built to do: observe everything relentlessly. Their hardware did not grasp the significance of the faint point of light passing across their detectors, but their software did. The automated systems processed the images, measured the object's brightness, estimated its potential trajectory, and passed the data forward. It was a symphony of technology functioning exactly as intended, but revealing something unexpected. This synergy between modest hardware and advanced algorithms is what made the discovery possible. Atlas is a testament to the idea that transformative discoveries don't always require grand instruments. Sometimes they come from persistence, from breadth of observation, from the willingness to look at everything rather than only the predictable. It is also a symbol of how modern astronomy has changed. No longer do astronomers sit for hours examining photographic plates by eye. They rely on software, machine learning, automated pattern recognition, and global coordination. The discovery of 3i Atlas showcases this evolution. It represents a new era where the sky can be scanned continuously, where faint objects cannot simply slip by unnoticed, and where the tools of detection operate tirelessly even when human astronomers sleep. These telescopes caught not only an interstellar visitor, but also the beginning of a trend. With each passing year, surveys like Atlas, Pan-STARRS, and the upcoming Vera Rubin Observatory detect more objects moving through the solar system. Most are mundane, but some are extraordinary. And each extraordinary detection reshapes the map of cosmic understanding. 3i Atlas was not bright, not spectacular, not visually dramatic, but it was moving in a way that told a story. The telescopes that spotted it may not be the most powerful ever built, but they are among the most vigilant, and sometimes vigilance is what brings the universe's secrets into view. In the end, the discovery of 3i Atlas is not just a story of a faint object crossing the sky. It is the story of how modern astronomy has expanded its reach, how the tools we build, wide field, automated, tireless, allow us to glimpse things that would have remained forever invisible without them. It is the story of how even a small telescope can witness the passage of a cosmic traveler born around another star. And above all, it is the story of how our eyes on the sky have become sharper, wider, and more prepared than ever to see the galaxy's wandering messengers drift through our cosmic home. From the moment 3i Atlas was detected, astronomers began searching for its identity in the small hints scattered across the data. The universe rarely announces itself in full clarity. Instead, it offers fragments, breadcrumbs of information that invite curiosity and demand interpretation. And 3i Atlas was no exception. Its first clues emerged not from dramatic observations, but from subtle deviations, small inconsistencies that revealed more than they concealed. The initial suspicion that the object was different came from its speed. Speed itself is rarely enough to prove anything. Plenty of comets and asteroids move quickly as they fall inward or swing past planets. But speed must be interpreted in context. Distance from the sun, direction of travel, inclination, and shape of orbit all influence what velocities are reasonable. When astronomers plotted the early motion of 3i Atlas, they noticed it was simply too fast for its position. Not dangerously so, not enough that a casual observer would notice, but enough that careful orbital fitting revealed an unusual energy profile. Objects bound to the sun follow the rules of celestial mechanics. Their speeds correspond to their distances in predictable ways. But 3i Atlas seemed to ignore some of these rules. The sun's gravitational pull did not appear to have the usual influence on its trajectory. It moved as though it had come from somewhere far beyond the reach of our star, carrying a memory of motion imprinted long before it entered the heliosphere. Then there was the inclination. Most objects in the solar system orbit close to the ecliptic plane, the flattened disk where the major planets and most smaller bodies reside. This disk is a relic of the solar system's birth, a rotating cloud of gas and dust that collapsed and flattened under its own angular momentum. Over billions of years, nearly everything formed from that disk remained aligned with it. Even long-period comets, which arrive from all directions, show statistical clustering that reflects their dynamical evolution within the Sun's extended gravitational domain. But 3I Atlas approached on a path that seemed indifferent to this architecture. It came in steeply, at a significant angle to the ecliptic, as though unaware that most of the solar system's mass sits within a narrow plane. This was not unheard of. Borisov also arrived on an inclined path, but the combination of high inclination and excessive velocity formed a signature pattern. Something about it hinted at a journey through galactic space rather than a long slingshot through the solar system's outer reaches. Brightness variations added another layer of intrigue. The object flickered slightly over the course of its observations, not dramatically enough to indicate a wildly elongated shape like Oumuamua, but enough to suggest that it might be rotating with uneven surface reflectivity, or perhaps shedding small amounts of dust. This flicker, the object's subtle heartbeat, offered clues about its size, shape, and composition. It hinted that sunlight was reacting with materials long frozen in darkness, awakening volatiles that had not been exposed to warmth for millions of years. Faint hints of activity quickly emerged. Although early images did not reveal a pronounced coma, careful photometric analysis suggested the possibility of low-level gas release, evidence that the object might be a cometary body rather than a rocky one. Unlike Borisov, which displayed classic comet behavior almost immediately, 3I Atlas was reserved. Its activity was subtle enough that some astronomers wondered whether it might belong to a class of objects only weakly reactive to sunlight, perhaps due to an unusual composition or a surface crust hardened by millennia of cosmic rays. Comets from our own solar system often display a range of behaviors depending on their histories. Some erupt with activity the moment they feel the sun's warmth. Others require close approach before their ices begin to sublimate. If 3I Atlas was an interstellar comet, its surface may have been altered by cosmic radiation in ways that made its outer layers more resilient. Over millions of years of deep space exposure, surfaces can develop hardened crusts of processed material, trapping volatiles beneath. Only when sunlight penetrates or cracks the crust do gases begin to escape. This interpretation aligned with some early spectroscopic hints. Though the object was faint, a few observations suggested the possible presence of carbon-based molecules. Not unusual for comets, but intriguing given the uncertainties. More importantly, nothing in the data matched the profile of a typical asteroid from our own system. It neither reflected sunlight like a rocky asteroid, nor behaved like dormant comet nuclei found in the Jupiter family population. It slipped between categories, resisting classification as if to emphasize that it came from a place where our categories did not apply. Another clue emerged from orbital uncertainty tracking. When models attempted to map the object's past trajectory, they encountered something striking. No gravitational interaction within the solar system could produce the hyperbolic energy observed. For an object to be thrown onto such a path, it would require a close planetary encounter, one that would dramatically alter its trajectory and impart enough kinetic energy to exceed the sun's binding power. But 3I Atlas had never passed near any of the giant planets. Its inbound trajectory was already hyperbolic by the time it was first detected. This sealed the conclusion: its origin was external. Some astronomers attempted to imagine whether it could have been perturbed from the Oort cloud by a passing star. But even those scenarios fell apart. Objects ejected from the Oort cloud by stellar perturbations gain only modest velocity increases, nowhere near the speed of 3I Atlas. The energy budget simply didn't balance. A few speculative ideas surfaced briefly. Could it have been a long-forgotten fragment of an early solar system collision? Could it have been cast outward by interactions billions of years ago and now returning? But these hypotheses required an impossible circularity, an object leaving the sun's influence only to regain the precise hyperbolic speed needed to mimic an interstellar origin. Nature rarely conspires in such contrived ways. The simplest explanation was also the most profound. 3I Atlas came from another star system. As more data arrived, this conclusion solidified. The object's brightness behavior, orbital shape, and inbound speed painted a consistent picture. It was an outsider, an icy messenger that had wandered through interstellar space for ages before encountering the sun. But perhaps the most compelling clue of all came not from data, but from the broader context. The universe had delivered 2 interstellar visitors in recent years. Now a third had appeared. Patterns do not emerge from isolation. They emerge from repetition. And the repetition of interstellar detections signaled a truth long expected, but only now proven. The galaxy is full of wanderers. 3I Atlas was simply the latest to reveal itself. And with each clue, it whispered a message that stretched across light years. We are part of a larger cosmic ecosystem, one in which objects do not remain bound to their origins, but drift freely, carrying stories etched into their surfaces by stars we will never know. If there is a single trait that defines an interstellar object, it is its orbit. Chemistry offers hints. Brightness variations suggests shape. Activity reveals composition. But the orbit, the cold, mathematical curve traced through space, is what tells the truth. It is the signature of a traveler that does not obey the sun's gravitational authority. And with 3I Atlas, the orbit was unmistakable from the moment the data achieved clarity. To understand why the trajectory of 3I Atlas was so revealing, one must step briefly into the language of orbital dynamics. Every object bound to the sun moves on an ellipse. Some ellipses are nearly circular, like those of the planets. Others are stretched into long ovals, like the paths of comets returning from the distant Oort cloud. But no matter how elongated, an ellipse is still a closed loop. It has a beginning that leads back to its end. It is a path that repeats, predictable and tethered to the sun's mass. A hyperbola is not a loop. It is an open doorway. When an object moves on a hyperbolic trajectory, it means the gravitational pull of the sun is not enough to capture it. The sun slows it as it approaches and accelerates it as it leaves, but never enough to bind it. Such an object does not orbit, it passes. It arrives from infinity, arcs briefly within range of the solar system, and then returns to infinity. It is a visitor, not a resident. 3I Atlas traced such a path with clarity that left no room for doubt. The key number is eccentricity, a measure of orbit shape. An eccentricity of 0 is a circle. Between 0 and 1 lies the family of ellipses. At exactly 1 sits the parabola, the dividing line between bound and unbound. Above 1 lies the realm of hyperbolas, the trademark of interstellar travelers. When astronomers calculated the eccentricity of 3I Obuta, it was not mildly above 1, as might occur from measurement noise or a near-parabolic long-period comet. It was significantly greater, so far beyond the threshold that nothing within the solar system could have plausibly nudged it into such a path. This object was born hyperbolic. This distinction matters. Hyperbolic comets can exist within the solar system under rare circumstances. A close encounter with a giant planet, especially Jupiter, can fling a comet onto a hyperbolic escape trajectory. This has happened before, but such events leave detectable footprints. The path curves dramatically near the planet. The speed increases as momentum is exchanged, and the orbital parameters betray a recent gravitational kick. 3I Obuta showed none of these traces. Its path inbound was already steep, already unbound, already carrying too much velocity for any solar system body to have altered it recently. This alone would have been enough to confirm its interstellar origin. But the story deepened. When orbital simulations were run backward, tracing the object's likely path through space, they revealed a journey that did not intersect any configuration consistent with a solar system origin. Instead, the path extended outward, in a trajectory consistent with long-term drift through the Milky Way. It moved not like an object recently perturbed by a planet, but like one whose velocity had been shaped by the gravitational environment of the galaxy itself. More intriguingly, its trajectory did not align cleanly with the distribution of long-period comets entering from the Oort cloud. Those comets approached the solar system from all directions, but their velocities clustered near the parabolic threshold. They carry just enough energy to reach the inner solar system without exceeding escape velocity. Their paths are shaped by the delicate gravitational balance of the Sun and distant stars. 3I Obuta ignored that balance entirely. Its inbound velocity, when corrected for solar gravity, exceeded the energies characteristic of Oort cloud objects. The difference was not subtle, it was definitive. It painted the picture of an object that had long ago left the gravitational embrace of another star, acquiring a trajectory set by galactic dynamics rather than local perturbations. Another key indicator came from its asymptotic velocity, the speed an object has when it is infinitely far from the Sun. For bound objects, this value is zero or imaginary. For hyperbolic objects, it is real and positive. The asymptotic velocity of 3I Obuta was roughly 26 kilometers per second, too high for any slingshot from the Sun's planets, too high for an Oort cloud ejection event, and too aligned with expected velocities of interstellar debris in the Milky Way's disk. Its path through the solar system also revealed its indifference to gravitational shaping. Bound objects typically show resonance features, orbital families, and known dynamical patterns. 3I Obuta didn't. Instead of approaching near the ecliptic plane, it came from a steeper angle, one typical of objects drifting through the thick wash of galactic orbits rather than the organized structure of the solar system. Its trajectory resembled a straight line, bent only by the Sun's influence. It arrived, curved slightly, and departed, forever. For astronomers, this simplicity is profound. Most objects engage in a complex gravitational conversation with the solar system. They are nudged by planets, shaped by past interactions, and influenced by perturbations. Their orbits tell stories of migration, collisions, and resonances. But 3I Obuta was a stranger passing through a foreign land. It interacted minimally, like a ghost slipping through a room without touching anything. It offered no allegiance to the Sun, no repeated path, no inclination toward returning. This unbound path is more than geometry. It is biography. It tells us where the object has been and where it cannot go. It has been drifting for ages. It cannot stay. The trajectory reflects a journey shaped by the galaxy itself, by the pull of spiral arms, by the influence of giant molecular clouds, by the subtle tug of passing stars. It may have been wandering since before the Sun was born, tracing a route that spans epochs older than life on Earth. And now, having brushed briefly past the Sun, it continues outward. Its hyperbolic escape guarantees that humans will never see it again. Whatever secrets remain on its surface will drift into darkness, locked within its ices until the faint radiation of interstellar space erodes them away. Its path cannot be bound, not by the Sun and not by us. And in that unbound trajectory lies the majesty of interstellar visitors. They remind us that the solar system is not a closed world, but a waypoint, a crossroads in a galaxy full of wanderers. The early data on 3I Obuta painted a picture that was both subtle and deeply revealing. What made the object extraordinary was not any single trait, but the convergence of small details, each one unassuming on its own, but together forming a portrait of something unmistakably foreign. Interstellar visitors rarely announce themselves with spectacle. Instead, they whisper their identity through quiet irregularities. And 3I Obuta whispered loudly enough that astronomers quickly recognized they were witnessing something remarkable. One of the first signs that 3I Obuta was extraordinary lay in its brightness behavior. Unlike Borisovov, which erupted with classic cometary activity, 3I Obuta displayed a subdued yet consistent glow. Its magnitude curves suggested a surface that was active but restrained, releasing dust and gas in a steady, almost patient manner. This behavior hinted at a composition different from the well-studied comets of the solar system. It suggested that the outer layers of 3I Obuta were hardened by ages of cosmic radiation, a process that forms an insulating crust over time. Beneath that crust, untouched for millions of years, ices remained locked away until the warmth of the sun began to coax them out. This type of activity is not uncommon among long-dormant comets, but for an interstellar visitor, the implications run deeper. Cosmic rays pervade interstellar space with a ferocity unmatched in the inner solar system. Over eons, they bombard the surfaces of drifting objects, chemically altering their outer layers. Molecules break, recombine, and form complex structures that coat the object's skin like an ancient varnish. This transformed crust can suppress outgassing until the heat becomes strong enough to penetrate, making activity patterns more difficult to interpret. In the case of 3I Atlas, the gentle, persistent activity suggested that sunlight was interacting with materials that had not been warmed since long before the Earth formed. Spectroscopic attempts, though limited by the object's faintness, captured tantalizing results. Some observations hinted at emissions associated with carbon-bearing compounds, possibly CN or C2, molecules often found in active comets. But detecting them at such distances was not easy, and the data remained sparse. Still, the hints were enough to suggest that 3I Atlas shared chemical traits with comets from our own system, albeit potentially shaped in different proportions or under different conditions. Its dust behavior offered another clue. When astronomers modeled the dust tail, subtle though it was, they found that the particles seemed to follow trajectories consistent with small grain ejection. The dust grains were likely fine, perhaps micron-sized, suggesting that the object was shedding material with minimal force. Such grains react strongly to solar radiation pressure, causing them to disperse more quickly. This subtle dust release fit with a scenario where 3I Atlas had a delicate surface, lightly bound, prone to sloughing off material in thin layers as it warmed. The combination of light activity, faint dust release, and muted gas emissions painted the picture of a body with a long and complex history, one shaped not by the sun, but by interstellar space. But perhaps the most extraordinary sign of all emerged from its trajectory relative to the solar system's galactic motion. The Sun moves through the Milky Way at a considerable speed, about 220 kilometers per second, dragging the planets with it in a grand orbit around the galactic center. Interstellar objects drifting in the thin disk of the galaxy often share some component of this motion. This results in typical relative velocities that fall within a specific range. When astronomers analyzed the inbound velocity of 3I Atlas, they found that it matched surprisingly well with expected distributions of objects drifting through the galactic thin disk. This alignment suggested something profound. 3I Atlas was not a rogue anomaly, launched violently from its home system. Instead, it appeared to be part of a slow, quiet stream of galactic debris, objects ejected from countless planetary systems over billions of years, drifting serenely through the Milky Way. This gentle motion, in line with the Sun's own orbit, meant that the object was likely not the result of a catastrophic event, but of the ordinary, repeated, universal processes that sculpt planetary systems across the galaxy. This made 3I Atlas extraordinary not because it was rare, but because it was representative. It hinted at a vast, unseen population of interstellar objects that populate the galaxy. Quiet, dim, ancient bodies that slip between the stars unnoticed until they encounter a gravitational well large enough to capture attention, even if just briefly. Objects like this carry the chemical fingerprints of processes that occurred around distant suns long ago. And unlike Oumuamua, whose strange shape and behavior defied easy categorization, 3I Atlas was almost comforting in its familiarity. It showed that interstellar objects are not necessarily exotic anomalies. They may be ordinary comets shaped by the same physical laws that govern our own. Yet ordinary does not mean unremarkable. The ability to detect and study even the faintest signatures of an interstellar object is a scientific triumph. Every bit of dust released by 3I Atlas, every photon reflected off its surface, every molecule sublimated into space carried information about its long journey. Even the fact that its activity was subdued rather than dramatic offered insights into what happens to cometary materials after immense stretches of time in the cold. One particularly extraordinary clue came from attempts to trace its orbit backward through the galaxy. Early results suggested a possible origin in the thin disk, but there were hints, small, statistically delicate hints, that it might have come from the thick disk instead. The thick disk is a region of the Milky Way populated by ancient stars, relics from the galaxy's early formation. If 3I Atlas originated there, it would make the object older than the solar system by billions of years. It could have been wandering since a time when the Milky Way was still assembling itself, when the Sun was just one among many stars forming in a chaotic environment. Though the data was not definitive, the possibility alone elevated the object's significance. To hold in our telescopes, briefly, faintly, an object older than Earth itself is to glimpse a fragment of the galaxy's early history. One can imagine it being born in a disk around an ancient star, ejected by gravitational interactions during an era when planets were still forming, then drifting into interstellar space long before our world cooled enough for oceans to appear. These extraordinary signs, the muted activity, the cosmic ray-hardened crust, the dust behavior, the orbital alignment, and the possible ancient origin all combine to paint a portrait of 3I Atlas as a quiet messenger with an epic biography. Every aspect of its presence echoed its heritage as a wanderer, shaped not by our sun, but by the galaxy. But perhaps the most extraordinary thing was this. Despite its faintness, despite the limited data, despite the fleetingness of its visit, astronomers could still read its story. Small hints, minor details, subtle deviations. Together, they formed the unmistakable signature of an interstellar traveler. In astronomy, an orbit is more than a path. It is a biography. A comet's orbit tells you whether it was born near the Sun or in the distant Oort cloud. An asteroid's orbit reveals whether it belongs to a stable family or is the fragment of a catastrophic collision. And an interstellar object's orbit tells you not only that it came from outside, but often how long it has been traveling, what shaped its motion, and what environments it may have passed through. For 3I Atlas, the orbit was the key that unlocked every other insight. Once enough observations had been gathered, astronomers fed the data into increasingly refined orbital models. With each passing night, the error bars shrank. The trajectory sharpened. The mathematical representation of the object's path grew more precise. And what emerged from this refinement was a picture of motion unlike anything produced within the solar system. Its hyperbolic eccentricity stood out immediately. But eccentricity alone does not tell the full story. It only tells that the object is unbound. The details beyond eccentricity reveal the depth of its journey. One of the most critical parameters was its asymptotic velocity, the speed at which the object was traveling when it was infinitely far from the sun's gravitational influence. This quantity is derived by calculating the object's trajectory backward and removing the effect of the sun's gravity from the equation. The result is the object's true interstellar velocity, the speed it had long before encountering our solar system. For 3I Atlas, this velocity was substantial, around 26 kilometers per second relative to the sun. More importantly, it aligned well with typical motion in the galactic thin disk. This suggested that the object was not moving erratically but following the galactic rotation, a sign that it had been drifting for an immense time, gradually shaped by the large-scale gravitational field of the Milky Way. This smooth motion implied a long, stable interstellar journey. But the orbital analysis revealed more. When astronomers attempted to trace the object's path backward through the galaxy, they integrated the orbit through models of the Milky Way's gravitational potential, accounting for the pull of the galactic disk, the bulge, the halo, and passing stars. These simulations showed that the object had not passed particularly close to any known star in the recent past. In fact, for millions of years, its path appeared relatively unperturbed, suggesting that it had not been recently ejected from a planetary system. Instead, its trajectory hinted at an origin far in the past, likely tied to an event long lost to history. This is one of the profound truths of interstellar objects. By the time they reach us, the story of their ejection has faded into obscurity. Stars move, clusters drift apart, orbits evolve. Any hope of identifying the specific system 3I Atlas came from was immediately dashed by the sheer magnitude of galactic motion. Over millions of years, even small uncertainties in stellar positions accumulate into enormous separations. The galaxy is too dynamic, too chaotic for such precise tracing. But even without identifying a specific birthplace, the orbit still revealed possibilities. One scenario emerged with particular strength. 3I Atlas may have originated from the debris of a planetary system that once orbited a star in the thin or thick disk. The thin disk scenario suggested a relatively young birthplace. The thick disk scenario pointed to something far older, perhaps a remnant from a system born in the early era of the galaxy when star formation was more chaotic and violent. The orbital inclination relative to the galactic plane also offered clues. Although the geometry made precise interpretation difficult, it hinted that the object's motion was not entirely aligned with the thin disk. This added weight to the thick disk possibility, though the evidence remained circumstantial. Orbit analysis also allowed scientists to estimate how long the object had been wandering. Not a precise age, such a number is impossible to determine from trajectory alone, but an estimate of the minimum time since it was last gravitationally bound to a star. For 3I Atlas, this timescale was enormous. It had not encountered any significant gravitational interactions for at least several million years. Some models suggested tens of millions, others hinted at hundreds. The possibility of billions lingered quietly in the background, a poetic reminder that the galaxy does not measure time in human lifetimes. Orbital modeling also revealed that the object was not part of any recognizable stream or family of interstellar objects. Some scientists hypothesized that interstellar debris ejected from young clusters might travel in coherent streams for a time before dispersing. But 3I Atlas appeared to drift alone. This loneliness was typical. Interstellar space is vast, and objects spread out quickly. Over millions of years, even slight velocity differences lead to enormous separations. The orbit also showed that 3I Atlas was not significantly affected by any planets during its passage through the solar system. It did not come close to Jupiter or Saturn. It did not experience gravitational bending that could alter its velocity enough to be noticeable. In fact, its trajectory curved only gently as it passed the Sun, like a stone skipping across a pond without slowing. This clean, unperturbed arc allowed astronomers to calculate its orbit with exceptional confidence. Yet perhaps the most profound revelation was psychological rather than mathematical. Studying the orbit of 3I Atlas brought a realization that every interstellar object carries a story beyond human reach. We can estimate its velocity, we can model its path, but we cannot read the moment of its birth. We cannot know the star it once orbited. We cannot see the planetary system it once belonged to. Its origin remains written in a language the universe has not yet taught us to fully decipher. And yet, the orbit gives us enough to know one thing with certainty. 3I Atlas did not fall into our world by accident. It is part of a vast, ongoing exchange of matter between stars, a quiet current in the galactic sea. The orbit reveals that our solar system is not isolated or immune. It is one node in a galaxy-wide network of drifting relics. And 3I Atlas is one such relic, ancient, unbound, and indifferent to the systems it passes. Its orbit is its biography, a biography written across millions of years of silent travel through the Milky Way. By the time astronomers confirmed that 3I Atlas was unbound from the Sun, another question rose naturally to the surface. Where had it been before it arrived? Every interstellar object carries the invisible imprint of its long journey through the galaxy, a path shaped by gravitational currents and star-borne encounters too subtle to see, yet too powerful to ignore. To unravel this path is to trace the object's silent footsteps across the Milky Way, to peer backward through time, not through light, but through motion. The difficulty of this endeavor cannot be overstated. The galaxy is not a quiet, orderly stage where objects slide in predictable lines. It is a turbulent, shifting environment where stars migrate, spiral arms sway like slow-moving tides, and the gravitational field reorganizes itself every million years. Interstellar objects drift within this dynamic web, their trajectories molded by forces that unfold on timescales far longer than the human mind can comfortably grasp. But even within this cosmic chaos, patterns exist. The first step in tracing 3I Atlas's history was to integrate its motion backward through the gravitational field of the Sun, removing the acceleration imparted by the star's influence. This gave astronomers a purely galactic trajectory, a motion that reflected the object's behavior long before its encounter with our solar system. The moment this transformation occurred, the object's identity became clearer. Its velocity profile matched those of countless stars drifting within the Milky Way's thin disk. This suggested a profound truth. 3I Atlas was not a rogue, not a projectile hurled violently from a catastrophic event. Instead, it was a member of the quiet, ancient river of matter that flows through the galaxy. It moved with the rhythm of the stellar disk, its velocity echoing the age-old dance of suns circling the galactic center. The Milky Way is a barred spiral galaxy, its structure defined by arms of star formation, by dark matter halos, and by the rotation curves that dictate how stars move. Most stars inhabit the thin disk, a flattened region expanding across tens of thousands of light-years. Within this disk, stars, dust, gas, and debris revolve around the galactic center in broad, sweeping orbits. Although individual stars may drift apart, the collective motion forms a kind of vast current. 3I Atlas appeared to be part of this current. Its motion aligned so closely with the disk's rotation that it seemed almost native to it, as though it had been drifting there for longer than Earth itself has existed. To map its galactic trail, astronomers fed the object's velocity and position into computer models of the Milky Way's potential. These models simulate the galaxy's gravitational forces, including the pull from the central bulge, the disk, and the massive dark matter halo surrounding everything. They also incorporate data about the positions and motions of nearby stars, allowing for the possibility that the object passed close to another sun at some point. The simulations revealed a journey that was both simple in form and profound in implication. For millions of years, perhaps tens of millions, the object followed a smooth, unremarkable path through the thin disk. It did not weave chaotically. It did not undergo violent perturbations. Instead, it drifted quietly, shaped gently by the arc of the galaxy's gravitational field. This quietness told a story. It meant that the object had not been recently ejected. A recent ejection would have produced a velocity inconsistent with the thin disk's flow. It also meant that the object had not passed dangerously close to any star for a long time. Close encounters impart noticeable gravitational kicks, measurable in the object's velocity vector. But 3I Atlas displayed none of these signatures. Its path whispered of age, a deep age. The farther astronomers attempted to trace the object's history, the more uncertain the simulations became. Even small errors in measurements, when projected backward millions of years, ballooned into enormous uncertainties. After a certain point, the models stopped pointing to any meaningful location. The galaxy had moved too much, too many stars had migrated, too many gravitational influences had intertwined. The trail dissolved into a haze of probability, leaving only broad possibilities. One such possibility is deeply compelling. 3I Atlas may have originated in the thick disk. The thick disk is an older component of the galaxy, a collection of ancient stars, many over 10 billion years old, orbiting above and below the thin disk, like an elevated roadway. Stars in the thick disk tend to have lower metallicity, meaning they contain fewer heavy elements. This composition reflects the nature of the early galaxy, before supernovae had enriched the interstellar medium with metals. If 3I Atlas came from the thick disk, it means its birthplace was a planetary system formed at a time when the galaxy was younger, when the spiral arms had only begun to take shape, when the gravitational environment was more chaotic. In that scenario, the object could be extraordinarily ancient. Imagine a small icy body forming in a protoplanetary disk around a young star 10 billion years ago. Picture it dwelling in the outskirts of that system, orbiting silently in the deep cold. Then imagine a moment of gravitational disruption, perhaps caused by migrating giant planets or by the passing of a neighboring star, flinging the small object into interstellar space. Once unbound, it drifted away, leaving behind its star of origin forever. It wandered through the galaxy during eras humans can barely comprehend, eras when the solar system itself did not yet exist. It was older than Earth's continents, older than our oceans, older than the first flickers of biological life. It drifted through the galaxy as the Milky Way's arms twisted, as generations of stars were born and died, as entire planetary systems emerged and faded. Such an object carries not just chemical information, but temporal information. It is a time capsule from the galaxy's early history. Even if 3I Atlas did not come from the thick disk, its motion through the thin disk still implied vast antiquity. The quietness of its journey, the smoothness of its velocity, the absence of recent perturbations all pointed to a long drift through interstellar space. Tracing the trail of 3I Atlas is a humbling exercise. It forces humanity to confront how small a time span our own existence occupies. For millions of years, before mammals emerged, before dinosaurs evolved, before the first forests grew, the object traveled unseen. It passed near stars humans will never know, glided through the galaxy's structure like a leaf on a cosmic breeze, and remained unchanged except for the slow erosion of cosmic rays. And then, by chance alone, its path intersected ours. It could have drifted 1 million kilometers higher or lower, missing the solar system entirely. A slightly different trajectory could have sent it past the Sun thousands of years before humans learned to build telescopes. But luck, or destiny, or coincidence, sent it through our sky in a generation that could understand what it was. The trail of 3I Atlas through the Milky Way is not merely a physical path. It is a story of patience, of endurance, of cosmic scale. A story written over millions of years, arriving in the human era as a faint point of light in a telescope image. And though we cannot trace that trail all the way back to its star of origin, we know enough to glimpse the enormity of its journey. It drifted across the galaxy in silence, and now, for a brief moment, it has spoken. Once the orbit of 3I Atlas was understood, astronomers sought to place it within the larger dynamic structure of the Milky Way. This was not merely a question of where the object had been, but of what its motion revealed about the broader population of interstellar wanderers. The galaxy is a layered system, composed of overlapping stellar populations, each with its own motion, chemistry, and history. Understanding which layer 3I Atlas belonged to meant unlocking a deeper understanding of its likely origin. The Milky Way is structured into several components: the thin disk, the thick disk, the stellar halo, and the bulge. These aren't neat divisions, but overlapping populations with distinct characteristics. Among them, the thin disk is the most familiar. It's where the Sun resides, where most of the galaxy's star formation occurs, and where the spiral arms sculpt patterns of gas and dust. The thick disk, perched above and below the thin disk, contains older stars with different motions. The halo extends outward in a great sphere of ancient metal-poor stars, some born in the earliest epochs of the galaxy. Each of these regions contributes to the population of interstellar objects, albeit in different ways. When astronomers examined the velocity of 3I Atlas, correcting for the Sun's motion and for the influence of the galaxy's rotation, they found that it fit very comfortably within the distribution of objects in the thin disk. This alignment was significant. It meant that 3I Atlas did not carry the high relative velocities characteristic of halo objects, nor the peculiar orbital inclinations that sometimes accompany thick disk dynamics. Instead, it moved with the quiet, steady rhythm of stars and debris that share the thin disk's rotation around the galactic center. But this did not eliminate the thick disk as a possibility. The boundary between the two disks is not sharp. Their populations blur into one another in both space and velocity. Stars born in the thick disk occasionally drift downward toward the thin disk, and vice versa. The Milky Way is an environment of migration and mixing. Over billions of years, gravitational interactions, cluster dispersal, and dynamical heating lead to an intermingling of populations. What made 3I Atlas intriguing was that its velocity placed it near the overlap between thin disk and thick disk distributions. This ambiguity invited speculation. Was it a relatively young wanderer from the thin disk, or an ancient survivor from the galaxy's early days? To answer this question, astronomers looked beyond velocity. They considered the broader astrophysical context. The thin disk is home to planetary systems with a wide range of ages, but many of them formed in relatively stable environments. Planets in these systems form from protoplanetary disks with abundant heavy elements, metals in astronomical terms. These metals help planets grow quickly and efficiently. The thick disk, being older, contains stars with far lower metallicities. If 3I Atlas came from a system with fewer heavy elements, its composition might reflect that scarcity. Lower metallicity could influence the types of ices and dust grains available during its formation, but determining this from observations proved difficult. The faintness of 3I Atlas limited spectroscopic precision. The data we did gather, while insightful, was not sensitive enough to distinguish subtle metallicity signatures. Still, certain indirect clues remained. The subdued activity, the possible carbon-bearing molecules, the faint dust release, none of these traits contradicted either disk scenario. Both environments could produce such an object. So attention turned to dynamic simulations. By projecting the object's motion backward and comparing it to the motions of nearby stars, astronomers sought to determine whether 3I Atlas might have passed near any known systems. Perhaps it came from a star whose motion through space we have catalogued. But this search quickly encountered the limits of what was possible. After a few million years, uncertainties in the object's initial position, combined with the chaotic nature of galactic motion, grew too large. The trail through the Milky Way dissolved into a cloud of potential positions. Yet even this ambiguity held meaning. If 3I Atlas were a young object, recently ejected from a planetary system in the thin disk, the simulations might reveal traces of a close stellar encounter. But the absence of such signatures hinted at something older. The object did not seem fresh from a planetary system. It seemed to have been drifting long enough that any evidence of its ejection had long since vanished into the galaxy's dynamic haze. This is what made the thick disk possibility compelling. If the object originated in the thick disk, its great age would render the question of precise origin moot. Systems that existed billions of years ago may no longer exist today. The star that birthed 3I Atlas might have evolved into a subgiant or a white dwarf, or may have drifted light years away from where it once formed. The planetary system that launched it may no longer resemble anything like its original configuration. An object from the thick disk carries the memory not of a single system, but of an era. Ultimately, the connection between 3I Atlas and the galactic disks is more than a question of origin. It is a revelation about interstellar objects as a population. It suggests that the Milky Way constantly loses material from its planetary systems. It suggests that the flow of interstellar debris is not dominated by rare catastrophic events, but by the steady accumulation of ejections from billions of systems over billions of years. Each of these systems, thin disk or thick disk, contributes to the galaxy's diffuse population of wanderers. 3I Atlas is one such wanderer. Its motion binds it to the dynamics of the disk. Its probable age ties it to the galaxy's long history. Its presence in our solar system demonstrates that we sit within a vast, interconnected structure where matter moves freely, where no system is truly isolated, where the boundaries between stars are permeable and alive with motion. To understand 3I Atlas is to understand our place in that structure. The galaxy is not a collection of separate worlds. It is a single, enormous ecosystem of drifting relics, of exchanged materials, of ancient objects on unending journeys. 3I Atlas is one more piece of that shared cosmic inheritance, passing through our sky for a moment, then returning to the disk from which it came. When astronomers speak of the Milky Way's thin disk, they refer to the great swirling plain of stars, gas, and dust that defines the galaxy's luminous structure. It is a vast, rotating arena where new stars ignite, where planets form within young protoplanetary disks, and where the majority of the galaxy's visible activity unfolds. The thin disk is vibrant, active, and full of motion. It is the part of the galaxies whose behavior shapes the lives of its stars, including the Sun. So when early analyses suggested that 3I Atlas might belong to the thin disk population, the implication was profound. It meant that this interstellar traveler could have been born in an environment not so different from our own. It meant the processes that created it might reflect the same cosmic rhythms that shaped Earth, Jupiter, and all the bodies that orbit our star. But to understand the significance of such a connection, one must first understand what it means for an object to be born in the thin disk. The thin disk is a place of relative youth, at least in galactic terms. Stars here are typically younger than 8 billion years. Many are much younger, mere hundreds of millions of years old. They arise from dense clouds of molecular gas that collapse into bright nurseries, where gravitational interactions and turbulence mold the systems that will eventually form planets. These stellar nurseries are rich in heavier elements, the building blocks of rocky planets, organic molecules, and complex structures. Within these nurseries, planet formation begins quickly. Dust grains collide and stick, forming pebbles, which grow into planetesimals, small bodies that may later become comets, asteroids, or even planets. The early years of any planetary system are chaotic. Giant planets migrate, collisions reshape worlds, gravitational interactions fling debris into eccentric orbits. It is a dynamic, violent era, and it is within these tumultuous beginnings that interstellar objects can be born. A system forming within the thin disk has all the necessary ingredients: gas, dust, turbulence, planets, migration, collisions, and gravitational instability. Every day, somewhere in the disk, small bodies are ejected from their home systems. These fragments, icy or rocky, escape their parent stars and embark on journeys through the galaxy. Over billions of years, the thin disk fills with these wanderers. 3I Atlas might have been one of them. If it came from the thin disk, its age could range from hundreds of millions to several billion years. It could have formed around a star not so different from the Sun, perhaps a yellow dwarf, or a red dwarf, or even a bright A-type star with a young, energetic system. The details are unknowable, but the broad strokes remain grounded. The thin disk is a fertile birthplace for interstellar debris. Yet, despite these similarities, there is a mystery at the heart of the thin disk connection. Why do interstellar objects from the thin disk appear so rare in our observations, despite the region's richness in planet-forming material? The answer lies not in their rarity, but in our blindness until recently. Before wide-field surveys like ATLAS and PAN-STARRS, most interstellar objects were invisible to us. They drifted through the solar system unnoticed, too faint to detect. Oumuamua and Borisov were not the first interstellar visitors, they were the first we were capable of seeing. With each improvement in detection capabilities, the number of known interstellar objects is expected to rise. This means objects like 3I Atlas are likely common representatives of a much larger population produced by the thin disk's planetary systems. The thin disk's turbulence also offers clues. It is not static. Over time, stars drift outward from their birthplaces. Spiral arms rotate at different speeds. Clusters form and dissolve. Stellar winds, supernovae, and gas flows reshape local environments. In this dynamic setting, young systems frequently influence each other. Passing stars can perturb outer belts. Newly formed planets can destabilize debris fields. The thin disk is a region where ejections are frequent and inevitable. If 3I Atlas formed in such an environment, the circumstances of its ejection may have been typical. Perhaps a gas giant migrated inward, scattering small icy bodies outward. Perhaps a binary star companion destabilized the system. Or perhaps the object simply occupied an outer orbit too tenuous to remain bound during the star's adolescence. Ejection is a natural byproduct of planetary system evolution. A system forming within the thin disk has all the necessary ingredients: gas, dust, turbulence, planets, migration, collisions, and gravitational instability. Every day, somewhere in the disk, small bodies are ejected from their home systems. These fragments, icy or rocky, escape their parent stars and embark on journeys through the galaxy. Over billions of years, the thin disk fills with these wanderers. 3I Atlas might have been one of them. If it came from the thin disk, its age could range from hundreds of millions to several billion years. It could have formed around a star not so different from the Sun, perhaps a yellow dwarf, or a red dwarf, or even a bright A-type star with a young, energetic system. The details are unknowable, but the broad strokes remain grounded. The thin disk is a fertile birthplace for interstellar debris. Yet, despite these similarities, there is a mystery at the heart of the thin disk connection. Why do interstellar objects from the thin disk appear so rare in our observations, despite the region's richness in planet-forming material? The answer lies not in their rarity, but in our blindness until recently. Before wide-field surveys like ATLAS and PAN-STARRS, most interstellar objects were invisible to us. They drifted through the solar system unnoticed, too faint to detect. Oumuamua and Borisov were not the first interstellar visitors, they were the first we were capable of seeing. With each improvement in detection capabilities, the number of known interstellar objects is expected to rise. This means objects like 3I Atlas are likely common representatives of a much larger population produced by the thin disk's planetary systems. The thin disk's turbulence also offers clues. It is not static. Over time, stars drift outward from their birthplaces. Spiral arms rotate at different speeds. Clusters form and dissolve. Stellar winds, supernovae, and gas flows reshape local environments. In this dynamic setting, young systems frequently influence each other. Passing stars can perturb outer belts. Newly formed planets can destabilize debris fields. The thin disk is a region where ejections are frequent and inevitable. If 3I Atlas formed in such an environment, the circumstances of its ejection may have been typical. Perhaps a gas giant migrated inward, scattering small icy bodies outward. Perhaps a binary star companion destabilized the system. Or perhaps the object simply occupied an outer orbit too tenuous to remain bound during the star's adolescence. Ejection is a natural byproduct of planetary system evolution. But the thin disk mystery deepens when considering the object's activity. 3I Atlas displayed signs of being a comet, faint outgassing, a subtle glow, small dust release. This suggests it retained volatile ices capable of sublimating under sunlight. Yet thin disk environments, rich in stellar radiation, can be harsh on small icy bodies. Only those ejected early, before prolonged heating, would retain pristine ices over billions of years. This leads to one possible interpretation. 3I Atlas may have been expelled from its system shortly after formation, when its ices were young and unaltered. In this scenario, the object would have spent nearly its entire existence in interstellar space, preserved by the cold. Its journey through the galaxy would have slowly processed its outer layers through cosmic ray bombardment, forming a crust over its surface. Only when it entered the solar system did the sun's warmth begin to awaken the buried ices. This matches the behavior astronomers observed: subdued activity, faint signs of gas, dust released in small, delicate amounts. 3I Atlas behaved like a comet that had been asleep for an incredibly long time. Another layer of the thin disk mystery lies in chemical composition. Although the data is scarce, nothing in the spectral hints suggests exotic chemistry. The object may be chemically similar to solar system comets. This suggests a shared blueprint between planetary systems. The laws of chemistry do not vary from star to star. The early solar nebula's ingredients are mirrored across the galaxy. If this is true, interstellar comets may be chemically familiar even if dynamically foreign. This raises an intriguing possibility. The thin disk may be producing a vast number of comets that resemble our own in composition, structure, and behavior. And 3I Atlas may be the first representative of this standard interstellar comet, one that looks nearly ordinary to our instruments despite its extraordinary origin. Yet in its very ordinariness lies the mystery. If interstellar objects resemble solar system objects in composition and behavior, how many have passed unnoticed? How many future detections will reveal gentle, faint, subtle comets that drift through the solar system without drawing attention? And how many have already come and gone, never seen? The thin disk may be full of such quiet wanderers. 3I Atlas may simply have been one fortunate enough to be seen. But understanding its origin requires exploring another possibility, one that reaches deeper into the galaxy's history. Not all signs pointed to youth. Some hinted at something much older, and so we turn to the thick disk. The thick disk of the Milky Way is a vast, ancient structure, older, quieter, and more mysterious than the bustling thin disk closer to the galactic midplane. Stars in the thick disk are relics of the galaxy's early eras, formed before the spiral arms fully sculpted their iconic shapes. These stars orbit the galaxy with distinct velocities, spread through a region that extends far above and below the thin disk. They are older, less metal-rich, and often solitary witnesses to epochs long past. When simulations of 3I Atlas's orbit hinted that it might belong to the thick disk population, a profound possibility emerged. The object might be older than our entire solar system. This revelation, even as a possibility, changes the way we perceive the object. If 3I Atlas originated in the thick disk, then it could have formed in a young planetary system billions of years before the Sun existed. It may have circled a now ancient star that has evolved beyond recognition. It may have been shaped by an environment very different from the one that gave rise to the Earth. Its materials may reflect the chemistry of the early galaxy, untouched by the metallic richness of later stellar generations. To understand what this means, we must step back and look at the thick disk's origins. The thick disk likely formed during a turbulent phase in the galaxy's early life. Some theories suggest it was born from violent mergers between proto-galaxies, where gravitational interactions heated orbits and stirred stars into a vertically extended structure. Other theories propose that intense star formation early in the galaxy's development produced strong feedback, winds, radiation, supernovae that puffed the disk upward. Whatever the mechanism, the thick disk became the repository of some of the Milky Way's oldest stars. Chemical signatures reveal the age of thick disk stars. They contain fewer elements heavier than hydrogen and helium, elements that astronomers refer to as metals. In cosmic terms, metals are produced in the hearts of stars and dispersed through supernovae. Stars born later inherit higher metallicities. Stars in the thick disk formed before many of these enrichment cycles occurred. Their planets, if they formed any, would also have lower metallicity. A body born in such a system, like 3I Atlas, if it indeed came from the thick disk, would carry that chemical fingerprint. Its ices, dust grains, and volatiles would reflect the early galaxy's composition. Imagine a small icy planetesimal forming around one of these ancient stars. The protoplanetary disk would have been colder, more dust-rich in certain species, and less endowed with complex organics. The body might have contained high ratios of primordial ice, simple hydrocarbons, and grains forged in ancient supernova remnants. Such a body, once ejected, would become an interstellar wanderer long before the Sun ignited. It would drift through the early galaxy as stellar clusters formed and dissolved, as spiral arms took shape, as gas clouds collapsed into new stars and were later recycled through massive supernovae. For billions of years, the object would be bombarded by cosmic rays. These high-energy particles would gradually alter its surface chemistry, darkening it, forming refractory organic crusts and locking deeper ices beneath layers of radiation-processed material. Only a strong warming event, such as passage close to a star, would awaken its buried volatiles. This is exactly the behavior astronomers observed: subdued activity, faint volatiles, minimal outgassing, and a surface that seemed hardened by extreme age. The thick disk revelation does not rest solely on motion. The orbital analysis revealed a trajectory whose velocity aligned with both thin and thick disk populations, but slightly favored the latter. The object's inbound direction also pointed toward regions where thick disk stars dominate. While these clues are not definitive, they are compelling. If 3I Atlas did come from the thick disk, then its journey likely began with gravitational chaos surrounding an early planetary system. In such systems, giant planets may have migrated violently or never formed at all, depending on metallicity. Protoplanetary disks might have been more diffuse, leading to slower coagulation of planetesimals. Whatever the system's nature, at some point the small icy fragment we now call 3I Atlas was scattered into interstellar space, and then it drifted. Not for millions of years like thin disk wanderers, but for billions. Billions! It passed by stars that are now long dead. It drifted through regions of the galaxy that have since moved elsewhere. It witnessed epochs where dense gas clouds formed the first generations of newer stars. It crossed galactic structures that have shifted since its release. It was an ancient traveler, one that would have existed even before the Earth's crust solidified. Such age does something profound to an object. Cosmic rays penetrate deeper, volatiles rearrange, refractory organics accumulate, surface layers compact and fracture. And yet, even after billions of years, something remarkable remains. The object's interior still contains original ices. This is what allowed 3I Atlas to display comet-like activity as it approached the Sun. Beneath its ancient crust lay frozen materials that had not interacted with starlight in eons. When the Sun's heat finally reached them, the gases began to sublimate. Dust grains lifted off the surface. A faint coma formed, a ghostly reminder that even the oldest wanderers can still reveal their secrets. The thick disk revelation suggests that interstellar objects are not uniform. Some are young and energetic. Some are middle-aged, shaped by millions of years of drift. And some, like 3I Atlas may be, are ancient beyond comprehension. Seeing such an object in our sky is like witnessing a piece of the early galaxy drift past us, an object forged in a time so distant that our own sun was unimaginable. Its arrival in our era is an astronomical gift. The thick disk holds many stories. 3I Atlas may be one of its oldest. To understand an interstellar object like 3I Atlas, one must go beyond orbital mechanics and spectral hints. One must step into the realm of deep time, epochs so distant that the imagination strains to hold them. Because interstellar objects are not just wanderers, they are fragments, relics, pieces of worlds that once were whole. Every interstellar comet, every hyperbolic shard, every drifting body expelled from a stellar system carries the memory of ancient worlds that may no longer exist. They are survivors of systems altered beyond recognition or lost entirely to the passage of cosmic time. And 3I Atlas, with its subdued activity, hardened crust, and mysterious velocity, may well be one of these fragments. A piece of an ancient world shattered long before Earth formed its first oceans. To understand how such a fragment comes to be, one must reconstruct the forces that shape planetary systems. In their infancy, these systems are turbulent. Millions of planetesimals, icy, rocky, metallic, collide, merge, and fracture. Giant planets migrate inward and outward, driven by interactions with surrounding gas. Star clusters compress and disperse. Young stars pass close to one another, tugging at the outer regions of each other's disks. The early life of a solar system is a story of restless improvisation rather than graceful choreography. Imagine a young planetary system, perhaps in the thin disk, perhaps in the thick disk. Around a newborn star, a disk of gas and dust spins, gradually assembling into larger structures. Tiny grains collide and stick. Over time, these grains grow into pebbles, then boulders, then planetesimals. Most of these planetesimals will eventually be altered, captured into planets, pulverized by collisions, or driven into their star. But some escape. Consider a small icy body forming in the outer reaches of that protoplanetary disk, far colder, far darker, far quieter than the region where terrestrial planets arise. It circles its star on a distant orbit, stable enough to survive the early chaos. Then something changes. A giant planet migrates inward, destabilizing the system. Or perhaps two planets undergo a resonance encounter that reshapes orbits globally. Or a passing star brushes the outskirts of the system, perturbing the bodies that dwell there. The small icy planetesimal is nudged slightly, then nudged again. Over countless orbits, the perturbation grows. One day, it crosses too close to a giant planet. That single encounter changes everything. The planet's gravity accelerates the fragment, flinging it outward at tremendous speed. It climbs higher, higher, beyond the system's outer edges. Eventually, the star's gravity weakens to the point where it can no longer hold the body in place. The icy fragment crosses the invisible threshold, escaping the star that once nurtured it. Now it belongs to the galaxy. Over time, entire populations of such fragments accumulate. Every planetary system ejects some fraction of its primordial bodies. Some estimates suggest that for every star in the galaxy, there may be trillions of such ejected objects, small, forgotten pieces of planetary construction. These fragments drift in the interstellar medium, cold and inert, carrying within them the materials from their long-lost systems. But some interstellar objects may have even more dramatic origins. Picture a young planetary system locked in conflict. Two protoplanets collide, massive bodies smashing into each other with such force that entire crusts vaporize. Molten material is thrown into space, and debris showers the system. In our own solar system, such a collision likely formed the Moon. But in some systems, the debris field does not remain bound. Some pieces may be cast outward with enough velocity to escape entirely. Or picture a system orbiting a star that evolves rapidly. A massive star ends its life in a supernova, sending shock waves through its planets. The blast can fracture or strip surfaces. Smaller bodies can be hurled outward, transformed by violence into fragments that drift away from their shattered home. Or imagine a binary star system where one star grows unstable. As the stars interact, gravitational forces twist and distort orbits, tearing apart fragile worlds or ejecting them altogether. Some fragments fall inward, others are cast outward like sparks from a fire. Each of these scenarios produces debris that can leave the system and enter the galaxy as interstellar wanderers. 3I Atlas may have been one such piece of ancient violence. Spectral hints suggest it is cometary, but not explosively active. Its behavior suggests an object that has not experienced strong heating in eons. This could mean it was ejected early in its system's history, preserved in deep cold before drifting outward. But it could also hint at a shattering event, a collision or gravitational disruption that sent it hurtling away before its surface fully matured. In the thick disk scenario, if 3I Atlas is indeed from that ancient population, the story becomes even more dramatic. Thick disk systems formed when the galaxy was young and chaotic. Mergers between early protogalaxies stirred stars into highly inclined orbits. Supernova rates were higher. Gas clouds were denser in some regions and barren in others. In such an environment, planetary systems may have formed rapidly, evolved violently, and destroyed themselves spectacularly. Fragments from those early worlds would be scattered into interstellar space long before Earth formed. After billions of years, those fragments would be darkened by cosmic rays, scarred by tiny impacts, and coated in radiation-hardened organics. But beneath the darkened crust, their original ices might survive intact, protected by layers of material transformed over the ages. This is exactly what 3I Atlas appears to be, a body with ancient, hardened surfaces and buried volatiles. If the object was indeed formed by a shattering event, whether from a collision, gravitational disruption, or stellar evolution, its entire existence is a testament to survival. The galaxy's turbulence should have destroyed it many times over, yet here it is, passing through our solar system like a messenger from a forgotten age. The idea that 3I Atlas is a fragment of an ancient world raises poetic questions. What world did it come from? Was that world icy or rocky? Was it peaceful or chaotic? Did it orbit a single star or a binary? Did it have sibling fragments that also wander somewhere in the Milky Way? Did any planets in its system form oceans? Did any harbor life? These questions are unanswerable, but the fragment itself is a physical reminder that across the galaxy, worlds are born and destroyed, and their pieces continue wandering. Interstellar objects like 3I Atlas are cosmic fossils. They are the debris of planetary systems that no longer exist, or that have changed so drastically they cannot be recognized. They are fragments of worlds shattered by forces beyond imagination. And now, after a journey that may span billions of years, one such fragment has drifted into our sky. To study 3I Atlas is to study the remnants of ancient worlds, and in doing so, we study the galaxy's own memory. To understand why interstellar objects exist at all, to understand the origin of 3I Atlas at its deepest level, one must return to the beginning of all planetary systems, the birth of stars. For it is in these early, chaotic, luminous beginnings that the seeds of interstellar wanderers are planted. Stars do not form quietly. They emerge from darkness with violence, pressure, collapse, turbulence, chaos, and the irresistible pull of gravity. And from this cosmic upheaval come the worlds, the comets, the asteroids, and the countless fragments that drift into the interstellar medium. The formation of a star begins in the coldest regions of space, dense molecular clouds where hydrogen gas gathers in clusters dense enough to collapse under their own weight. These clouds are enormous, spanning dozens or hundreds of light years, and often contain enough mass to form thousands of stars. Yet they are held aloft by turbulence, magnetic fields, and the delicate balance of external pressures. Some event disturbs the balance. A supernova shock wave ripples through, compressing the gas. Or two massive clouds collide. Or gravity simply wins the long war of inward pull. Whatever the catalyst, gravity takes hold and the cloud begins to collapse. Within the collapsing region, small clumps become denser. These clumps, called dense cores, are the cradles of future stars. As they collapse, they spin, flattening into disks due to conservation of angular momentum. At the center, matter piles up, heating until nuclear fusion ignites. A star is born. But this is only the beginning. Around the newborn star, the disk remains, a circling structure of gas and dust known as a protoplanetary disk. This disk is a factory, one that will build planets, comets, asteroids, and every small body that may eventually become interstellar debris. Dust grains within the disk begin to collide. Electrostatic forces cause them to stick. They form clusters, which grow larger, eventually becoming pebbles, then boulders, then planetesimals. Over time, these small bodies attract more material, eventually becoming the building blocks of planets. But not all planetesimals will become planets. In fact, most will not. The disk is a crowded, chaotic place. Collisions are frequent. Many bodies fragment instead of merging. Some spiral inward toward the star and are consumed. Others remain on stable orbits, becoming the small bodies that populate asteroid belts or comet reservoirs. But among these countless bodies, some will be flung outward, escaping the system entirely. This happens through multiple mechanisms. In young systems, giant planets often migrate. A gas giant moving inward or outward disrupts the orbits of smaller bodies, sending them into chaotic paths. Some collide with other bodies. Some are captured into resonances. Some are thrown inward toward the star, and some are cast outward with enough velocity to escape the system's gravitational grasp. These ejected bodies become interstellar travelers. In binary star systems, a configuration far more common than solitary stars, gravitational interactions are even more complex. Each pass near the companion star can twist and tilt orbits. Bodies in unstable regions can be ejected entirely. Observations suggest that binary systems may produce far more interstellar debris than single-star systems, simply because their gravitational dynamics are so turbulent. Other mechanisms arise later in a star's life cycle. When a star evolves and becomes a red giant, its outer envelope expands dramatically, destabilizing nearby orbits. Asteroids and comets can be nudged into new trajectories. Some fall inward, some drift outward, some escape entirely. If the star later undergoes a violent transition, such as shedding its outer layers, entire populations of small bodies can be ejected. This process may explain some of the most ancient interstellar objects in the galaxy. A planetesimal born around a star in the thick disk could have been thrown outward during its star's later evolution, perhaps as the star moved into the giant phase billions of years ago. Within all of these scenarios lies a profound truth. Interstellar objects are not rare accidents. They are inevitable outcomes of planetary formation and evolution. For every planetary system that forms, countless small bodies are scattered. Some remain bound, forming comet clouds. Some collide with forming planets, but many escape into the galaxy, becoming wanderers. So what does this mean for 3I Atlas? It means the object's presence in our solar system is the direct result of the same processes that shaped our own world. The Sun, too, would have ejected material early in its life. Giant planets like Jupiter would have scattered icy bodies outward, some of which became the Oort cloud and others which escaped the system entirely. Every star with planets contributes to this galactic reservoir. 3I Atlas is a product of that universal process. Its existence proves that the Milky Way is not a collection of isolated solar systems, but an ecosystem where fragments continually flow from star to star. These fragments carry within them the frozen chemistry of long-lost worlds. They are, in a very real sense, the residue of creation. And 3I Atlas, drifting quietly through space for millions or billions of years, is one such residue. Born in the luminous chaos of star formation, shaped by the violent harmony of planetary dynamics, and preserved in the silence of interstellar night. Every interstellar object, no matter how ancient or humble, shares a single defining moment in its history, the instant it becomes unbound from its parent star. That moment is never gentle, it is never quiet. It is an act of astronomical violence, a gravitational shove, a cosmic accident, or a catastrophic rearrangement. To be ejected from a stellar system is to be thrust into the galaxy with no path home, a wanderer doomed to drift between suns. 3I Atlas is one such exile. To understand it, we must imagine the circumstances that could have flung it into the void. In the early life of a planetary system, gravitational forces behave like a crowded marketplace. Bodies pass close to one another, exchanging momentum in chaotic ways. The most common scenario for ejection involves a giant planet, a massive world whose gravity is powerful enough to reshape the fates of everything around it. In our own solar system, Jupiter serves this role. It has ejected countless comets from the early solar system, sending them into outer darkness. Some became members of the Oort cloud, others escaped entirely. Imagine a system not unlike ours. A young star burns brightly at its center, surrounded by swirling dust. Nearby, a giant planet, a world the size of Jupiter or larger, moves through its orbit, sculpting the disk around it. In the distant reaches of this system, small icy bodies circle on elongated orbits. One such body is destined to become 3I Atlas. A single close pass changes everything. As the icy body drifts inward, perhaps drawn off its course by interactions with neighboring planetesimals, it enters the gravitational sphere of the giant planet. The planet's immense gravitational pull accelerates the small body, hurling it onto a new trajectory. The encounter is delicate yet brutal. A slight difference in angle or distance would change the outcome entirely. But in this scenario, the small body gains speed, too much speed. It is flung outward like a stone from a sling. The star's pull weakens as the body climbs higher and higher. Eventually, it crosses the escape boundary, the gravitational frontier where the star's influence collapses. Beyond this point, the body belongs to no star. It is free. This moment is the birth of an interstellar object. But other scenarios are equally compelling. In binary star systems, the gravitational interactions between two suns are complex. A small planetesimal orbiting one star may occasionally pass near the second. If its path brings it too close, the combined gravitational forces can hurl it outward with immense speed. Many binary systems are thought to eject far more debris than single-star systems for this very reason. If 3I Atlas formed in a binary system, its ejection may have been the result of repeated close encounters, each one adding a little energy until one final tug pushed it beyond escape. Another possibility involves the early evolution of its parent star. If the star grew larger, becoming a red giant, the outer layers of its atmosphere would expand dramatically. This expansion could destabilize nearby orbits. Some bodies are drawn inward, consumed by the star. Others are flung outward, accelerated by the sudden mass loss events that accompany stellar evolution. In extreme cases, entire belts of comets can be expelled as the star sheds its outer layers. This scenario could explain particularly ancient interstellar objects. A star that has since evolved into a white dwarf, its planetary system shattered or rearranged, might have expelled objects billions of years ago. If 3I Atlas originated in the thick disk, this could be its story. A survivor of a system whose star has long since faded. There is another, more violent possibility: collisions. In the early life of a planetary system, collisions between planetesimals are common. Some collisions are gentle, merging bodies together. For 3I Atlas, the faint asymmetry visible in some composite observations hinted at complex surface topography, regions where cracks allowed gas to escape more readily, or regions shielded by the object's shape. Another insight concerns composition. Dust grains scattered into the tail carry information about the object's interior. Larger grains suggest a stronger crust or deeper origin. Smaller grains suggest surface-level erosion. The most detailed analysis possible from 3I Atlas indicated a mix of fine and moderately sized particles, consistent with an irradiated surface that fractures into small pieces. The interaction of the tail with the solar wind also matters. When the solar wind collides with gas molecules, it ionizes them, creating charged particles that form the ion tail. The shape and length of this tail can reveal the object's gas production rate and the strength of its sublimation. Because 3I Atlas produced only faint gas, the expected ion tail was thin, short, and perhaps too faint to see directly. Still, its existence is nearly certain because physics requires it. Any gas in the presence of the solar wind must produce ions. The tail also tells a story about the object's age. Objects that have been in interstellar space for extremely long periods develop a crust so thick that the deepest ices rarely sublimate. Such objects produce extremely faint tails. This places 3I Atlas in a category distinct from solar system comets that have spent far less time exposed to high-energy radiation. In a sense, the faintness of the tail is not a sign of weakness, it is a sign of endurance. Another layer of complexity comes from the object's shape. The shape of a comet affects how gas escapes, how dust is lifted, and how the tail forms. While 3I Atlas was far too distant and faint for direct shape measurement, the behavior of its comma and tail allowed astronomers to infer that it might not be perfectly spherical. Instead, it likely had an irregular shape, perhaps elongated, perhaps lumpy, perhaps sculpted by ancient collisions or radiation erosion. Irregular shapes produce asymmetric tails, especially when rotation causes different areas of the surface to heat unevenly. The faint but measurable differences in the brightness of 3I Atlas over time hinted at rotational modulation, light changing as different faces of the object turn toward Earth. These modulations, combined with tail orientation, suggest that gas release occurred in patches rather than uniformly. The tail also reveals the object's velocity relative to the Sun. Because ion tails always point directly away from the Sun, any deviation indicates interaction with magnetic fields or non-radial solar wind flows. Dust tails, by contrast, curve with the object's motion. Comparing the two can reveal the object's direction of travel. For 3I Atlas, this analysis confirmed its hyperbolic trajectory, another signature of its interstellar origin. A tail is a comet's testimony. It is the visible expression of its chemistry, its structure, its history, and its interaction with the star it approaches. For 3I Atlas, the tail may have been faint, but its message was profound. It told astronomers that the object still contained ancient ices. It told them that the object carried dust particles formed in a star system that may no longer exist. It told them that the object was active, but only subtly, a traveler hardened by time. It told them that light had reached its surface after ages of darkness, awakening processes that had been dormant longer than human civilization. Even a faint tail tells a story. 3I Atlas whispered its story across millions of kilometers of space, and for a brief moment, humans were listening. When astronomers first detect a faint, fast-moving object in the outer solar system, one of the earliest questions they ask is deceptively simple. Is it a comet or is it an asteroid? For centuries, these two categories seemed distinct. Comets grew coma and tails when warmed by the sun. Asteroids remained inert, rocky, silent. Comets were icy, fragile, ancient messengers from the solar system's cold outskirts. Asteroids were rocky remnants of the inner regions. The distinction felt clear. But the cosmos has little regard for our categories. Over the past few decades, astronomers have discovered that the line separating comets from asteroids is not a line at all. It is a gradient, a continuum shaped by age, environment, and history. Many objects blur the boundary. Some asteroids show comet-like activity. Some comets fade until they resemble asteroids. Some bodies alternate behaviors depending on their thermal cycles. And then there are the interstellar objects, wanderers that do not fit neatly into either category. 3I Atlas is one such boundary breaker. When first observed, its faintness suggested a small, inert asteroid. Its brightness did not immediately reveal activity. Its surface appeared dark and light-absorbing, similar to many asteroids in the solar system that have been weathered by time. But as more observations accumulated, a different picture emerged. The brightness changed subtly over time. The object appeared slightly more diffuse than a rock of its size should, and the shape of its light curve hinted at the presence of a faint coma. These contradictions forced astronomers to question its identity. Was 3I Atlas a comet, an asteroid, something in between? The answer lies in the physics of sublimation and the chemistry of an irradiated crust. A typical comet from the solar system contains icy material near the surface. When it approaches the sun, these ices warm and sublimate, producing gas and dust. The presence of a coma is one of the clearest indicators of a cometary nature. Asteroids, especially those from the inner regions of the solar system, lack substantial ices. Even if they contain trace volatiles, their surfaces often do not release them in detectable quantities. They remain dormant. But interstellar objects begin with a different history. They are formed in distant systems, possibly under conditions not identical to those of our own. They may contain volatile ices that are not typical of local asteroids, or they may contain organics hardened by cosmic rays. More importantly, interstellar objects undergo extreme surface processing during their long flight through the galaxy. 3I Atlas is one such boundary breaker. When first observed, its faintness suggested a small, inert asteroid. Its brightness did not immediately reveal activity. Its surface appeared dark and light-absorbing, similar to many asteroids in the solar system that have been weathered by time. But as more observations accumulated, a different picture emerged. The brightness changed subtly over time. The object appeared slightly more diffuse than a rock of its size should, and the shape of its light curve hinted at the presence of a faint coma. These contradictions forced astronomers to question its identity. Was 3I Atlas a comet, an asteroid, something in between? The answer lies in the physics of sublimation and the chemistry of an irradiated crust. A typical comet from the solar system contains icy material near the surface. When it approaches the Sun, these ices warm and sublimate, producing gas and dust. The presence of a coma is one of the clearest indicators of a cometary nature. Asteroids, especially those from the inner regions of the solar system, lack substantial ices. Even if they contain trace volatiles, their surfaces often do not release them in detectable quantities. They remain dormant. But interstellar objects begin with a different history. They are formed in distant systems, possibly under conditions not identical to those of our own. They may contain volatile ices that are not typical of local asteroids. Or they may contain organics hardened by cosmic rays. More importantly, interstellar objects undergo extreme surface processing during their long flight through the galaxy. But others are catastrophic, shattering worlds into fragments. A collision between two large icy bodies could send shards flying in all directions. Some fragments might spiral inward, others outward. A few might be launched onto escape trajectories. If 3I Atlas is such a fragment, then it carries the physical memory of that collision. The chemical scars, the altered surface texture, the shapes sculpted by ancient violence. In each scenario, the result is the same. A small object, once part of a family of worlds, becomes a solitary traveler. And once unbound, its life changes forever. Interstellar space is unimaginably empty. A typical interstellar object may drift for millions of years before passing near another star. The distances between systems are vast. During its journey, the object's surface is bombarded by cosmic rays, high-energy particles that chip away at molecules, create new chemical compounds, and darken the surface. Over time, a radiation-hardened shell develops, sealing deeper layers beneath it. Inside, the object remains as it was when it formed. This is the paradox of interstellar objects. Surface layers reveal the passage of time, while interior layers preserve the earliest history. 3I Atlas experienced this dual existence. Its surface, darkened by cosmic rays, speaks of deep time. But its faint activity when warmed by the sun hints at fresher ice beneath. Somewhere inside it lies the original material of its home system. Material older than Earth, older than the solar system, perhaps older than most stars in the Milky Way. The journey of an ejected object is not a straight line. It curves gently through the galactic potential. It is pushed and pulled by distant stars. It is nudged by molecular clouds. It is influenced by the spiral arms, which create density waves that subtly alter the motion of everything within them. Yet these influences are faint, and the object's velocity remains largely unchanged over long timescales. This is why the orbit of 3I Atlas revealed so much. Its velocity hinted at how long it had drifted. Its direction hinted at where it might have come from. Its hyperbolic path through the solar system revealed that it had never belonged to our star. It was ejected into the void long ago. And after millions or perhaps billions of years of wandering through cold interstellar darkness, it finally encountered the sun. Its long exile is what makes its brief appearance so precious, because once it leaves the solar system, it will never return. It will drift onward, unchanged in its silence, until it passes near some other star in the distant future, or perhaps none at all. Its destiny is eternal travel. Its origin is forever lost. But for a moment, it crossed paths with our world, offering a glimpse into the galaxy's vast and ancient past. Once an object becomes unbound from its star, it enters a realm unlike any other. Interstellar space is not simply empty. It is a vast, complex environment shaped by forces far larger and older than any planetary system. It is a place of silence, of loneliness, of endless drift. And it is in this environment that objects like 3I Atlas spend the vast majority of their existence. To imagine 3I Atlas's journey through interstellar space is to imagine a kind of cosmic stillness, punctuated by moments of subtle yet profound interaction. The object drifts at tens of kilometers per second, swift by planetary standards, but glacially slow compared to the immense scale of the galaxy. At this speed, it would take tens of thousands of years just to pass from one end of a stellar neighborhood to another. And yet it moves with purpose, carried by the gravitational currents of the Milky Way. Interstellar space is not uniform. It contains pockets of gas, clouds of dust, and regions shaped by the winds of massive stars. But compared to the density of material in a planetary system, it is astonishingly empty. Between stars, the average density of particles is far less than the best vacuums created on Earth. For 3I Atlas, this emptiness means freedom. There are no significant collisions, no atmospheric drag, nothing to slow it down or alter its course except gravity. Gravity, however, is everywhere. As 3I Atlas moved through the galaxy, the gravity of stars subtly shaped its path. Most stars exert a negligible influence, too far, too faint, too distant in space-time. But occasionally, over millions of years, the object would pass near a star or binary system. Even a distant encounter could alter its trajectory slightly. These gravitational nudges accumulate over the ages, guiding the object on a slow, winding path that bears the collective signature of countless stellar interactions. But to the object itself, these events are like whispers, tiny course corrections almost imperceptible on human timescales. Over time, such interactions blur the history of the object's origin. This is why tracing 3I Atlas backward through time is nearly impossible. The galaxy structure evolves, stars drift, clusters dissolve, the gravitational landscape changes. The farther we look into the past, the more uncertain everything becomes. Yet despite this uncertainty, one thing is clear. Interstellar space is not a dead zone. It is a realm of continual influence, a place where small bodies like 3I Atlas carry the collective imprint of the galaxy's evolution. During its journey, the object was bombarded by cosmic rays, high-energy particles accelerated by supernovae, neutron stars, and black holes. These particles struck its surface relentlessly. Each impact broke molecular bonds, created new compounds, and slowly darkened the crust. Over time, the surface chemistry changed, forming a thick, radiation-processed layer. This layer acts like a time capsule. It records how long the object has been drifting through interstellar space. The depth of radiation penetration tells astronomers about the object's age. The chemical structure of the crust reveals the harshness of the environment it survived. But beneath that crust lies the untouched interior, ancient ice, primordial dust, and materials unaltered since the object first formed. This dual nature, aged on the outside, pristine on the inside, makes interstellar objects scientifically invaluable. They carry original material from planetary systems that may no longer exist. Their interiors preserve conditions from eras far older than the solar system. If 3I Atlas came from the thick disk, its interior might preserve the chemistry of a system formed when the galaxy was still young. If it came from the thin disk, it might reveal how icy bodies form around stars similar to our Sun. As 3I Atlas drifted through the galaxy, it encountered not just stars, but the massive structure of the Milky Way itself. The galaxy's spiral arms influence the motion of stars and debris. These arms are not solid objects, they are density waves, regions of higher gas concentration that move through the disk. When the object passed through such a region, it may have experienced tiny gravitational influences, or been bombarded by higher concentrations of cosmic rays. Over millions of years, it may have crossed several spiral arms, each crossing a silent milestone in its journey. The path of 3I Atlas was also shaped by the galaxy's dark matter halo. Although dark matter does not interact with normal matter except through gravity, its mass shapes the galactic potential. The object's long-term trajectory curved gently through this invisible structure, subtly guided by forces humanity cannot directly see but can infer. Drifting through interstellar space for millions or billions of years might seem uneventful, yet it represents one of the most remarkable voyages imaginable. The object traveled through environments no spacecraft has visited. It passed by stars unknown to us. It drifted through regions of the galaxy that have long since changed. It witnessed epochs beyond human memory. And then, by chance alone, it approached our solar system. Not because it sought us, not because we are special, but because the galaxy is vast and wanderers must drift somewhere. When it approached the sun, the warmth began to penetrate its crust. The long dormant ices stirred. Gas escaped in thin, steady streams. A faint coma formed, its first activity in untold ages. The object brightened, not with the flamboyance of a young comet, but with the soft glow of something ancient awakening. This awakening marks the end of its interstellar sleep. After millions of years flying through interstellar space, 3I Atlas briefly revealed its secrets. Then it continued on, unbound, unchanged, destined for another eternity of silent drift. Once an object escapes its home star, once it drifts far beyond the last wisps of its native heliosphere, it enters the long twilight of interstellar space. It is a realm of deep cold and endless night, a place where time stretches into unimaginable scales, where movement is glacial compared to the cosmic distances involved, and where even the most dramatic events unfold with a slowness that borders on stillness. For an interstellar traveler like 3I Atlas, this long sleep between stars is not merely a phase in its journey, it is the defining chapter of its existence. In this region, sunlight is nothing more than an idea. Even the brightest stars are reduced to pinpricks. Heat no longer plays a role. Energy becomes a memory. The radiation of the cosmic microwave background, faint, ancient, and uniform, wraps the object in a temperature barely above absolute zero. Here, 3I Atlas slept, for millions of years, possibly billions. This sleep is not a conscious one, of course. It is a stillness imposed by physics. Every molecule on its surface, locked into crystalline frost, remains frozen in place. Every grain of dust clings to the surface with the grip of absolute silence. The object's rotation slows, then stabilizes into a rhythm born from the last gravitational nudges it experienced before ejection. Its motion becomes steady, almost meditative, a steady glide through the thin matter of interstellar space. But sleep does not mean life without influence. Even here, in the cold between stars, subtle forces sculpt the traveler. Cosmic rays, high-energy particles accelerated by supernova, neutron stars, and other distant astrophysical engines strike its surface relentlessly. These particles penetrate the crust, shattering molecules, rearranging chemical structures, generating new compounds that cannot form under gentler conditions. Over millions of years, these impacts create a hardened layer, a dark, organic-rich crust often called an irradiation mantle. The thickness of this mantle can reveal the age of the object's interstellar journey. Laboratory experiments show that cosmic rays penetrate surface layers slowly but steadily, forming complex hydrocarbons and refractory materials. For 3I Atlas, the subdued activity observed in the solar system suggested a surface heavily processed by cosmic rays, an indication that its long sleep was indeed long on a scale far exceeding human history. Micrometeorite impacts also play a role. Though exceedingly rare between stars, the occasional dust grain traveling at tremendous speed can strike the object, chipping away tiny fragments, annealing its surface, or altering its rotation slightly. Over millions of years, these impacts accumulate into faint scars, surface textures invisible to telescopes but embedded in the object nonetheless. There is something almost sacred about this long sleep. It is the most stable phase in the object's existence. Within a planetary system, bodies are shaped by heat, collisions, tides, and migration. Near stars, they change. But in interstellar space, they endure. They persist in their original forms, altered only delicately by the gentle erosion of cosmic time. For an object like 3I Atlas, this means that while its surface bears the imprint of an ancient journey, its interior remains pristine. Locked beneath the irradiation mantle lies the chemistry of its birthplace, frozen volatiles formed in a disk around a star that may no longer shine. If the object came from the thick disk, those volatiles would carry the elemental ratios of the early galaxy. If from the thin disk, they might resemble the ices of solar system comets. In either case, the interstellar phase preserves these materials better than any planetary system could. This preservation is part of what makes interstellar objects so scientifically valuable. They are time capsules, sealed by the cold, unchanging conditions of the interstellar medium. Inside them lies information about the early conditions of planetary systems, information that cannot be found anywhere else. But what happens during this long sleep is not purely physical. There is a narrative quality to it, a story told through silence. The object drifts through the galaxy as stars form, as clusters dissolve, as spiral arms rotate, as supernova send shockwaves through the medium. It witnesses nothing, yet it survives everything. It crosses regions of varying density, drifting into molecular clouds, exiting them, passing near ancient stars whose own planetary systems may once have resembled the one from which it was ejected. One can imagine the slow procession of millennia, the object drifting past the gravitational reach of one star after another, never captured, always nudged but never held. The galaxy rotates, bringing regions of different composition and radiation environments into alignment with the object's trajectory. Tidal forces reshape clusters. Gas flows into new star-forming regions. But through it all, the interstellar traveler remains unchanged in its course. And occasionally, very occasionally, it passes close enough to a star to feel a subtle influence. A few gravitational encounters over 1 billion years are enough to alter its trajectory just slightly. Each star that passes near the object leaves a fingerprint, a faint signature written into its path. These fingerprints accumulate, but they do not change the object's fundamental independence. No star ever fully captures it. It remains unbound, free, drifting in its long sleep. The stillness of this sleep is part of what makes the object's awakening so poignant. When a star finally approaches close enough, when the faint tug of gravity accelerates the object and directs it inward toward a planetary system, the sleep ends. Usually, the object does not know it yet. It continues drifting, unaware that it has entered the outer reaches of a star's influence. As it approaches the heliosphere of the new star, it begins to encounter solar particles for the first time in eons. The solar wind pushes against its surface. Electrons and ions interact with its crust. But even then, the object remains largely unchanged. Only when sunlight becomes strong enough to penetrate the irradiation mantle does the awakening begin. For 3I Atlas, this occurred when it approached the sun. After countless ages of dormancy, the object felt warmth, not heat, not enough to melt its surface, but enough to initiate the faintest processes of sublimation. Volatile molecules beneath the crust warmed. They expanded into gases, pressure built within tiny pockets. Eventually, the crust cracked in microfractures, releasing faint jets of gas and dust. This was the moment of awakening. After millions or billions of years in silent, frozen slumber, the object stirred. Not violently, not dramatically, but subtly, like a creature stretching after a long, dreamless sleep. A thin coma formed, not the bright, majestic tail of a young comet, but a ghostly haze that reflected sunlight in soft, diffuse glimmers. That faint glow was not just activity. It was the object's voice, the first whisper it had spoken in ages. From the long sleep between stars, 3I Atlas emerged into a world of light again. Its journey resumed, Not the quiet glide of interstellar drift, but the brief, bright arc through a planetary system. And for a moment, it allowed humanity to witness its awakening. One of the most powerful forces acting on an interstellar object during its long drift through the galaxy is cosmic radiation. Unlike sunlight, which warms and melts and alters surface materials through heat, cosmic rays reshape objects through relentless high-energy impacts. They are the sculptors of interstellar surfaces, the agents of chemical transformation, the keepers of cosmic time. And for 3I Atlas, cosmic radiation was a defining factor in its evolution. Cosmic rays are subatomic particles, mostly protons, some electrons, occasional heavier nuclei, accelerated to incredible energies by astrophysical events. Supernova explosions blast shockwaves into space, flinging particles outward at near light speeds. Rapidly rotating neutron stars send out beams of radiation energetic enough to strip atoms apart. Black hole accretion disks hurl particles in all directions. These events create what becomes a diffuse, ever-present rain of high-energy particles filling the galaxy. Interstellar objects drift directly through this radiation. With no atmosphere to shield them and no magnetic field to deflect it, the particles strike their surfaces unimpeded. The effects are cumulative and profound. When a cosmic ray proton impacts the surface of an icy body like 3I Atlas, it transfers enormous energy to the molecules it hits. Bonds shatter, new bonds form. Simple ices like water, carbon dioxide, methane, and ammonia are chemically processed into more complex organic compounds. Over time, these reactions form dark, carbon-rich materials, substances similar to the refractory organics found on the surfaces of some comets and outer solar system moons. This process creates the darkened crust that coats many interstellar objects. In the case of 3I Atlas, the faint activity observed during its passage through the solar system suggested that the object's crust had been hardened by eons of irradiation. Beneath that crust lay fresher material, frozen and untouched since its formation. But the crust itself was a chemical record of its long exposure to the galaxy. Cosmic radiation is relentless but predictable. The rate at which particles strike a surface depends on the object's size, the density of the surrounding interstellar medium, and the local cosmic ray environment. Laboratory experiments and spaceborne detections have allowed scientists to estimate how quickly irradiation mantles form. These estimates provide a kind of cosmic clock. For 3I Atlas, the observed crust thickness, deduced indirectly from its activity level, suggested that it had been drifting in interstellar space for at least several million years. Some models suggested tens of millions. Others, using more aggressive assumptions, suggested hundreds of millions or longer. If the object came from the thick disk, the timescale could stretch into billions. This is what cosmic radiation offers. Not precision, but possibility. A glimpse into age, into duration, into the immense timescales of galactic drift. The chemical transformations induced by cosmic rays are equally fascinating. When radiation breaks molecular bonds, it creates radicals, molecules with unpaired electrons that are chemically reactive. In the vacuum of space, these radicals recombine into more stable structures. Over time, these structures accumulate into complex organic residues. Such compounds have been found on objects from comets to Kuiper belt bodies, and their presence on interstellar objects would be expected. This chemical processing could make interstellar objects appear darker, more reddish, and less reflective. 3I Atlas, though faint, showed signs of such darkness. Its photometric behavior hinted at a surface that reflected less sunlight than typical young comets. This darkness is a hallmark of cosmic ray processing. Another critical role cosmic radiation plays is in altering the mechanical properties of the surface. Over time, radiation can compact and cross-link polymeric structures in organic materials, creating a stronger, more cohesive crust. This crust locks in buried volatiles. Only when heat penetrates the crust does sublimation begin. This explains why 3I Atlas displayed subdued activity. It was insulated by its own history. Radiation also contributes to the fragmentation of interstellar objects. Over long periods, repeated irradiation and micrometeorite impacts can weaken structural cohesion, making the object more susceptible to fracturing when exposed to strong thermal gradients. In extreme cases, such objects might break apart during close passage to a star. But 3I Atlas survived. Its structure remained intact through its encounter with our Sun. This resilience suggests a strong composition, perhaps a body composed of tightly bound ices and dust with a robust organic crust. Cosmic radiation is not uniform across the galaxy. Regions near star-forming areas, supernova remnants, or active galactic structures can have higher fluxes. Regions of the galactic disk differ from those of the thick disk. The object's cosmic ray exposure therefore encodes information about where it has been, not just how long it has traveled. For example, if 3I Atlas spent time in the thick disk, it might have experienced slightly different cosmic ray environments than an object drifting through the dense spiral arms of the thin disk. Each region leaves subtle chemical hints. Scientists cannot see these hints directly from afar, but they can infer them through comparisons with known irradiation effects. The faintness of 3I Atlas limited detailed spectroscopic analysis, yet its behavior alone provided clues. Objects with heavily irradiated crusts tend to exhibit delayed onset of activity, low dust release, and faint gas production. 3I Atlas showed all of these traits. Cosmic radiation may also have affected the object's rotational behavior. Over time, small jets from sublimation events, even extremely subtle ones, can impart torque. In interstellar space, where such events are rare, cosmic ray-induced microfractures might occasionally release faint puffs of gas that alter the spin ever so slightly. These tiny changes accumulated over millions of years would shape the object's rotation state by the time it reached the solar system. Radiation also preserves interior fluids. Paradoxically, the crust created by radiation protects the object's interior from further processing, sealing in the chemistry of its formation. This is why interstellar objects are so scientifically precious. They contain primordial material protected by a radiation-developed shell. When 3I Atlas entered the Sun's sphere of influence, it carried the full weight of this cosmic history on its surface. The way it glowed, the way it released dust, the color it reflected, all of these were products of its encounter with cosmic radiation. And when the Sun's warmth began to peel back the crust, releasing faint gases into the vacuum, it was as though the object was revealing its ancient story, molecule by molecule. Cosmic radiation is not just a destructive force. It is a storyteller, a chronicler of time. For an object like 3I Atlas, radiation was the sculptor that shaped its surface, the guardian that preserved its interior, and the silent historian that marked the passage of epochs. Its journey through the galaxy is written in radiation. And now, passing through the solar system, it shared a fragment of that story with us. When we imagine an interstellar object drifting through the Milky Way, it is easy to picture it as a stone floating in perfect emptiness, untouched and unchanging. But the galaxy is not empty, and the path of an object like 3I Atlas is never truly straight. Though space seems quiet on human timescales, the Milky Way is a vast ocean of invisible forces, currents, tides, waves, and gradients, all acting slowly, subtly, and inexorably over millions or billions of years. These forces shape the path of every star, every cloud of gas, and every wandering object expelled from its home system. 3I Atlas did not drift through a blank void. It traveled through a galaxy alive with structure. The most obvious force is gravity. The Milky Way is a gravitational system held together by hundreds of billions of stars, enormous clouds of gas, and a halo of dark matter whose mass dwarfs all the luminous components combined. This gravitational field creates a dynamic flow, one that determines how everything moves. Interstellar objects, once ejected, fall under the influence of this galactic potential. The galaxy's gravitational potential is not uniform. It varies by location. Near the center, the gravitational field is strong, and objects orbit rapidly. In the mid-disk, where the Sun resides, the gravitational forces are balanced between the pole of the central bulge and the mass of the disk itself. Farther out, rotation curves flatten due to the influence of the dark matter halo. 3I Atlas traveled within this complex gravitational map. Its long-term path was influenced by the total mass of the galaxy, not just individual stars. Over time, the galaxy's tides, gradients in gravitational force that stretch and compress orbits, altered its trajectory. These galactic tides are weak on human timescales, but powerful over millions of years. They slowly reorient the object's motion, causing slight oscillations above and below the galactic plane. These oscillations may have brought 3I Atlas into different environments within the galaxy. The object might have spent time passing through regions dense with stars, then moved into sparsely populated areas, then into the outskirts of a spiral arm. Each region leaves subtle chemical hints. Scientists cannot see these hints directly from afar, but they can infer them through comparisons with known irradiation effects. The faintness of 3I Atlas limited detailed spectroscopic analysis, yet its behavior alone provided clues. Objects with heavily irradiated crusts tend to exhibit delayed onset of activity, low dust release, and faint gas production. 3I Atlas showed all of these traits. Cosmic radiation may also have affected the object's rotational behavior. Over time, small jets from sublimation events, even extremely subtle ones, can impart torque. In interstellar space, where such events are rare, cosmic ray-induced microfractures might occasionally release faint puffs of gas that alter the spin ever so slightly. These tiny changes accumulated over millions of years would shape the object's rotation state by the time it reached the solar system. Radiation also preserves interior fluids. Paradoxically, the crust created by radiation protects the object's interior from further processing, sealing in the chemistry of its formation. This is why interstellar objects are so scientifically precious. They contain primordial material protected by a radiation-developed shell. When 3I Atlas entered the Sun's sphere of influence, it carried the full weight of this cosmic history on its surface. The way it glowed, the way it released dust, the color it reflected, all of these were products of its encounter with cosmic radiation. And when the Sun's warmth began to peel back the crust, releasing faint gases into the vacuum, it was as though the object was revealing its ancient story, molecule by molecule. Cosmic radiation is not just a destructive force. It is a storyteller, a chronicler of time. For an object like 3I Atlas, radiation was the sculptor that shaped its surface, the guardian that preserved its interior, and the silent historian that marked the passage of epochs. Its journey through the galaxy is written in radiation. And now, passing through the solar system, it shared a fragment of that story with us. When we imagine an interstellar object drifting through the Milky Way, it is easy to picture it as a stone floating in perfect emptiness, untouched and unchanging. But the galaxy is not empty, and the path of an object like 3I Atlas is never truly straight. Though space seems quiet on human timescales, the Milky Way is a vast ocean of invisible forces. Currents, tides, waves, and gradients, all acting slowly, subtly, and inexorably over millions or billions of years. These forces shape the path of every star, every cloud of gas, and every wandering object expelled from its home system. 3I Atlas did not drift. Each region imparted its own subtle influence. The spiral arms, in particular, are not physical structures, but density waves. Regions where star formation, gas density, and gravitational potential fluctuate. When an interstellar object passes through a spiral arm, it experiences a slightly higher gravitational pull due to the increased mass concentration. The exact effect is small but cumulative. Over millions of years, such interactions can alter the object's velocity, tilt its trajectory, or shift its inclination relative to the galactic plane. Another force acting on interstellar objects is gravitational encounters with stars. Most stars exert negligible influence because distances are enormous. But over long epochs, chance encounters accumulate. Even a flyby at several light-years distance can alter the object's course. Each small change accumulates into a chaotic pattern. The final trajectory is the sum of countless tiny pushes from stars that passed nearby long ago and whose names we will never know. The gravity of giant molecular clouds, massive structures filled with gas and dust, also leaves its mark. These clouds are thousands of times more massive than the Sun. When an interstellar object passes near one, even at great distance, its velocity changes slightly. These changes can shift the object's path by enough to alter its ultimate destination by tens of light-years over cosmological timescales. Then there are the galaxy's magnetic fields. While interstellar objects are not charged, and therefore not directly influenced by magnetic fields, the behavior of cosmic rays, which constantly bombard the object, depends on these fields. Regions with stronger magnetic fields produce different cosmic ray fluxes, which in turn alter the radiation processing of the object's surface. In this way, the magnetic structure of the galaxy indirectly affects the chemistry of an interstellar traveler. All these forces intertwine, creating a subtle but continuous sculpting of motion. For 3I Atlas, this interplay of invisible influences shaped a journey that cannot be fully reconstructed. The uncertainties grow too large as we trace the object farther into the past. After a few million years, the possible trajectories diverge into a fan of possibilities. After tens of millions, the galaxy's chaotic nature turns the object's past into an untraceable labyrinth. But the inability to identify a precise origin does not diminish the story. Instead, it reveals something profound, that the galaxy itself is a fluid environment, one where every object moves through a sea of gravitational interactions. One can imagine 3I Atlas drifting through the spiral arms, passing near star clusters, gliding past dead stars, drifting above and below the galactic plane like a leaf caught in a cosmic tide. It encountered regions warm with starlight and others cold with emptiness. It crossed paths with stars that had long ago merged into new structures or wandered elsewhere. For most of its journey, there were no planets to warm it, no star to illuminate it, no collisions to reshape it. Instead, it existed in a state of extraordinary stillness, broken only by the slow pull of gravity and the steady erosion of cosmic radiation. This long exposure to galactic forces shaped the object into what it was when we found it. Its surface chemistry carried the imprint of dozens of cosmic environments. Its trajectory carried the signature of countless gravitational encounters. Its velocity reflected the motion of the galactic disk itself. This is why interstellar objects are so valuable. They are messengers not just from one star, but from the galaxy as a whole. They drift through multiple environments, experiencing the Milky Way in a way nothing bound to a single star ever could. 3I Atlas traveled through the galaxy's invisible currents for longer than the age of many planets. And when it finally approached our solar system, it carried this entire cosmic history on its surface. Every speck of dust, every faint emission, every curve of its orbit whispered a tale shaped by forces far larger and older than our Sun. And now, for a brief moment, humans could listen. Interstellar objects are more than curiosities. They are more than visitors, more than rare cosmic events, more than objects with unusual orbits. They matter because they represent something far deeper, A link between stellar systems, a physical connection between the worlds of the galaxy, a sampler of materials from places humanity may never reach. When 3I Atlas entered the solar system, it brought with it a story billions of years in the making, one that began around another star and unfolded in silence across light years of empty space. Its brief appearance allowed astronomers to glimpse that story, even if only in fragments. And that glimpse revealed why interstellar objects are so important. First, they are direct samples of other solar systems. The composition of an interstellar comet carries the chemistry of its birthplace. Every molecule within it formed in the disk of another star. Every particle of dust originated in a different stellar nursery. Every volatile ice formed in temperatures and pressures we can only infer. While telescopes allow us to study distant systems indirectly through light curves, spectra, or gravitational signals, interstellar objects are the only pieces of alien solar systems that physically enter ours. Even with limited data, 3I Atlas offered insight into the chemistry of its home environment. Its faint activity suggests it carries ices similar to those in comets of the solar system. This indicates that the processes forming icy planetesimals are universal, not unique to our Sun. If its composition had been dramatically different, that would have hinted at exotic chemical environments. But its familiarity tells a more profound story. The galaxy shares a common blueprint for building worlds. Second, interstellar objects reveal the processes that shape planetary systems. The trajectory of 3I Atlas tells us it was ejected. How it was ejected depends on the dynamics of its original system. Whether through giant planet migration, stellar evolution, a binary star encounter, or early disk turbulence, the mechanism provides information about the architecture of other systems. Every interstellar object is a data point in understanding how planetary systems evolve, how they eject material, and how often they produce wanderers. The more such objects we detect, the more accurately we can model these processes. Third, interstellar objects help explain the origin of the solar system's own structures. Our solar system has a massive Oort cloud, a vast spherical population of comets extending halfway to the nearest star. But how did it form? One theory suggests that interactions between the early Sun and nearby stars caused debris to be flung outward. Another theory posits that some Oort cloud bodies may not have originated in the solar system at all. They may be captured interstellar objects. Studying objects like 3I Atlas helps test these theories. If interstellar objects are common, then capture becomes more likely. Their compositions may even resemble some solar system comets if both populations share similar origins. Fourth, interstellar objects provide a way to study material older than Earth. If 3I Atlas came from the thick disk, then its interior could preserve chemistry from the early galaxy. Such material would be older than any comet in the solar system. Even if it came from the thin disk, it may still predate the Earth by hundreds of millions of years. Interstellar objects allow astronomers to study ancient chemical processes directly, offering clues about how the galaxy's composition evolved over time. Fifth, interstellar visitors offer a window into the distribution of small bodies in the Milky Way. For decades, astronomers believed interstellar debris existed, but they had no direct evidence. Oumuamua and Borisov were the first proof. 3I Atlas became the third. Each detection indicates that such objects may be far more abundant than once thought. Their detection rate suggests the galaxy is filled with trillions upon trillions of icy fragments drifting silently through space. This has profound implications. It means the exchange of material between solar systems is constant. It means no system is isolated. It means planetary formation everywhere contributes to a vast galactic ecosystem of drifting debris. Sixth, interstellar objects may play a role in the spread of organic molecules. While the idea of panspermia remains speculative, it is undeniable that comets contain complex organic molecules. Interstellar objects could carry such molecules from one system to another. Even if they do not carry life, they may carry the building blocks of life, scattering them across the galaxy. 3I Atlas likely contained organics formed through cosmic ray processing. These molecules, if delivered to a young planetary system, could contribute to its chemical diversity. 7th, interstellar objects challenge and refine our detection capabilities. 3I Atlas was faint, it was subtle, it nearly escaped detection. Its discovery showed that the next generation of sky surveys, especially the Vera Rubin Observatory, will detect many more such objects. Improving these capabilities opens an entirely new field of astronomy, interstellar small body science. Each object detected will expand our understanding of the galaxy. Finally, interstellar objects illuminate our place in the cosmos. Before their discovery, humanity viewed the solar system as a mostly closed system, a place where objects formed and stayed. Now we know the truth. The solar system is open. It exchanges material with the galaxy. It receives visitors from distant stars. And one day, it may send fragments from our own world into other star systems. 3I Atlas matters because it reminds us that our story is part of a much larger one. The galaxy is not a set of isolated islands. It is an interconnected web of worlds, exchanging fragments across unimaginable distances and timescales. Every interstellar visitor is a chapter in that shared story. 3I Atlas is one such chapter, and because we observed it, however briefly, we now know a little more about the galaxy we call home. For millions, perhaps billions of years, 3I Atlas drifted quietly between the stars. It existed in a state of perfect cosmic anonymity, untouched by sunlight, shaped only by gravity, radiation, and time. But every interstellar journey eventually crosses a new boundary. For 3I Atlas, that boundary was the invisible frontier of our solar system, the heliosphere, the vast bubble carved into interstellar space by the solar wind. And the moment it crossed into this domain marked the beginning of its brief awakening. The entry of an interstellar object into the heliosphere is a silent event. There is no shock wave, no flare of light, no sudden change in temperature. Even the solar wind is tenuous, so sparse that every square centimeter contains only a few protons. Yet for an object that has spent millennia drifting through the quiet interstellar medium, the heliosphere is a different environment. It is warmer, more energetic, more dynamic. And its influence, though gentle, begins long before sunlight becomes strong enough to awaken any buried ices. When 3I Atlas crossed the heliopause, the boundary separating the solar wind from the interstellar medium, it entered a region shaped entirely by the sun. Here, charged particles stream outward from the star in all directions. These particles, though diffuse, interact with the surface of any object they encounter. They accumulate charges. They create faint chemical reactions within the uppermost layers of dust. They subtly warm the surface. For 3I Atlas, these were the first environmental changes it had experienced in ages. But the sleep was not broken yet. As it drifted inward, the solar wind intensified. The solar magnetic field pressed against the object, producing forces too faint to alter its trajectory, but strong enough to begin stirring the dust clinging to its crust. The sun, from a distance of tens of billions of kilometers, began to exert its influence as an environment, rather than just a gravitational force. The object felt this subtly. Its rotation, long stabilized by countless years of inertia, remained unchanged. But its outermost frost, microns deep, began to shift. Dust grains, electrically charged by solar particles, might have moved slightly across the surface. The interstellar traveler was no longer in the silent deep. It was in a region alive with energy, even if that energy was too weak to warm it substantially. Still, it was not until the object crossed into the scattered outskirts of the Kuiper belt that its transformation truly began. The Kuiper belt is not dense, far from it. Vast spaces separate its icy bodies. But compared to interstellar space, it is structured, gravitationally organized, filled with objects orbiting under the sun's control. Passing through this region is like entering a silent city whose inhabitants do not stir. The presence of other objects changes nothing for 3I Atlas, yet for the first time in ages, it was among cousins, icy bodies with shared origins in planetary formation, though not from its own system. This region also illuminated another subtlety of its passage. As 3I Atlas moved inward, telescopes on Earth were not yet aware of its existence. It remained invisible, its faint glimmer lost among the distant stars. But its entry trajectory, the angle, the speed, the direction, was already locked in. The sun's gravity bent its path gently, turning its long, straight line into a curved arc. Inside the Kuiper belt, sunlight became stronger, still faint, but no longer negligible. Photons struck its surface with enough force to lift the very first molecules from its crust. The radiation-hardened mantle resisted sublimation, but sunlight crept into microscopic cracks and pores. Minute quantities of ancient gases, perhaps carbon monoxide or carbon dioxide, escaped into space. Not enough to form a coma, not enough to be detected, but enough to signal that the long sleep was ending. The first true warming occurred when the object crossed the distance where Jupiter orbits, even though it never approached the gas giant itself. At this distance, sunlight is weak but not powerless. The crust absorbed heat slowly. Beneath the crust, molecules vibrated. Volatiles trapped for ages began to test the strength of the surface. Still, 3I Atlas remained quiet. Its awakening would be subtle, not explosive. Meanwhile, Earth's telescopes remained unaware of the visitor streaking inward. Nothing yet distinguished it from the millions of other faint, distant points of light in the background sky. But something remarkable was about to happen, not in space, but on Earth. Night after night, the Atlas survey scanned the sky, searching for anything moving against the background stars. And one night, a faint point of light appeared in two images taken minutes apart. It shifted slightly, a tiny motion, but unmistakable. The automated systems flagged it. It was moving faster than the distant stars, meaning it was nearby relative to galactic distances. Data streams captured its trajectory. Orbital calculations began quietly in background processes. Nothing yet signaled the extraordinary nature of this discovery. Then more images arrived, more positions plotted, and something began to emerge, a trajectory bending more than expected, moving too rapidly, approaching from an angle that didn't match known populations of solar system bodies. The moment of entry into the heliosphere, into the solar system, into human scientific awareness was not a single instant. It was a sequence of subtle transitions, each one bringing the object closer to the revelation it carried. As 3I Atlas drifted inward, it did not know it was being watched. It did not know it had crossed a boundary that matters to humans. It did not know it was about to become a piece of astronomical history. But the moment it entered the heliosphere, its story became something more than a cosmic drift. It became a visitor, a messenger, a fragment from another world arriving at our doorstep. And that simple shift, from interstellar isolation to solar system presence, made all the difference. For the first time in its long journey, it was close enough for someone, somewhere, to notice. The moment of entry marked the beginning of a brief period when humans could finally witness what it was. When sunlight first touches an interstellar object after its long sojourn in the cold, the moment is not dramatic. There is no sudden flare, no explosion, no roaring jets of vapor. Instead, the awakening is slow, patient, almost shy. Light travels across billions of kilometers of empty space to reach the wanderer, and when it arrives, the transformation begins at the molecular level, quietly, invisibly, inevitably. For 3I Atlas, this moment marked the beginning of its brief visibility. A faint, ancient traveler, darkened by cosmic rays, hardened by eons, carrying secrets from distant stars, had entered the reach of our sun's warmth. The first thing sunlight does is strike the surface. Photons traveling at the speed of light, each delivering a small packet of energy. On the irradiation mantle of 3I Atlas, these photons break molecular bonds, releasing radicals created long ago by cosmic ray bombardment. These radicals react with other molecules, creating volatile compounds such as CO and CO2. In colder regions, these gases remain trapped. But as the object draws closer to the sun, they begin to seep out. At first, the release is microscopic. Molecules leave the surface in numbers too small to detect, but each one carries thermal energy away from the crust. Each one contributes to a gentle pressure beneath the surface. Over time, this pressure widens tiny cracks. These cracks allow more gas to escape. The process accelerates, though never dramatically. Unlike a young comet, whose interior is fresh and easily sublimates, 3I Atlas exhibits restraint. Its crust resists sublimation. Only in deeper layers does the true inventory of ancient ices remain. But sunlight continues to seep in. Day after day, as the object moves inward, the warming continues. The physics of sublimation depends on both temperature and composition. Different ices vaporize at different distances from the sun. Carbon monoxide sublimates at very low temperatures, so even faint sunlight can free it. Carbon dioxide requires slightly stronger warming. Water ice requires much more heat and may not sublimate significantly until closer to the inner solar system. But for an object like 3I Atlas, faint, small, ancient, hardened, the early activity is dominated by the most volatile components. These volatiles form the first traces of a coma, but this coma is nearly invisible. A coma is a cloud of gas surrounding a cometary body. But 3I Atlas, with its thick crust, releases only small amounts of gas. These trace gases may not scatter enough sunlight to be seen easily, yet they matter profoundly. They reveal that beneath the layers of cosmic ray processing, the object still retains its original chemistry. As 3I Atlas absorbs more sunlight, dust begins to lift from its surface. Not in dramatic jets like Comet Borisov, not in spectacular outbursts like some solar system comets. Instead, faint dust grains drift outward, pushed by gas expanding into space. These grains form a tenuous haze around the object, one too faint to be noticed by early observations, but undeniable once models account for the object's brightness profile. This moment, when dust first leaves the surface, is significant. It marks the first time the object interacts with a star in perhaps millions of years. It is the first time sunlight has touched its deeper layers. It is the first time it has shed material since its ejection. It is a kind of rebirth, a quiet emergence from cosmic isolation. As 3I Atlas continues inward, the rate of sublimation increases slightly, but its crust resists. Unlike Borisov, whose dramatic activity signaled a surface rich in exposed ice, 3I Atlas behaves like a seasoned wanderer, careful, cautious, releasing only what the warming forces from beneath it. The sunlight also reveals another property of interstellar objects, their color. 3I Atlas appears faint and slightly reddened, consistent with a surface coated in organic-rich materials created by long-term cosmic ray irradiation. These materials absorb blue light more efficiently than red light. The result is a reddish cast typical of radiation-hardened surfaces. This coloration is another hint of the object's age and interstellar tenure. As the object brightens, astronomers using automated surveys begin to notice it. At first, it appears as a faint point of light. Then, as more observations accumulate, something becomes clear. Its brightness does not follow the typical pattern of an inert asteroid. There is subtle enhancement, subtle signs of activity, subtle deviations from what a rocky, inactive body would exhibit. These deviations lead astronomers to suspect a cometary nature. Meanwhile, sunlight continues its work. It warms the object slowly, gradually, layer by layer, molecule by molecule. Each photon that strikes the object carries the possibility of awakening a little more of its interior. Yet the warming is not uniform. The rotation of the object means some regions face the sun longer than others. Thermal gradients form. These gradients produce stress across the crust. Sometimes microfractures expand. Sometimes small pieces of dust detach. Over days and weeks, the object adjusts to its new environment. This entire process, gentle warming, faint sublimation, tiny dust release, is the sun's way of introducing itself. After ages of drifting through darkness, 3I Atlas has found another star. And that star is touching it, awakening it, reviving chemistry that has been dormant for an unimaginable length of time. If interstellar objects could speak, this would be their moment of breath. Light touches an ancient traveler. The traveler responds, quietly but unmistakably. And in that response lies the key to understanding where it came from, what it is made of, and how long it roamed the galaxy. As the sun warms it further, the object brightens enough for humanity to study it. Telescopes capture its faint glow. Astronomers model its orbit. Its interstellar nature becomes undeniable. And all of this, the detection, the study, the understanding, begins with a single, profound moment. Light touches an ancient traveler. The rest is the story it chooses to reveal. There is a moment in the life of every comet, whether it was born in our solar system or in the distant cradle of another sun, when the heat of a star awakens it. For 3I Atlas, that moment came slowly, hesitantly, as though the object were reluctant to break the silence it had held for ages. But like all things bound by physics, it could not remain dormant forever. As sunlight seeped into the layers beneath its radiation-hardened crust, the first wisps of gas began to escape. This is the birth of a coma. A coma does not appear all at once. It is not a sudden eruption of vapor or a dramatic explosion of ices. Instead, it begins as a whisper. Molecules, ancient, frozen, preserved from a world that may have ceased to exist, start to vibrate as they absorb heat. They tremble within their crystal structures, gaining energy. Eventually, some gain enough energy to break free. At first, these molecules seep out through nanopores in the crust. They escape like specters, invisible and unmeasurable. The pressure they create beneath the crust remains small, insufficient to break through. The object continues to drift, its surface altering in ways imperceptible even to the most sensitive telescopes. But as 3I Atlas continues its inward approach, the energy from the sun increases. The rate of sublimation rises. More gas collects beneath the surface. The pores widen. Where once only single molecules escaped, now clusters of molecules begin to move. The crust, though strong, is not invincible. It was forged through cosmic ray bombardment, not mechanical compression. It contains weaknesses, thin fissures, ancient microfractures, voids created millions of years earlier by radiation impacts. These weaknesses are the gateways through which the coma is born. Bit by bit, gas escapes, carrying tiny dust particles with it. These grains, only microns in size, drift outward in the vacuum, pushed by the expanding gas. They form a hazy envelope around the object, still faint, still subtle, but now measurable in the way it scatters sunlight. This is how astronomers first suspect a coma, not by seeing gas directly, but by noting its indirect effects. A comet with even a tiny coma appears brighter than a bare rock of the same size. The brightness does not match a purely reflective surface. There is a softening of its visual profile, a smearing of light across pixels that cannot be explained by the optics of the telescope alone. This faint blurring was one of the early clues that 3I Atlas was not an inert asteroid. The coma, even in its earliest stages, is more than a cloud. It is a revelation. It tells astronomers that the object contains ices. It tells them that the object is not metallic or rocky. It tells them that the object has a layered structure shaped by time. Most importantly, it tells them that the object once belonged to a region in its home system where ices were abundant, likely beyond the frost line of its star, perhaps in a region analogous to the Kuiper Belt or the inner edge of an Oort cloud. A coma also reveals something about the object's past. The thickness of the crust determines how easily sublimation can occur. A young comet with a thin outer layer erupts quickly. A heavily processed one, hardened by millions of years of radiation, awakens slowly. The behavior of 3I Atlas matched the second pattern. Its coma was faint, reluctant, subdued. This subtlety allowed scientists to infer something extraordinary, that the object may have been traveling through interstellar space for far longer than the solar system has existed. A short interstellar journey would not produce such a hardened crust. The extent of cosmic ray processing points to a lifespan measured not in millions, but possibly in billions of years. The coma also carries the chemical fingerprint of the object's interior. Though direct measurements were limited due to the object's faintness, the early gas likely consisted of the most volatile ices: carbon monoxide, carbon dioxide, perhaps small amounts of nitrogen-bearing compounds. These are the first to sublimate. Only later, if ever, would more complex ices like water vapor emerge. But even without direct measurements, astronomers know that any coma at all is significant. It confirms that interstellar objects can preserve volatile ices for extreme periods of time. It challenges earlier assumptions that such objects, drifting unprotected through the galaxy, would lose their ices. Instead, the hardened crust acts as a shield, preserving the interior material. As the coma forms, it interacts with the solar wind. Charged particles from the sun collide with gas molecules, creating ions. These ions begin to form a tail, not the bright, sweeping tail of a young, vigorous comet, but a faint, delicate thread pushed outward by the pressure of the solar wind. If observed closely enough, such a tail reveals not only the composition of the gas, but also the interaction between the object and its new stellar environment. 3I Atlas's tail was too faint for detailed study, but its presence, suggested indirectly through modeling, hinted at the same underlying processes observed in other comets. The coma also affects the object's rotation. Gas escaping through cracks produces minuscule jets. These jets impart torque, slowly altering the spin. Over time, these changes can accumulate, reshaping the object's rotational dynamics. For a small object like 3I Atlas, even faint outgassing might cause measurable rotation changes, though detecting them at such distances is beyond current capabilities. Still, the physics remains the same. The coma is both a signature and a sculptor. As sunlight continues to warm the object, the coma grows slightly. It remains modest, a whisper compared to the roaring comas of comets like Hale-Bopp or 2I Borisov. But size is not the measure of significance. Even a faint coma carries vast scientific value. It means the object is alive in the most cosmic sense, responsive, reactive, shaped by the presence of a star. It means that within it, locked beneath ancient layers, lies preserved material from its birth system. It means that humanity is witnessing a chemical awakening older than its species, older than its planet, older than its star. A coma begins to rise. A traveler stirs. The object that drifted silently for ages begins to reveal itself in delicate, glowing breath. This is the moment when 3I Atlas stopped being a distant point of light and became a living remnant of another star's world. The coma is only the first sign that a comet has awakened. The second, often more dramatic, more iconic, and more scientifically revealing, is the tail. A comet's tail is not a single structure, but a complex interplay of forces. a dance between sunlight, gas, dust, and the solar wind. For 3I Atlas, the tail was faint, almost shy in its appearance, but even its subtle presence carried profound meaning. Every comet's tail forms through two primary processes. The first involves dust, the second involves gas. Together, they reveal the history, composition, and structure of the object. When gas escapes from beneath the surface of a comet, it expands outward, pushing dust grains with it. These grains, liberated from the crust, drift into the surrounding space. Sunlight then scatters off these grains, creating the dust tail. The dust tail curves gently away from the sun, shaped partly by radiation pressure and partly by the motion of the comet itself. For 3I Atlas, the dust tail was extremely faint, so faint that early observations barely detected it. But faint does not mean absent. In fact, its faintness was itself a clue. A bright dust tail indicates abundant loose material on the surface. A faint dust tail indicates a surface that is tightly bound, compacted, or crusted over. For an interstellar object hardened by cosmic rays, this is exactly what astronomers expect. Dust must be excavated from beneath the crust or forced loose by gas pressure. 3I Atlas did release some dust, enough to alter its brightness profile subtly, but not enough to create a prominent tail. This faintness suggested a long exposure to interstellar conditions. The gas tail, formed when ionized molecules are pushed directly away from the sun by the solar wind, is usually straighter and narrower than the dust tail. It requires more detectable gas emission, which 3I Atlas did not produce in large quantities. Still, the object likely had an ion tail, however subtle, perhaps detectable only indirectly through small enhancements in the coma's directionality. Even a whisper of a tail is enough to unlock dozens of scientific insights. One insight concerns rotation. The direction of dust release can reveal regions of the surface where sublimation is strongest. If a tail is slightly asymmetrical, it may indicate the orientation of the comet's spin axis. For 3I Atlas, the faint asymmetry visible in some composite observations hinted at complex surface topography, regions where cracks allowed gas to escape more readily, or regions shielded by the object's shape. Another insight concerns composition. Dust grains scattered into the tail carry information about the object's interior. Larger grains suggest a stronger crust or deeper origin. Smaller grains suggest surface-level erosion. The most detailed analysis possible from 3I Atlas indicated a mix of fine and moderately sized particles, consistent with an irradiated surface that fractures into small pieces. The interaction of the tail with the solar wind also matters. When the solar wind collides with gas molecules, it ionizes them, creating charged particles that form the ion tail. The shape and length of this tail can reveal the object's gas production rate and the strength of its sublimation. Because 3I Atlas produced only faint gas, the expected ion tail was thin, short, and perhaps too faint to see directly. Still, its existence is nearly certain because physics requires it. Any gas in the presence of the solar wind must produce ions. The tail also tells a story about the object's age. Objects that have been in interstellar space for extremely long periods develop a crust so thick that the deepest ices rarely sublimate. Such objects produce extremely faint tails. This places 3I Atlas in a category distinct from solar system comets that have spent far less time exposed to high-energy radiation. In a sense, the faintness of the tail is not a sign of weakness, it is a sign of endurance. Another layer of complexity comes from the object's shape. The shape of a comet affects how gas escapes, how dust is lifted, and how the tail forms. While 3I Atlas was far too distant and faint for direct shape measurement, the behavior of its coma and tail allowed astronomers to infer that it might not be perfectly spherical. Instead, it likely had an irregular shape, perhaps elongated, perhaps lumpy, perhaps sculpted by ancient collisions or radiation erosion. Irregular shapes produce asymmetric tails, especially when rotation causes different areas of the surface to heat unevenly. The faint but measurable differences in the brightness of 3I Atlas over time hinted at rotational modulation, light changing as different faces of the object turn toward Earth. These modulations, combined with tail orientation, suggest that gas release occurred in patches rather than uniformly. The tail also reveals the object's velocity relative to the Sun. Because ion tails always point directly away from the Sun, any deviation indicates interaction with magnetic fields or non-radial solar wind flows. Dust tails, by contrast, curve with the object's motion. Comparing the two can reveal the object's direction of travel. For 3I Atlas, this analysis confirmed its hyperbolic trajectory, another signature of its interstellar origin. A tail is a comet's testimony. It is the visible expression of its chemistry, its structure, its history, and its interaction with the star it approaches. For 3I Atlas, the tail may have been faint, but its message was profound. It told astronomers that the object still contained ancient ices. It told them that the object carried dust particles formed in a star system that may no longer exist. It told them that the object was active, but only subtly, a traveler hardened by time. It told them that light had reached its surface after ages of darkness, awakening processes that had been dormant longer than human civilization. Even a faint tail tells a story. 3I Atlas whispered its story across millions of kilometers of space, and for a brief moment, humans were listening. When astronomers first detect a faint, fast-moving object in the outer solar system, one of the earliest questions they ask is deceptively simple. Is it a comet or is it an asteroid? For centuries, these two categories seemed distinct. Comets grew coma and tails when warmed by the sun. Asteroids remained inert, rocky, silent. Comets were icy, fragile, ancient messengers from the solar system's cold outskirts. Asteroids were rocky remnants of the inner regions. The distinction felt clear. But the cosmos has little regard for our categories. Over the past few decades, astronomers have discovered that the line separating comets from asteroids is not a line at all. It is a gradient, a continuum shaped by age, environment, and history. Many objects blur the boundary. Some asteroids show comet-like activity. Some comets fade until they resemble asteroids. Some bodies alternate behaviors depending on their thermal cycles. And then there are the interstellar objects, wanderers that do not fit neatly into either category. 3I Atlas is one such boundary breaker. When first observed, its faintness suggested a small, inert asteroid. Its brightness did not immediately reveal activity. Its surface appeared dark and light-absorbing, similar to many asteroids in the solar system that have been weathered by time. But as more observations accumulated, a different picture emerged. The brightness changed subtly over time. The object appeared slightly more diffuse than a rock of its size should, and the shape of its light curve hinted at the presence of a faint coma. These contradictions forced astronomers to question its identity. Was 3I Atlas a comet, an asteroid, something in between? The answer lies in the physics of sublimation and the chemistry of an irradiated crust. A typical comet from the solar system contains icy material near the surface. When it approaches the sun, these ices warm and sublimate, producing gas and dust. The presence of a coma is one of the clearest indicators of a cometary nature. Asteroids, especially those from the inner regions of the solar system, lack substantial ices. Even if they contain trace volatiles, their surfaces often do not release them in detectable quantities. They remain dormant. But interstellar objects begin with a different history. They are formed in distant systems, possibly under conditions not identical to those of our own. They may contain volatile ices that are not typical of local asteroids, or they may contain organics hardened by cosmic rays. More importantly, interstellar objects undergo extreme surface processing during their long flight through the galaxy. 3I Atlas is one such boundary breaker. When first observed, its faintness suggested a small, inert asteroid. Its brightness did not immediately reveal activity. Its surface appeared dark and light-absorbing, similar to many asteroids in the solar system that have been weathered by time. But as more observations accumulated, a different picture emerged. The brightness changed subtly over time. The object appeared slightly more diffuse than a rock of its size should, and the shape of its light curve hinted at the presence of a faint coma. These contradictions forced astronomers to question its identity. Was 3I Atlas a comet, an asteroid, something in between? The answer lies in the physics of sublimation and the chemistry of an irradiated crust. A typical comet from the solar system contains icy material near the surface. When it approaches the sun, these ices warm and sublimate, producing gas and dust. The presence of a coma is one of the clearest indicators of a cometary nature. Asteroids, especially those from the inner regions of the solar system, lack substantial ices. Even if they contain trace volatiles, their surfaces often do not release them in detectable quantities. They remain dormant. But interstellar objects begin with a different history. They are formed in distant systems, possibly under conditions not identical to those of our own. They may contain volatile ices that are not typical of local asteroids, or they may contain organics hardened by cosmic rays. More importantly, interstellar objects undergo extreme surface processing during their long flight through the galaxy. Cosmic radiation bombards them continuously, turning their outer layers into a hard, dark shell. This shell suppresses sublimation. Gases cannot escape until the crust cracks. Dust does not lift easily. As a result, even objects with substantial interior ices can appear inert. 3I Atlas, in this sense, behaves like a transitional object. It contains ices, like a comet. It releases gas, however faintly. It produces a coma, but its surface behaves like an asteroid's, hard, compact, resistant to activity. Its activity is not bright, not showy, not explosive. It is controlled and subtle. This is where the categories blur. An asteroid with rare faint outgassing would be called an active asteroid. A comet with a hardened crust and faint activity might be called a depleted comet. An interstellar object like 3I Atlas is both and neither. The distinction between a comet and an asteroid is ultimately about origin and behavior. If an object formed beyond the frost line, where ices were abundant, it is cometary by heritage. If it formed closer to its star, rocky and dry, it is asteroidal. But interstellar objects challenge these definitions. We cannot know where 3I Atlas formed. We cannot know its parent system's frost line. We cannot see its deep interior. We can only observe how it behaves now. And its behavior is comet-like, just faintly so. One could imagine an interstellar object that lost its ices entirely during its long journey. Such an object would behave as an asteroid, even if it began life as a comet. Conversely, an object with a thick irradiation crust could conceal its ice until very close to the star, making it appear asteroidal until it suddenly awakens. Guiding principles from comet science support this range of behavior. Comets that remain dormant for long periods develop crusts that resist sublimation. Over time, they may be misclassified as asteroids until they approach the Sun more closely than before, breaking open their crusts and producing unexpected comae. These returning comets sometimes surprise astronomers with sudden outbursts. 3I Atlas is not a returning comet, but the underlying physics is the same. Its crust is the product of age, not cycles around a star. But once sunlight reached its interior, the gases stirred. They escaped. They carried dust with them. This is a defining hallmark of a comet. Another clue lies in the object's trajectory. Although hyperbolic, meaning it is not bound to the solar system, its inbound speed is consistent with objects born through scattering from planetary systems. Comets, not asteroids, dominate that category. Systems eject icy bodies more easily than rocky ones because they are more abundant and form in regions susceptible to gravitational instabilities. The morphology of its coma also offers insight. Even faint activity tends to produce a particular brightness profile around the nucleus, an extension in the sunward direction, a slight thickening perpendicular to the motion, a gradient consistent with gas-driven dust release. 3I Atlas displayed signs of this morphology. Though faint, though subtle, the shape of its brightness matched cometary signatures more closely than asteroidal ones. But the most important evidence lies in its ability to respond to heat at all. Asteroids without volatiles do not respond to heat. They do not grow comae. They do not release dust through sublimation. They may produce dust through thermal fracturing, but the pattern is different, sharp, sudden, lacking the smooth gradients seen in comets. 3I Atlas showed smooth gradients. It showed gently increasing brightness as it neared the sun. It showed signs of gas-driven dust release. Thus, even if faint and subdued, its behavior confirms its cometary nature. But being a comet does not mean it resembles solar system comets. It might be structurally distinct. It might contain different volatile ratios. It might be shaped by evolutionary processes we do not yet understand. This ambiguity reveals something profound. Interstellar objects force us to confront the limits of our classifications. They show that the categories we use, asteroid, comet, are products of our local perspective. They remind us that the universe is not obliged to arrange itself according to our definitions. They challenge our assumptions, refine our tools, and expand the scope of what is possible. 3I Atlas is comet-like, but not in the way comets from the solar system are. It is asteroid-like, but not in the way asteroids from the solar system are. It is both, it is neither. It is something in between. It is a new kind of object, one that can only exist when a piece of a world is shaped by another star, cast into the galaxy, and preserved across cosmic time. The blurred line between comet and asteroid becomes not a source of confusion, but a gateway to understanding the diversity of planetary systems across the Milky Way. 3I Atlas sits at that boundary, reminding us that the cosmos is full of things we have yet to name. Before 3I Atlas arrived, humanity had encountered only two confirmed interstellar visitors: the enigmatic Oumuamua, whose shape and behavior sparked a global debate, and the remarkable comet 2I Borisov, whose spectacular activity made it appear almost indistinguishable from ordinary solar system comets, save for its origin. So when 3I Atlas appeared, the natural instinct of astronomers was to compare it to Borisov, the only other confirmed interstellar comet. The comparison is illuminating, not because the objects are similar, but because they are profoundly different. 2I Borisov was bright, active, and rich in volatiles. Discovered in 2019, it displayed a spectacular coma even before reaching perihelion. It produced jets, dust, and gas in quantities rivaling many solar system comets. Its brightness made it easy to observe with telescopes worldwide. Its chemical composition, measured directly through spectroscopy, revealed familiar molecules: water, carbon monoxide, cyanide. It was, in nearly every respect, a classical comet, one that just happened to come from another star. 3I Atlas, by contrast, was quiet, subtle, reserved. It behaved like a comet at the end of its life cycle, a body with a hardened crust, limited volatile exposure, and low-level activity. Where Borisov shed large amounts of dust and gas, 3I Atlas barely stirred. Where Borisov's coma stretched across thousands of kilometers, 3I Atlas's was faint and compact. Where Borisov produced dramatic images, 3I Atlas was almost invisible. The differences begin with origin. Borisov likely came from the thin disk, a region of the galaxy filled with young stars and active planetary systems. Its composition suggested it formed in a region cold enough for abundant ices to accumulate, perhaps in an outer disk similar to our Kuiper belt. Its ices remained fresh, unprocessed by cosmic rays, indicating it had not spent long drifting through interstellar space. 3I Atlas, in contrast, may have come from the thick disk. If so, it formed in a region of the galaxy far older than Borisov's birthplace. It may have been ejected billions of years ago. Its crust, hardened by eons of cosmic radiation, indicates a much longer interstellar journey. Its ices were preserved only beneath a thick, dark mantle. This difference in age explains much. The brightness of a comet's coma depends on how easily sunlight can access fresh ices. Borisov's ices were near the surface. 3I Atlas's were buried deep beneath the crust. The difference in composition also plays a role. Borisov contained volatile ices that sublimated easily. This produced dramatic jets. 3I Atlas likely contained similar volatiles, but the surface shielding delayed or suppressed their release. The difference in dust production is equally telling. Borisov produced dust in abundance. It shed grains into space with ease, creating dense tails. 3I Atlas released dust sparingly. Its crust held tightly to its particles. Only the deepest ices expelled tiny grains through narrow vents. Even their structural properties may differ. Borisov's strong activity suggests a porous, fragile structure. 3I Atlas, hardened by time, likely had a more cohesive surface. But the differences go deeper. Borisov gave astronomers a clear view of what a young interstellar comet looks like. Its composition and behavior showed that planetary systems beyond our own form comets remarkably similar to those here. This was a profound revelation, but also a comforting one. 3I Atlas, by contrast, showed what an ancient interstellar comet may look like. It represented the other end of the evolutionary spectrum. Its faint activity demonstrated how cosmic rays shape surfaces over long timescales. Its compact coma illustrated the effects of extreme aging. In this sense, 3I Atlas taught astronomers something new. Interstellar comets are not a single category. They exist on a spectrum shaped by age, origin, environment, and journey. They evolve differently depending on how long they drift between stars. This has profound implications for astronomy. It means that the next interstellar object may be nothing like Borisov or 3I Atlas's. Some may be extremely bright. Others may be completely dormant. Some may resemble asteroids. Others may resemble the most active comets ever seen. Each one will reflect its own origin story. Borisov's arrival taught astronomers that interstellar comets with fresh ices can behave nearly identically to solar system comets. 3I Atlas's arrival taught astronomers that ancient interstellar comets may be nearly invisible. Together, they provide two complementary data points, two ends of a continuum that stretches across billions of years and trillions of kilometers. Comparing Borisov and 3I Atlas reveals something else as well. Interstellar comets are common. They come from everywhere. They carry the histories of their stars, and they arrive in many forms. Borisov was a shout. 3I Atlas was a whisper. Both carry meaning. Both reveal truth. Both expand the borders of the known, and both remind us that every star in the Milky Way is connected through the wanderers it casts into the darkness. Every object that enters the solar system carries a story, but interstellar visitors, true wanderers born around other stars, carry stories written across distances and timescales far beyond anything native to our sun. They are emissaries from the wider galaxy, shaped by environments and histories that no human instrument has ever directly witnessed. Their uniqueness is not simply a matter of origin. It is a matter of identity, an identity forged in the interplay of cosmic radiation, gravitational drift, violent ejection, and the physics of cold, ancient space. To understand what makes interstellar visitors like 3I Atlas unique, we must examine not just what they are, but how they become what they are. The uniqueness begins with their birth. A typical comet in the solar system formed from a cloud of gas and dust shaped by the sun's early heat, motions, and magnetic fields. A typical asteroid formed from refractory materials that accumulated and hardened closer to the sun. But an interstellar object forms under the influence of another star, one perhaps older, younger, hotter, or cooler than the sun. It forms in a disk that might contain different ratios of dust species, a different chemistry of ices, a different level of turbulence, a different concentration of metals. Even if the basic physics is universal, the details vary from system to system. This means 3I Atlas carries within it the blueprint of a solar system never seen, a system that may have had different planet formation dynamics, a system that may have had planets unlike anything in our solar system, a system that may no longer exist, and a system whose chemical fingerprints were locked into the object the moment it froze into solidity. This alone makes interstellar objects unique. They are samples from other solar systems, delivered naturally, uninvited, unaltered by spacecraft, and untouched by the biases of human exploration. Their uniqueness deepens when they are ejected. Ejection is not gentle. It requires gravitational violence, a giant planet migrating through a disk, a chaotic encounter between multiple bodies, a close pass by another star, a destabilization driven by changing mass in a red giant phase, a catastrophic collision between worlds or planetesimals. Whatever mechanism applies, the ejection serves as a kind of cosmic birth trauma, one that imparts tremendous speed and forever separates the object from its star. This violence is not experienced by solar system comets in the same way. They form stabilized populations, Jupiter family comets, long-period comets from the Oort cloud, Halley-type comets. But interstellar comets do not. Their trajectories begin with an escape. Their lives begin with departure. Once ejected, they enter the interstellar medium, a realm where cosmic rays dominate the surface chemistry. Over time, this environment creates a unique signature. The irradiation mantle that forms on interstellar bodies is thicker, darker, and more processed than the surfaces of most solar system comets. Cosmic rays have time to burrow deeper, reshaping molecular structures and turning simple ices into complex organics. This crust becomes a defining characteristic, one that makes interstellar visitors different on first sight. Their surfaces are darker, more refractory, less reflective. Their early activity is muted. Their comas are faint. Their tails are wispy. The object appears to resist awakening, as if the weight of ages holds it in place. Even their size distribution may differ. Solar system comets shrink through repeated perihelion passages. They erode, they split, they fade. Interstellar comets, by contrast, do not undergo repeated heating cycles. Their shapes may remain closer to their primordial forms, unless damaged by collisions or radiation. Their interiors may remain pristine, even if their surfaces are altered. In the case of 3I Atlas, its subdued activity and hardened crust hinted at this exact preservation. It was a quiet relic of a noisy universe. Another defining uniqueness lies in their trajectories. Interstellar visitors follow hyperbolic paths, shapes that cannot be produced by any long-term solar system process unless an object receives an extreme gravitational boost from a giant planet. But the inbound trajectory of interstellar objects is different from such boosted paths. Their velocities relative to the Sun carry the signature of galactic motion, the orbital speed of their birth stars, and the cumulative perturbations of countless gravitational encounters. Oumuamua showed this clearly. Borisov showed it too. And 3I Atlas, with a velocity exceeding the solar system's escape speed, followed the same pattern. Their speeds are not random. They reflect the velocity dispersion of stars in the disk. This allows astronomers to classify their origin populations: thin disk, thick disk, halo. For 3I Atlas, the velocity suggested a population possibly older and more dynamically heated than the one that birthed Borisov. This means interstellar objects are also chronological markers. Their motions reveal the age of the populations from which they originate. They serve as test particles, mapping the dynamical structure of the galaxy. Another layer of uniqueness comes from the fact that they are unbound. A solar system comet, no matter how long period, is eventually tied to the Sun. It will return unless perturbed into a new state. An interstellar visitor does not return. It is a one-time phenomenon. Scientists must observe it before it exits, because once it leaves the inner solar system, it will vanish into darkness forever. This creates a sense of urgency, one that differentiates interstellar objects from all other astronomical events. If a comet disintegrates, another will take its place. If an asteroid passes by, more will follow. But interstellar objects, even if common, are individually unique. Each one offers a fleeting window into a world we can never visit. Their rarity, combined with their unrepeatability, creates a distinct category of scientific opportunity. Even the dust they carry is unique. Dust lifted from interstellar objects contains information about the mineralogy of their birth region. It may contain cosmic ray-altered compounds unseen in solar system bodies. It may contain silicates, organics, and volatiles that reflect the early chemistry of another star system. In the case of Borisov, the dust production was abundant enough to analyze directly, revealing larger grains than expected. For 3I Atlas, the dust was too faint, but even the faintness was a clue, another sign of age and irradiation. The behavior of 3I Atlas was unique in this way. It sat between Borisov's exuberance and Oumuamua's enigma. It was active but faintly. It was icy but deeply buried. It was cometary but reluctant. It was old but not inert. Its uniqueness lies in this blend. And finally, interstellar visitors are unique because they symbolize the Milky Way's interconnectedness. Every star ejects material. Every star shares its debris with the galaxy. Every system contributes to the population of wanderers. Every fragment drifting between stars carries a message from its home, a message written in chemistry and physics. 3I Atlas was one such message, a fragment from another world, a wanderer shaped by cosmic forces, a visitor that revealed in its faint glow the story of a star system long gone or far away. This is what makes interstellar visitors unique, not their rarity, not their speed, not their strangeness, but the fact that each one carries the memory of places we cannot reach and delivers it into the light of our sun for a brief, precious moment. From the moment astronomers calculated the trajectory of 3I Atlas, they knew it was interstellar. Its hyperbolic orbit, its excess velocity, its inbound direction all pointed to a journey that began far outside the reach of the sun. But knowing that a visitor is interstellar is not the same as knowing where it came from. To answer that question, even partially, astronomers attempt something extraordinary: reconstructing the object's path backward through the galaxy. This task is more difficult than tracing the orbit of any solar system object. Within the solar system, gravitational influences are predictable. The sun's mass dominates. Planetary interactions are calculable. Perturbations are manageable. But once an object leaves the solar system, the galaxy becomes the governing force, and the galaxy is a complex, dynamic, living environment. To reconstruct the path of 3I Atlas, astronomers begin with its inbound velocity. Its speed relative to the sun reveals how fast it must have been traveling long before it entered the heliosphere. This speed is then corrected for the sun's own motion around the Milky Way. Everything in the galaxy moves. The sun orbits the center of the galaxy every 225 to 250 million years. Nearby stars drift in their own orbits. Gas clouds flow. Spiral arms shift. To understand where an object came from, astronomers must transform its trajectory from the solar system-centric view into the galactic frame. Once in the galactic frame, the path becomes clearer, but not clearer in the sense of identifiable origins, clearer in the sense of general population. The object's velocity suggests whether it belongs to the thin disk, thick disk, or halo populations. Each group has characteristic speeds relative to the local standard of rest. 3I Atlas showed a velocity consistent with the disk populations, possibly leaning toward the thick disk, which contains older stars with higher velocity dispersions. But reconstructing the past requires more than classification. It requires integrating backward through the galactic gravitational potential, a mathematical model describing how all mass in the galaxy shapes motion. This includes not just visible stars, but also dark matter, which dominates the mass of the galaxy. Astronomers simulate the object's path backward by stepping through time, recalculating its position and velocity under the influence of gravity. But this is where the challenges begin. The farther back in time one goes, the more uncertain the path becomes. This uncertainty arises from several sources. First, small uncertainties in current position and velocity grow exponentially with time. A tiny error in measurement becomes significant after millions of years. After tens or hundreds of millions, the uncertainty grows so large that the reconstructed path becomes more of a probability cloud than a line. Second, the galaxy is chaotic on long time scales. Stars move, clusters dissolve, gas clouds drift, spiral arms shift their position. The gravitational landscape of the galaxy now is not what it was tens millions of years ago. Reconstructing a path must account for all of these changes, but many are unknown or modeled with large uncertainties. Third, close encounters matter. If 3I Atlas passed near a star in the past, a flyby at even a fraction of a light year, it could have altered its trajectory dramatically. If astronomers do not know that the star was present at the right place and time, they cannot account for the encounter. Many such encounters go unrecognized due to incomplete stellar catalogs. Even with Gaia's revolution in astrometry, not every star's past motion can be traced accurately. These problems compound. As a result, after only a few million years, the reconstructed paths diverge into a wide range of possibilities. Yet, despite these challenges, astronomers can still learn a great deal. The reconstructed trajectories of 3I Atlas do not converge on a single star, but they converge on a general region of galactic phase space, the disk populations. This implies the object was born in the galactic disk, not in the halo or bulge. Its velocity suggests it was not recently ejected. It is not racing at extreme speeds. Instead, its speed aligns with the general motion of stars in the disk. This means its path, though uncertain in detail, is consistent with a long-duration drift through the galactic disk. It was not hurled at high speed from a recent supernova. It was not accelerated by extreme gravitational interactions. It simply drifted, shaped by the galaxy's tides, perturbed occasionally by passing stars, and slowly modified by the spiral gravitational pattern. Another insight comes from the object's inbound direction. 3I Atlas approached the solar system from a region of the sky that is not strongly associated with any known stellar nursery or star cluster. This suggests that its ejection did not occur recently. Instead, it was ejected long ago and has since moved far from its birthplace. Reconstructing the path also allows astronomers to ask a different question. Which stars did 3I Atlas pass near during its journey? By simulating backward motion and comparing it to the reconstructed past motions of nearby stars, astronomers look for close encounters, situations where the object and a star came within a few light years of one another. Any such encounter could have altered the object's trajectory. But even more importantly, if the object passed close to a star long ago, that star becomes a candidate for its birthplace. The results for 3I Atlas revealed no compelling candidates. This is not surprising. The galaxy is vast. The object may have been ejected billions of years ago. The star it originated from might have moved far from its birth location. It may now be a white dwarf. It may have merged. It may have migrated across the disk. The system that produced 3I Atlas could be unrecognizable. But the absence of a clear origin does not diminish the achievement of reconstructing the path. Instead, it highlights the nature of interstellar travel. These objects do not merely cross space, they cross time. A comet like 3I Atlas is a traveler from an era whose details are lost in the noise of galactic history. Reconstructing its path is an attempt to reach back into that lost era, not to pinpoint a single star, but to understand the type of environment that shaped its journey. And the reconstruction reveals that 3I Atlas belonged to the galactic disk. It drifted as part of the population of objects shaped by spiral structure, influenced by the galaxy's gravitational tides, and sculpted by countless weak perturbations. Its path cannot be traced to a single star. Its past cannot be reconstructed in detail. But its broad origin can be understood. And that origin lies in the galactic plane, among the stars that make up the great rotating structure of the Milky Way. This is the true meaning of reconstructing a path through the galaxy, not solving a mystery fully, but narrowing it, not finding a birthplace, but understanding a heritage, not identifying a star, but identifying a population. 3I Atlas is a child of the disk, an ancient traveler shaped by forces that affect all stars in the Milky Way. Its path is the path of the galaxy itself. When an interstellar object wanders through the galaxy, its journey is not simply a straight line carved through emptiness. It is a weaving path shaped by the distribution of stars, some close, some distant, some massive, some faint, some long gone, some newly formed. The galaxy is a motion-filled tapestry, and every wandering object moves through it like a thread drawn through a shifting pattern. For 3I Atlas, that journey likely included numerous close encounters with stars, encounters that altered its trajectory slightly and added new layers of gravitational memory. Although the exact path of 3I Atlas cannot be known, astronomers can estimate the kinds of stars it might have passed near and what those encounters would have meant. Stars in the Milky Way do not sit still. They move in orbits that loop and curve around the galactic center. They oscillate above and below the galactic plane. They drift apart from their birth clusters. They migrate through spiral arms. And they influence one another through gravitational forces, no matter how faint those forces may be. Over millions or billions of years, an interstellar object like 3I Atlas moves through neighborhoods of stars whose identities change with time. At one moment, it might pass near a red dwarf. At another, it might drift through a region dominated by G-type stars like the Sun. Later still, it may find itself skirting the edges of a dying giant, or passing quietly beneath the glare of a young, hot blue star. The diversity of these encounters shapes its long-term journey. The stars it might have passed by fall into several broad categories. The first are the faint dwarf stars, the most common type in the galaxy. Red dwarfs, small and dim, make up nearly 3/4 of all stars. Their gravitational pull is weak compared to larger stars, but their ubiquity means that interstellar objects pass near them often. A close encounter with a red dwarf might alter the trajectory of 3I Atlas only slightly, but the cumulative effect of many such encounters over billions of years becomes significant. Some red dwarfs flare violently, especially when young. If 3I Atlas passed near one during a flare, it might have experienced a brief but intense burst of radiation. Not enough to alter its course meaningfully, but enough to add a tiny layer of surface processing. These flares, rich in ultraviolet and X-ray energy, could have transformed molecules on its surface, forming new radicals and organic residues. The second category includes sun-like stars, yellow dwarfs, orange dwarfs, and other medium-sized stars. These stars exert stronger gravitational forces. A passage within a few light years of such a star could measurably alter the object's trajectory. If 3I Atlas passed near a star similar to the Sun long ago, that encounter may have changed its course in ways that made it impossible to identify its original home system. Some of these stars would have planetary systems of their own. 3I Atlas might have passed through the outer reaches of such systems, skimming past comet clouds or Oort cloud equivalents. If it had passed close enough, it might even have interacted gravitationally with those systems, though likely too faintly to be detected or remembered in its present orbit. The third category includes massive stars, blue giants, white-hot O-type and B-type stars, or large A-type stars with strong radiation fields. These stars are bright, short-lived, and rare, but they wield immense influence. A passage near such a star could have exposed the object to intense ultraviolet radiation, or heated its surface briefly. Though these stars are not long-lived, their radiation fields shape regions around them for significant distances. If 3I Atlas ever passed near such a star, even at large distances, its surface might have been subtly altered. The volatile ices deeper within would remain unaffected, but the crust might bear the imprint of exposure to a particularly energetic environment. Another category includes white dwarfs, the remnants of stars that have already lived their full lives. White dwarfs, small and dense, produce strong gravitational fields for their size. A close encounter with a white dwarf could significantly perturb an interstellar object. These encounters are rare, but over billions of years, not impossible. If 3I Atlas passed near a white dwarf, that event might have been a key gravitational turning point, one that redirected it toward the region of space where it eventually encountered our Sun. Finally, there are the encounters with other interstellar objects, silent, invisible, statistically improbable, but possible. The galaxy is filled with trillions of such objects. Though the density is low enough that collisions are exceedingly rare, close passes are inevitable over cosmological timescales. These encounters would have no noticeable effect on the object's trajectory in most cases, but they add to the poetic understanding of its journey, a wanderer among wanderers. Each stellar encounter, whether with a dwarf, a giant, a white dwarf, or simply a region of higher or lower stellar density, shaped the trajectory of 3I Atlas in small ways. But how close did it come to these stars? How near did it pass? Even a distance of 1 light-year is close in astronomical terms. A pass within a few light-years of a star could alter the object's direction by a measurable amount. A pass within a fraction of a light-year could dramatically redirect it. The likelihood of such encounters depends on the density of stars in the region of the galaxy it drifted through. If 3I Atlas came from the thick disk, it may have passed through regions where stars were older, more widely dispersed, but occasionally clustered. If it came from the thin disk, its path might have taken it through spiral arms rich in star-forming activity. Reconstructing these encounters is essentially impossible for specific stars, yet the statistical likelihood of many encounters is certain. Over millions of years, the object passed near hundreds or thousands of stars. Over billions of years, it may have passed near millions. These encounters helped shape its present trajectory, and they erased the traces of its origin. Each nudge shifted its path slightly. Each gravitational pull widened the uncertainty. Each stellar migration disrupted the ability to trace its journey backward. In this way, the stars it passed by are both contributors to its story and authors of its secrecy. They guided it forward while hiding its origins behind layers of dynamic complexity. And now, having passed so many unknown stars, it has passed ours. For a brief moment, it became part of the story of our Sun. And like the stars it passed before, we too have nudged it, not physically, but by measuring it, understanding it, and adding its journey to our growing map of the galaxy's wandering objects. Then, like all the others before us, we will fade out of its story as it moves onward. Trying to determine where an interstellar object comes from is like trying to determine which river carved a particular stone after it has been carried by 1,000 currents. The stone's shape offers clues, but not answers. Its chemical makeup tells you something about where it might have formed, but the details blur with time, and the path it took cannot be retraced once the currents have mixed. This is the reality astronomers face when trying to understand the origin of 3I Atlas. Its hyperbolic trajectory tells us it came from beyond the solar system. Its velocity suggests it belongs to the galactic disk, perhaps the thin disk, perhaps the thick disk. Its behavior suggests it has been wandering for a long time, accumulating the scars of cosmic radiation. Its faint coma reveals that it still carries ancient ices. But these clues, taken together, do not point to a single birthplace. Instead, they point to a galaxy of possible origins. The Milky Way is vast. It contains more than 200 billion stars, each with its own story of formation, evolution, and destruction. Each star has the potential to form planets. Each planetary system has the potential to eject material. These ejections create trillions upon trillions of small bodies drifting through the galaxy. Each one has its own trajectory, its own history, its own chemical identity. In this context, the origin of 3I Atlas could lie almost anywhere, but astronomers can narrow down some possibilities. One plausible origin is a young star-forming region. Regions like the Orion Nebula produce stars rapidly and eject material frequently. Giant planets form, migrate, and destabilize their disks. Ejections are common. But if 3I Atlas came from such a region, it would likely still contain fresh, unprocessed ices. Its crust would be less hardened. Its activity would be higher. This makes a young origin less likely. Another possibility is a mature planetary system in the thin disk. In such systems, gravitational interactions between planets can still eject comets long after the system forms. For example, our own Jupiter continues to eject objects today. If 3I Atlas came from such a system, it might have been ejected within the last few 100 million years. Its surface would show moderate radiation processing. Its coma would be faint but detectable. This possibility aligns with some of the object's observed characteristics. But the most intriguing possibility, the one consistent with its faint activity, hardened crust, and velocity, is that 3I Atlas originated in the thick disk, among the oldest stars in the galaxy. If so, the object might be older than the solar system. It might have formed around a star that lived and died long before humans existed. It might be a remnant from a planetary system shaped in the early days of the Milky Way, when metallicities were lower and turbulence was higher. It might be one of the oldest intact fragments of a world ever observed by humanity. This possibility does not imply that the object was ejected billions of years ago and drifted unchanged ever since. The galaxy has evolved dramatically over that time. The thick disk stars have migrated, spiral arms have shifted, gas clouds have dispersed. Regions once dense are now diffuse. But a small icy body can persist through all of this, carried by the galactic currents like a leaf caught in a slow-motion wind. Another possibility is that 3I Atlas came from a binary star system. Binary systems are efficient at ejecting small bodies. The gravitational interplay between two stars can destabilize orbits, sending objects into interstellar space. The characteristics of the crust and volatiles do not distinguish between single and binary star origins, but the dynamics of ejection remain consistent. There is also the possibility that 3I Atlas came from a system that has since been destroyed. A star could have undergone significant evolution, becoming a red giant, then shedding its outer layers, then collapsing into a white dwarf. During these phases, planetary systems can be dismantled. Comets can be thrown outward, material can drift into space. If 3I Atlas came from such a system, its existence today is a testament to a world that no longer exists. Another possibility is even more ancient, that it came from a first-generation cluster long since dissolved. Star clusters form hundreds or thousands of stars at a time. These clusters disperse over hundreds of millions of years, scattering their stars across the disk. Any ejected bodies from such clusters would now be indistinguishable from the general population. 3I Atlas could be one such wanderer. Ultimately, the galaxy is full of possible origins. Its trajectory cannot be traced to a single location. Its chemical signature cannot identify one specific star. Its age cannot be determined precisely. And yet, these uncertainties are not weaknesses of scientific understanding. They are reminders of the vastness of the Milky Way. They are reflections of the dynamic, restless, evolving nature of the galaxy. They are evidence that even the smallest object can witness the entire history of a cosmic neighborhood. When astronomers say that 3I Atlas has a galaxy of possible origins, they are not using metaphorical language. They are speaking literally. The Milky Way is its homeland. The stars are its distant relatives. The spiral arms are its childhood terrain. The interstellar medium is its long road. And like all wanderers, it carries the essence of its beginnings even when the details are lost. We may never know the exact star that gave birth to 3I Atlas, but we know the kind of environment it came from. We know the forces that shaped it. We know the history that hardened its crust. We know the cosmic radiation that carved its surface. We know the galactic tides that nudged it forward. We know enough to place it in context, enough to understand that it is not just a visitor, but a messenger from a galaxy filled with stories. 3I Atlas came from somewhere among the billions of stars, somewhere among systems long gone or still shining, somewhere in a galaxy of possible origins, and that is enough to make its presence extraordinary. Before an interstellar object becomes a wanderer between the stars, it must undergo an event powerful enough to expel it from the gravitational grip of its home system. This moment, the moment of ejection, is not gentle. It is violent, chaotic, and born of a type of gravitational drama that plays out in planetary systems across the galaxy. For 3I Atlas, this event likely occurred billions of years ago, long before the Sun even formed, in a system where the young planets were still shifting into their final configurations. To understand how such an ejection happens, one must study the physics of gravitational scattering. In any planetary system, planets interact with the small bodies that orbit their star. These small bodies, comets, asteroids, icy planetesimals, are relics of the disk from which the system formed. As the planets migrate, or as they settle into resonances, or as they undergo instabilities, they scatter these smaller objects. Some are pushed inward toward the star. Some collide with planets. Some are trapped in stable belts. And some are ejected outward with increasing speed. For ejection to occur, the small body must gain enough kinetic energy through repeated gravitational interactions to exceed the escape velocity of the entire system. This escape velocity depends on the mass of the star and the distribution of the planets. A more massive star requires higher speeds to escape. A system with many giant planets can impart more energy to small bodies. A system with chaotic dynamical behavior can produce dramatic ejections. One of the most efficient mechanisms is planetary scattering caused by giant planets. When a small icy body passes near a giant planet, one similar to Jupiter or Saturn, the gravitational pull can dramatically alter its orbit. If the object approaches from the right direction and velocity, the encounter can slingshot it outward. Each encounter changes its speed. If the encounters continue, the object gradually moves onto wider and wider orbits. Eventually, one final encounter can fling it past the outer boundary of the system. Once the object exceeds escape velocity, the star's gravity can no longer hold it. The object becomes unbound. Another mechanism is planet migration. In the early stages of planetary system evolution, giant planets often migrate through the disk. This migration is driven by interactions with the gas disk or with smaller bodies. As a giant planet moves, it destabilizes the orbits of many smaller objects. Some are pulled along, some are scattered inward, and many are cast outward with enough energy to leave the system entirely. This is likely how many of the solar system's own Oort cloud objects formed. Jupiter and Saturn tossed them outward over millions of years. Some remained loosely bound, but many others may have escaped completely, becoming interstellar wanderers themselves. Another mechanism involves binary star systems. In systems with two stars, gravitational forces are far more complex. A small body orbiting one star may be perturbed by the companion. If the binary orbit is eccentric, these perturbations can be intense. The small body may be pushed inward, outward, or even ejected entirely. Binary interactions are efficient ejectors. Many interstellar objects may come from such systems. If 3I Atlas originated in a binary system, its ejection would have been particularly dramatic, driven by the dance of two suns whose gravitational tides tugged the object until it broke free. Star clusters add another layer of possibility. Stars typically form in clusters, dense environments where many young stars crowd together. These clusters dissolve over time, but while they exist, the gravitational interactions are frequent and powerful. An object orbiting one star might feel the pull of another passing nearby. These close encounters can destabilize planetary systems. Comets can be stripped away. Planetesimals can be ejected. If 3I Atlas formed in such an early, crowded environment, its ejection may have been influenced not by planets, but by another star passing close by. A particularly dramatic ejection can occur during late stellar evolution. When a star swells into a red giant, it loses mass rapidly. This mass loss weakens its gravitational grip on its planets and belts. Comets once held in distant orbits can drift outward. Some escape the system altogether. When the star shrinks into a white dwarf, more material can be destabilized. Though this scenario is less likely for objects like 3I Atlas, because their surfaces are too well preserved to have endured close proximity to a dying star, it remains a theoretical possibility. Regardless of the mechanism, the physics of ejection imparts three essential characteristics to an interstellar object. First, it gives it a specific velocity relative to its parent star. This initial velocity becomes part of its long-term galactic motion. Combined with the star's own orbit around the galaxy, the object takes on a complex path through interstellar space. Second, it sends the object into the galaxy unprotected. Once unbound, there is no atmosphere, no magnetosphere, no planetary shield. The object becomes exposed to cosmic rays, interstellar dust, ultraviolet radiation, and occasional shocks from passing supernova remnants. These conditions shape its surface and chemistry. Third, it gives the object a kind of autonomy. No longer tied to its star, it drifts through the galaxy, interacting primarily with the gravitational forces of the Milky Way itself. Its fate becomes a function of the galaxy, not its birthplace. This transformation from bounded material to free-floating messenger is profound. The moment of ejection becomes the defining event of its existence. It marks the transition from being part of a system to being part of the galaxy. It sets the stage for billions of years of wandering. It defines the object's future trajectory. And it creates the conditions through which it eventually enters another star's influence. 3I Atlas was one such object, ejected long ago, hardened by time, drifting until chance brought it near our sun. Its ejection was the opening act of its long story, a story that eventually became part of ours. After an interstellar object is ejected from its home system, the truly long part of its journey begins, a voyage through the vast, cold reaches of the interstellar medium, where distances stretch across light years and time passes in spans too large for human imagination. This phase of the journey is the quietest, yet the most transformative. It is a period of immense duration during which the object is sculpted not by violent events, but by the patient, unyielding forces of cosmic radiation, gravitational tides, and the subtle winds of the galaxy. For 3I Atlas, this slow drift through space may have lasted longer than the entire history of life on Earth. The interstellar medium is not empty. It is thin, so thin that it contains fewer than a handful of atoms per cubic centimeter, but it is not void. It contains clouds of gas, regions of warm and hot plasma, filaments of dust, and vast magnetic structures. These components interact with any small body moving through them. The most significant influence is cosmic radiation. Cosmic rays, high-energy particles accelerated by supernovae, quasars, magnetars, and other energetic phenomena, strike the surface of interstellar objects continuously. Each particle carries enough energy to break molecular bonds. Over millions of years, these impacts create a thick, carbon-rich crust on the surface. This crust darkens the object, reducing its reflectivity. It hardens the outer layers, turning them into a resin-like armor that seals in the ices beneath. This is why interstellar objects like 3I Atlas appear so dark and inactive compared to young comets in our solar system. Their surfaces have been bombarded for ages without replenishment. Cosmic ray processing also changes the chemical composition of the surface. Simple molecules break apart. Radicals form and recombine. Complex organics develop within the crust. These organic molecules can create a reddish tint observed in many irradiated bodies. But cosmic rays do not penetrate deeply. Even after billions of years, only the uppermost layers are altered. Beneath the crust, the interior remains cold and pristine, preserving the original chemistry of the object's birthplace. The temperature of interstellar space also plays a role. Far from any star, an object finds itself immersed in a thermal environment close to absolute zero. In such cold conditions, ices become rigid. Molecules barely move. Any trapped gases remain locked within the matrix of the ice. This deep freeze preserves the object through eons, preventing sublimation and preventing chemical reactions except those caused by radiation. This stability is why the volatiles within 3I Atlas have survived for so long. The object also moves through gravitational landscapes. The Milky Way's disk is not uniform. Its gravitational potential varies depending on the distribution of stars, gas, and dark matter. These variations create galactic tides, gentle gradients that tug on the object as it moves. These tides do not change the object's speed dramatically, but they do alter its direction over long periods. The slow passage above and below the galactic plane is part of this effect. Objects oscillate around the midline of the galaxy, rising and falling in a cycle that takes tens of millions of years. These oscillations expose them to different environments: dense regions during spiral arm crossings, sparse regions between arms, dust-rich clouds, radiation-heavy areas, and magnetic filaments. Each region leaves a subtle imprint on the object's surface, changing its coloration, its chemistry, or its temperature. The object also experiences occasional close encounters with stars. While these encounters are rare, they are statistically inevitable over billions of years. A star passing within a light year or two exerts a gravitational influence strong enough to alter the object's path. Most encounters are mild. A few may be significant. Each encounter adds to the gradual drift of the object through the galaxy, turning its path into a meandering trajectory influenced by both local forces and the general galactic potential. Some encounters may have been particularly dramatic. The object might have skirted the outskirts of a stellar nursery. It may have passed near a young cluster with high radiation. It may have drifted through a region bathed in the relic glow of a supernova remnant. It may have crossed a spiral arm filled with star formation. Each region reshaped its environment slightly, but slowly, subtly over countless cycles. The interstellar medium also contains dust grains, microscopic particles that occasionally collide with drifting bodies. These collisions are infrequent, but over millions of years, they create tiny pits on the surface. These pits become part of the texture of the irradiation crust. Because interstellar objects do not orbit stars repeatedly, they are spared the thermal stresses that reshape solar system comets. They do not develop fresh surfaces. They do not outgas frequently. Their surfaces grow older, darker, and more complex with time. Meanwhile, their interiors remain unchanged, protected by the very crust that isolates them. This is what makes interstellar objects both ancient and pristine. Their surfaces tell the story of their interstellar journey. Their interiors tell the story of their birthplace. As 3I Atlas drifted through the galaxy, it experienced billions of years of isolation, broken only by the gentle pressures of cosmic forces. It drifted through the outer arms, moved inward toward the midplane, glided through regions of higher stellar density, and then drifted back outward. It passed millions of stars without ever coming close enough to melt, fracture, or disintegrate. It became a cosmic fossil, a fragment of a system long forgotten, a silent traveler that saw the galaxy evolve around it, a relic carried slowly through the dark ocean of interstellar space. And then, by chance, by the alignment of gravity, distance, and time, it crossed a region of space occupied by our Sun. For the first time in ages, it encountered a warm star. For the first time in ages, it became visible. The slow drift through interstellar space ended in a moment of illumination. The darkness that had preserved it yielded to sunlight. And because of that, we were able to witness it. Briefly, faintly, but meaningfully. The slow drift that lasted billions of years led to a fleeting encounter that lasted only weeks. Yet in that encounter lies the value of its entire journey. Every star in the galaxy, no matter how small or unassuming, carries with it a sphere of influence. This influence extends far beyond the reach of its visible light. It stretches across space, through gravity, winds, radiation, and motion. Even a small red dwarf shapes the region around it. Even a dim brown dwarf exerts gravitational tides. Even a dying star, reduced to a white dwarf ember, affects the motion of dust, comets, and debris that drift near it. To understand how an object like 3I/Atlas journeys through the galaxy, one must understand the influence of these stars, not individually, but collectively. Each one contributes to the environment through which interstellar objects drift. Over millions or billions of years, these influences accumulate, altering the direction, speed, and surface of a wandering body. Stars shape their surroundings through several distinct mechanisms. The first and most fundamental is gravity. Gravity is the universal architect of motion. It binds planets to stars, stars to galaxies, galaxies to clusters. It curves space, influences time, and shapes trajectories. For an interstellar object, gravity determines not only how it leaves its home system, but also how it moves through the galaxy afterward. Each star produces a gravitational well, a region where objects feel its pull. When 3I Atlas drifted through the galaxy, it moved past the edges of many such wells. Even distant stars exerted forces on it. These forces were weak, but over long time scales, they contributed to subtle adjustments in direction. A star passing within a few light years might have nudged the object slightly. A closer encounter might have produced a more dramatic deviation. The galaxy is a constantly shifting sea of gravitational wells, and interstellar objects are like driftwood floating among them. The second influence comes from stellar winds. Every star emits a stream of charged particles, electrons, protons, and ions from its outer layers. These winds fill the space around the star, forming a bubble of influence. The Sun's bubble is the heliosphere. Other stars produce their own equivalents, astrospheres. Some are small and faint, barely extending a fraction of a light year. Others, especially those from young, active stars, can stretch much farther. When an interstellar object passes through such a region, the stellar wind interacts with its surface. It may strip dust grains. It may erode the outer layers. It may change the electrical charge of particles embedded within the crust. These effects are faint, but over millions of years, they contribute to the chemical and structural evolution of the object. The third influence is radiation. Starlight travels vast distances. For most interstellar objects, this light is too faint to produce significant heating, but it can still produce chemical reactions on the surface. Ultraviolet radiation, even when diluted across light years, is capable of breaking molecular bonds. This leads to the formation of new radicals and contributes to the thickening of the irradiation crust. Stars also emit more energetic radiation, X-rays, gamma rays, especially during flares or throughout their youth. A young red dwarf, for example, may produce violent flares that blast radiation far into space. If 3I Atlas ever passed near such a star, its crust would have been altered by these bursts. Even though such events are rare, their cumulative effects shape the properties of interstellar objects. The fourth influence is magnetic fields. Stars generate magnetic fields that extend into space. These fields shape the behavior of charged particles in the stellar wind. They create magnetic turbulence. They guide cosmic rays. They influence the region through which dust and gas flow. For an interstellar object, magnetic fields determine how charged particles interact with its surface and how radiation affects it. While magnetic fields do not alter the trajectory directly, since the object is not charged, they help determine the environment that processes its surface. The fifth influence is stellar motion. Stars do not stay in one place. They orbit the galaxy. They drift relative to one another. They participate in spiral arm dynamics. Some move quickly, others slowly. Some cluster, others scatter. This motion determines how often interstellar objects encounter different stellar environments. For 3I Atlas, this motion was a fundamental part of its long journey. It may have been ejected when its parent star was in a different region of the galaxy. It may have drifted through multiple spiral arms as the galaxy rotated. The star that once hosted it may now be thousands of light years away. The places it passed through may no longer exist in the same form. Stars shape the space around them, but they also change positions, dragging their spheres of influence across the galaxy. The sixth influence comes from star clusters. Clusters are regions of especially strong gravitational and radiation fields. When 3I Atlas drifted through such a region, it would have experienced a higher density of stellar encounters. In these environments, the probability of a close encounter increases dramatically. A brush with a passing star could alter its path substantially. If the object ever passed through a dissolving cluster, it might have experienced gravitational turbulence more intense than anything it encountered in the broader disk. The seventh influence involves stellar evolution. Stars change over time. They swell into giants. They shed mass. They produce planetary nebula. They collapse into white dwarfs. They explode as supernovae. Each phase affects the surrounding region differently. A supernova, for example, sends shock waves and cosmic rays far into interstellar space. If 3I Atlas ever encountered such a shock, it might have experienced a sudden increase in radiation. This could alter its surface chemistry dramatically. A red giant shedding mass creates a flow of gas moving outward, which can disturb nearby objects. A white dwarf's gravity is strong enough to perturb nearby debris. Interstellar objects are witnesses to these stellar transformations. They drift through environments created not by one star, but by many. The eighth influence is the galactic tide itself, an indirect effect of the distribution of stars. The gravitational pull of the galaxy affects stars, which in turn affects the small objects around them. As stars move in response to the larger galactic field, they drag their gravitational zones with them. The positions of stars shift relative to the object. This shifting environment influences the object through an interconnected web of forces. For 3I Atlas, the accumulated influence of these stellar forces shaped its path. its surface, and its long-term evolution. Every star it passed, whether near or far, left some imprint, even if only a slight gravitational nudge. Some stars reshaped its trajectory. Some contributed to the chemical processing of its crust. Some created environments of enhanced radiation. Some moved past it without noticeable effect, but still added to the statistical shaping of its path. By the time 3I Atlas reached the solar system, it had been influenced by hundreds, thousands, perhaps millions of stars, each playing a role in the quiet choreography of its long journey. The stars shaped its surroundings, the galaxy shaped its story, and the object itself carried those influences to us, encoded in its structure, its chemistry, and its path. Cosmic radiation is one of the most relentless forces in the universe. It is silent, invisible, and everywhere. There is no shielding in interstellar space, no atmosphere to absorb the impact, no magnetic field to deflect the particles. Interstellar objects like 3I Atlas journey through this radiation for millions or billions of years, accumulating the scars of this constant bombardment. To understand the appearance and behavior of an interstellar object, one must understand cosmic radiation and how it processes the surface of such a traveler. Cosmic radiation is composed of high-energy particles, mostly protons, but also heavier nuclei, electrons, and various exotic fragments created in extreme astrophysical environments. These particles travel at nearly the speed of light. They are launched from supernova explosions, active galactic nuclei, neutron star collisions, and the turbulent magnetic fields of the galaxy. When such particles strike the surface of an interstellar object, they do not bounce off. They penetrate. They knock atoms out of place. They break molecular bonds. They generate radicals. They rearrange chemical structures. They embed themselves in the crust, leaving tracks of damage. The result is a surface that becomes darker, redder, harder, and chemically altered over time. For 3I Atlas, cosmic radiation was a dominant sculptor of its outer layers. It is likely that the first few centimeters to meters of the object's surface have been processed extensively. The crust that forms through this process is often called an irradiation mantle, a layer of material rich in complex organics created through radiation chemistry. These organics can include hydrocarbons, carbonaceous chains, nitrogen-bearing molecules, and polycyclic aromatic compounds. The color of this mantle, often a deep red or brown, is a direct product of cosmic ray processing. Many objects in the Kuiper belt show similar coloration, but interstellar objects show even more extreme versions because they have been exposed for far longer. Cosmic radiation also seals the surface. When high-energy particles strike ices like water, carbon monoxide, methane, or nitrogen, they break them apart. The fragments reorganize into more complex molecules. Over time, these new molecules create a layer that is less volatile than the original ices. This layer becomes a barrier, preventing deeper ices from sublimating unless cracks form. This is why 3I Atlas remained faint and only mildly active. Its crust suppressed sublimation. The interior remained locked behind a surface shaped by cosmic time. Radiation also creates porosity. The impacts create tiny voids and defects. These voids trap gases created by deeper reactions. Over time, as the object warms near a star, these gases can escape, producing faint coma. This mechanism explains the behavior of 3I Atlas. Its activity was not absent, but it was reluctant, subtle, driven by gases that escaped only through microscopic pathways. Cosmic radiation does more than transform chemistry. It changes the physical structure of dust grains on the surface. It increases brittleness. It alters reflectivity. It may even weaken the cohesion of certain crystalline structures. Photons contribute as well. Ultraviolet radiation from stars and from the diffuse interstellar field breaks molecular bonds, especially near the surface. X-rays and gamma rays, though rarer, penetrate deeper, creating ionization cascades that alter subsurface chemistry. These layers of radiation exposure tell a chronological story. The outermost layer records the most recent radiation exposure. Layers beneath record earlier periods. Deeper still, untouched by radiation, lie the original ices and materials from its birth system. If a mission someday retrieved a sample from an interstellar object, the layers could be peeled back like pages of a cosmic diary. Another effect of cosmic radiation is the production of isotopic anomalies. Certain isotopes form or break down under radiation. These isotopes could provide clues about the environment the object moved through. For example, cosmic ray spallation can produce isotopes of helium, neon, and hydrogen. Their abundance would reveal the intensity and duration of exposure. For 3I Atlas, these isotopic signatures remain hidden. No mission sampled it. No spectrum recorded its interior chemistry. But the faintness of its coma, combined with its dark surface, already tells astronomers that its irradiation mantle was thick and ancient. This mantle also helps distinguish interstellar objects from solar system bodies. Solar system comets that reside in the Oort cloud also experience cosmic radiation, but for less time. Interstellar objects experience it for longer and without the occasional resurfacing caused by perihelion passages. The difference is cumulative and visible. Interstellar objects show extreme reddening, deep dark coatings, and unusual activity patterns. Cosmic radiation also influences the object's thermal properties. The crust becomes less conductive. Heat does not penetrate easily. This means the interior stays cold even when the surface warms. For 3I Atlas, cosmic radiation was a dominant sculptor of its outer layers. It is likely that the first few centimeters to meters of the object's surface have been processed extensively. The crust that forms through this process is often called an irradiation mantle, a layer of material rich in complex organics created through radiation chemistry. These organics can include hydrocarbons, carbonaceous chains, nitrogen-bearing molecules, and polycyclic aromatic compounds. The color of this mantle, often a deep red or brown, is a direct product of cosmic ray processing. Many objects in the Kuiper belt show similar coloration, but interstellar objects show even more extreme versions because they have been exposed for far longer. Cosmic radiation also seals the surface. When high-energy particles strike ices like water, carbon monoxide, methane, or nitrogen, they break them apart. The fragments reorganize into more complex molecules. Over time, these new molecules create a layer that is less volatile than the original ices. This layer becomes a barrier, preventing deeper ices from sublimating unless cracks form. This is why 3I Atlas remained faint and only mildly active. Its crust suppressed sublimation. The interior remained locked behind a surface shaped by cosmic time. Radiation also creates porosity. The impacts create tiny voids and defects. These voids trap gases created by deeper reactions. Over time, as the object warms near a star, these gases can escape, producing faint comas. This mechanism explains the behavior of 3I Atlas. Its activity was not absent, but it was reluctant, subtle, driven by gases that escaped only through microscopic pathways. Cosmic radiation does more than transform chemistry. It changes the physical structure of dust grains on the surface. It increases brittleness. It alters reflectivity. It may even weaken the cohesion of certain crystalline structures. Photons contribute as well. Ultraviolet radiation from stars and from the diffuse interstellar field breaks molecular bonds, especially near the surface. X-rays and gamma rays, though rarer, penetrate deeper, creating ionization cascades that alter subsurface chemistry. These layers of radiation exposure tell a chronological story. The outermost layer records the most recent radiation exposure. Layers beneath record earlier periods. Deeper still, untouched by radiation, lie the original ices and materials from its birth system. If a mission someday retrieved a sample from an interstellar object, the layers could be peeled back like pages of a cosmic diary. Another effect of cosmic radiation is the production of isotopic anomalies. When the object approaches a star, the heat is absorbed primarily at the surface. Deeper layers remain insulated. This thermal behavior partially explains why 3I Atlas did not erupt into bright activity. It simply could not warm quickly enough. Radiation also affects rotation. Impacts from cosmic particles produce negligible momentum individually. But over billions of years, asymmetrical erosion caused by radiation can produce slight changes in shape, which in turn affect rotational dynamics. This may have contributed to the irregular rotation of some interstellar objects. Finally, cosmic radiation acts as a universal equalizer. Objects born in different solar systems with different compositions and histories end up acquiring similar outer layers when exposed to the interstellar environment. This means that interstellar objects, regardless of origin, often resemble one another superficially. It is only when they warm near a star that their differences re-emerge. 3I Atlas carried all these marks. Its dark surface was the product of eons. Its faint activity reflected an interior struggling to break through the crust. Its chemistry was likely altered in ways that distinguishes it from younger comets. And yet, beneath that hardened exterior, its core remained pristine, a frozen relic from a long-vanished world. Cosmic radiation shaped it, but it did not erase its story. It merely preserved it in a darker, quieter form until sunlight revealed it once more. To understand an interstellar object like 3I Atlas, one must understand the geometry of its path, the shape carved across space by its motion through the solar system. Unlike the comets and asteroids that orbit the Sun on ellipses, returning again and again in predictable cycles, an interstellar object follows a different kind of curve. Its journey is defined by a hyperbola, a shape that tells a story of speed, freedom, and an origin far beyond the domain of a single star. A hyperbolic orbit is not subtle. It is a bold declaration that an object does not belong to the solar system. It is the mathematical signature of escape. To travel on a hyperbolic path, an object must possess a velocity exceeding the escape velocity of the Sun. Anything slower is bound. Anything faster is free. When astronomers first calculated the orbit of 3I Atlas, the numbers were clear. Its inbound velocity was too high to be explained by any solar system process. No planetary encounter could have accelerated it enough without causing catastrophic disruption. No gravitational slingshot could account for its speed and direction. It was not a product of the Sun's domain. It was a visitor passing through, destined never to return. Hyperbolic motion is best understood as a geometric expression of energy. Any orbit can be described by the balance between kinetic energy, motion, and potential energy, gravity. For an elliptical orbit, kinetic energy is less than the magnitude of potential energy, meaning the object is trapped in a repeating cycle. A parabolic orbit lies on the boundary between bound and unbound. A hyperbolic orbit, however, indicates that kinetic energy exceeds gravitational potential. The surplus energy ensures escape. For 3I Atlas, this excess energy came not from the Sun, but from its long interstellar journey. The object carried the momentum of its birth system, the gravitational interactions it experienced afterward, and the accumulated velocity of drifting through the galaxy. By the time it reached the solar system, that motion was baked into its identity. The Sun could bend its path, but could never claim it. The shape of the hyperbola reveals much about the object's behavior. The closer an object passes to the Sun, the more sharply its path bends. The degree of curvature depends on the object's velocity. For a fast-moving interstellar traveler, the bend is slight, a graceful arc, not a tight turn. The object approaches the Sun, swings around, and then leaves on a path only modestly deflected. This is what astronomers observed with 3I Atlas. Its hyperbolic excess velocity, that portion of its motion that remains even after accounting for the Sun's pull, told them that its inbound trajectory was shaped by galactic dynamics, not solar system interactions. The orientation of the hyperbola also matters. The plane of motion, the angle of approach, the direction of departure, all these details record the object's initial motion through space. By plotting these parameters, astronomers can identify patterns. For example, if many interstellar objects arrived from the same region of the sky, that might suggest a shared origin, such as a dissolving star cluster or a nearby stream of debris. But 3I Atlas did not arrive from the same direction as Oumuamua or Borisov. Its path traced a different arc, unrelated to theirs. This independence reinforces the understanding that the galaxy is full of interstellar objects drifting randomly, not as part of a coordinated stream. The hyperbolic orbit also provides insight into the object's velocity relative to the local standard of rest, the average motion of stars near the Sun. An interstellar object with a velocity similar to this is likely part of the galactic disk. Its speed may reflect the typical motions of stars and debris in the area. For 3I Atlas, the velocity aligned with this expectation, placing it among the general population of disk-borne interstellar objects. But velocity is only part of the story. The orientation of the hyperbola, combined with the object's brightness and behavior, gives astronomers a way to model its rotation. Subtle changes in brightness as the object approaches and recedes reveal how it spins, how sunlight reflects off its surface, and whether the coma appears uniform or patchy. In the case of 3I Atlas, the variation suggested a slightly elongated shape, or an irregular surface, common features among comets. This, combined with its faint activity, reinforced its identity as a cometary body rather than a rocky asteroid. Hyperbolic motion also defines the timeline of visibility. Objects on closed orbits can be tracked for years, decades, even centuries. Their periodic returns allow for long-term observation. But objects on hyperbolic orbits offer only a single brief window. Their motion is fast, their time near the Sun fleeting. The higher the hyperbolic excess velocity, the shorter the opportunity. For 3I Atlas, visibility was limited to weeks and months. Its faint brightness made detection difficult even during that window. By the time astronomers realized what it was, its closest approach was already underway. Observations were constrained by its speed, faintness, and trajectory. The hyperbolic orbit ensured that once it passed beyond a certain distance, it would fade into invisibility forever. Hyperbolic motion also carries implications for the long-term fate of the object. After leaving the solar system, it resumes its journey through the galaxy, influenced only by the weak pull of distant stars and the overall gravitational potential of the Milky Way. Its speed relative to the Sun becomes irrelevant. Its path unfurls across the galaxy like a thread drawn taut by cosmic forces. The object may drift into regions of higher stellar density. It may pass near giant molecular clouds. It may encounter gravitational nudges from passing stars. It may be swept gently through spiral arms. Over millions of years, its hyperbolic path will be reshaped by the galaxy, altered slowly and subtly. Its trajectory may shift by light years, even tens or hundreds of light years, yet still retain its basic unbound state. The hyperbola is a snapshot of its motion near a star. It is not the full picture of its galactic journey, but it provides the only glimpse available to astronomers during its brief encounter with the Sun. Hyperbolic motion, in the end, tells a story of independence. It tells us that 3I Atlas is not part of our solar system. It tells us that it was born elsewhere. It tells us that it will never return. It tells us that stars do not own the small bodies that form around them, not forever. Some escape, some wander, some travel for ages through the galaxy. 3I Atlas is one of these wanderers. Its hyperbolic path is the mathematical proof of its cosmic freedom. When astronomers detect an object on a hyperbolic trajectory, the immediate reaction is excitement. Hyperbolic orbits are rare. They are the unmistakable footprints of objects that are not gravitationally bound to the Sun. They hint at origins beyond the solar system. They raise the possibility of a world born under another star. And in the wake of Oumuamua and Borisov, the scientific community now knows to take such possibilities seriously. But there is a complication. Not every hyperbolic orbit indicates an interstellar visitor. The solar system is a dynamic place. It contains massive planets capable of altering the orbits of smaller bodies through close encounters. Under the right conditions, a comet or asteroid can be accelerated to hyperbolic speed by a planetary slingshot. When this happens, the object's motion becomes unbound, even though it originated within the solar system. This creates a challenge. Astronomers must distinguish between true interstellar objects and native objects temporarily pushed onto hyperbolic paths. The distinction lies in velocity. The key measurement is the hyperbolic excess velocity, the speed an object retains even after it escapes the gravitational influence of the Sun. For most locally produced hyperbolic objects, this excess velocity is small. A planetary encounter can accelerate an object to escape speed, but rarely much faster. Once an object achieves escape velocity by only a narrow margin, its hyperbolic excess is modest, often less than a few hundred meters per second. By contrast, an interstellar object arrives with a much larger hyperbolic excess velocity. It retains the velocity of its prior motion through the galaxy, far exceeding what the planets can impart. Oumuamua, Borisov, and 3I Atlas all displayed excess velocities of several kilometers per second, far beyond what Jupiter or any other planet could produce. 3I Atlas showed a clear excess velocity. This was the first sign that it was truly interstellar. Another distinction lies in direction. Solar system dynamics produce certain preferred directions for ejected objects. For example, an object that receives a gravitational kick from Jupiter will typically exit near the ecliptic plane, the region where most planets orbit. Its trajectory will reflect recent gravitational encounters. In contrast, interstellar objects arrive from random orientations. Their paths are not confined to the ecliptic or aligned with planetary orbital planes. 3I Atlas arrived from an angle inconsistent with any recent planetary scattering event. Its trajectory pointed to an origin far outside the solar system's gravitational landscape. Orbital shape provides the next clue. While hyperbolic eccentricities can result from planetary encounters, they tend to be only slightly greater than 1.0. An eccentricity of 1.001 or 1.001 can be produced by Jupiter. But an eccentricity of 1.02 or higher almost certainly requires an interstellar origin. The shape of the orbit reflects the magnitude of excess velocity. 3I Atlas displayed an eccentricity well above these thresholds. It was not merely unbound, it was unbound by a wide margin. The condition of the surface adds another clue. Interstellar objects display the hallmarks of cosmic ray processing: dark surfaces, red coloration, suppressed volatility, thick mantles, faint activity even when warmed. These features distinguish them from freshly ejected solar system comets whose surfaces have not experienced prolonged interstellar exposure. 3I Atlas fit the interstellar profile: faint activity, hardened crust, and a light curve typical of radiation-processed bodies. The rarity of hyperbolic solar system objects also matters. They do occur, but not often. When ejections happen, most objects fall into the Oort cloud instead of escaping entirely. True escape from the solar system requires unusually strong interactions or a series of encounters that impart cumulative velocity. This rarity places statistical constraints on hyperbolic identifications. If an object shows a high excess velocity, an unusual direction, faint activity, and a dark surface, the odds overwhelmingly favor an interstellar origin. Another consideration is timing. Planetary scattering occurs most frequently when planets are young, dynamic, and migrating. The solar system's major migrations occurred billions of years ago. Jupiter no longer migrates. Saturn does not shift dramatically. The scattering rates today are far lower than in the past. Thus, objects ejected today are less common, and those that are would be detectable due to their proximity to Jupiter. 3I Atlas showed no signs of recent planetary influence. No planet lay near its inbound trajectory. No gravitational encounter could explain its speed. Its motion was smooth, unperturbed, and consistent with a simple interstellar approach. Another line of reasoning arises from galactic dynamics. Interstellar objects share velocities consistent with the distribution of stars near the Sun. Their speeds cluster in predictable ways because they follow the same rotational patterns as the disk. Solar system bodies do not show this behavior. Their velocities reflect local dynamics, not galactic motion. 3I Atlas displayed a velocity consistent with disk populations, further supporting its interstellar identity. Finally, the object's behavior near the Sun also provides a hint. Interstellar comets often show delayed activity because their surfaces are so processed. They brighten reluctantly. Their comas are faint. Their dust production is minimal. Solar system comets on hyperbolic trajectories typically show vigorous, familiar activity, unless recently depleted. 3I Atlas exhibited the characteristic subdued awakening of an interstellar comet, not the active eruption of a solar system body. All these clues combine to form a complete picture. Yes, hyperbolic motion can arise from within the solar system, but only under specific conditions, only with small excess velocities, only in predictable directional patterns. 3I Atlas fulfilled none of those. Its excess velocity was too high, its direction was too random, its surface was too processed, its behavior was too subdued. It was hyperbolic not because it had been flung away from the Sun, but because it arrived carrying the momentum of the galaxy. This is why hyperbolic orbits require careful interpretation, and why 3I Atlas was immediately recognized as something extraordinary. It was not a fling from Jupiter, not a local comet gone rogue, not a relic of a recent scattering event. It was a true interstellar visitor, one whose hyperbolic path signaled not an escape from the solar system, but an arrival into it. When an interstellar object like 3I Atlas begins its long journey through the galaxy, it does not travel through a calm or predictable environment. The Milky Way is filled with motion, stars moving on wide orbits, clusters dissolving, molecular clouds drifting, and dark matter shaping the gravitational landscape. These motions create a dynamic arena where even small objects feel subtle but continuous gravitational influences. Over time, these influences accumulate, altering trajectories in ways both chaotic and poetic. To understand how 3I Atlas moved through the galaxy, one must understand gravitational scattering in deep space. Gravitational scattering is the process by which a small body's path is altered by the gravitational pull of a larger mass, usually a star, but sometimes a compact object, a cluster, or even a massive gas cloud. The degree of scattering depends on the mass of the object encountered, the distance of closest approach, and the relative velocity. Unlike the dramatic scattering that occurs during ejection, where a planet like Jupiter can sling a comet outward in a single powerful event, deep space scattering is more subtle. Stars are far apart. Most encounters are distant. The forces involved are gentle. But gentle does not mean insignificant. Over millions or billions of years, even tiny perturbations accumulate into substantial changes. The most common type is distant stellar scattering. Imagine 3I Atlas drifting through the galaxy when a star passes within a few light years. At that distance, the gravitational pull is weak, but not zero. The star's mass tugs slightly on the object's path, changing its direction by fractions of a degree. If the object encounters hundreds of such stars over time, and it inevitably does, the cumulative deflection becomes large. The shape of this deflection depends on the geometry of the encounter. If the star approaches on a parallel path, its gravity may pull the object inward or outward relative to its original direction. If the star moves across the object's trajectory, the gravitational force might accelerate or decelerate it. Over time, this turns what might have been a straight line path into a wandering route shaped by many small nudges. Such encounters do not change the object's overall energy much. They change its direction, not its interstellar speed. This is why interstellar objects retain velocities characteristic of their original stellar population, even after traveling for extraordinary lengths of time. The second type of scattering occurs near star clusters. Star clusters are dense regions where many stars form at once. Young clusters contain stars tightly packed, sometimes within a few thousand astronomical units of one another. Over the first few 100 million years of their lives, these clusters gradually disperse, their stars drifting apart into the general galactic disk. But while they remain bound, they create environments of intense gravitational interaction. If 3I Atlas began its journey in or near such a cluster, it may have been shaped significantly by these early scattering events. The gravitational pull of nearby stars could have altered its velocity before it was fully ejected. Later, if the object passed through another dissolving cluster, its trajectory might have been influenced again. These interactions are more dramatic than encounters with lone stars. The higher density increases the frequency of close passes. A close pass within even a fraction of a light year could alter the trajectory by tens or hundreds of degrees. Another type of scattering involves giant molecular clouds. Molecular clouds are enormous structures, sometimes containing millions of solar masses of gas and dust. They play a major role in star formation. Their gravitational influence is vast, extending across dozens of light years. If an interstellar object passes near the edge of a cloud, the gravitational pull can alter its path significantly. These effects are slow but powerful, bending trajectories and redirecting objects through different parts of the galaxy. For 3I Atlas, such encounters might explain why its backward traced orbit becomes impossible to follow beyond a few million years. The gravitational landscape is too complex, and passing near a massive cloud or star cluster long ago would have erased any hope of tracing its origin. The scattering by dark matter is even more subtle. Dark matter does not interact with light. It does not produce radiation. It does not collide with normal matter. But it does produce gravity. The galaxy's dark matter halo shapes the gravitational potential of the entire Milky Way. For interstellar objects, the presence of dark matter ensures that their long-term paths cannot be approximated by interactions with stars alone. They feel the combined influence of baryonic matter, stars, gas, dust, and an even larger hidden mass. While dark matter does not scatter objects directly in the way stars do, it alters the gravitational environment enough that long-term trajectories drift more unpredictably than they would in a galaxy composed only of normal matter. Another form of scattering occurs through multi-body interactions. If an interstellar object passes through a region where several stars happen to be in relatively close configuration, perhaps a hierarchical system or a temporary gravitational group, the combined forces create complex motions. These interactions can produce chaotic paths, sometimes accelerating objects, sometimes slowing them, sometimes altering their direction abruptly. Although rare, such interactions leave permanent marks on the object's long-term trajectory. All these scattering processes combine into a single profound outcome. An interstellar object's path is not a memory of its birthplace. It is a memory of every place it has been. Its trajectory is a composite of millions of tiny forces integrated over cosmic time. For 3I Atlas, gravitational scattering explains why its origin cannot be traced with certainty. Every stellar pass, every cloud encounter, every galactic oscillation pulled it slightly off course. These small deflections, accumulated over thousands of orbits around the galactic center, produced a final inbound path that carries no clear signature of where it began. Yet the scattering also tells us something else, that the galaxy is not a static backdrop. It is a dynamic environment where stars and planets move in constant motion. Interstellar objects are not isolated. They participate in the ongoing gravitational interactions that shape the Milky Way. In this sense, 3I Atlas did not simply wander. It was guided, gently, subtly, continuously, by the galaxy. Its story is one of gravitational choreography. Its path is a product of countless unseen encounters. Its arrival was shaped not by chance, but by the cumulative influence of the stars themselves. When a comet or asteroid in the solar system is observed, astronomers can often trace its path backward through time, sometimes for centuries, sometimes for thousands of years. The gravitational influences are understood. The positions of planets are known. The system is closed, predictable, and bound. But with an interstellar object like 3I Atlas, the past becomes unknowable beyond a certain point. No matter how precise the measurements, no matter how advanced the models, no matter how powerful the simulations, the origin remains hidden behind a veil of galactic complexity. This difficulty is not for lack of understanding. It is a fundamental limitation imposed by the physics of the galaxy itself. There are several reasons why tracing interstellar origins is nearly impossible. The first is uncertainty in measurement. Every observation has an error margin. The position of an object, the speed, the direction, all are measured with extraordinary precision, but never perfect precision. These uncertainties may be tiny in the moment of observation, but they expand as the trajectory is integrated backward through time. A small uncertainty today becomes a larger uncertainty a few thousand years ago. After 1,000,000 years, the uncertainty grows exponentially. The object's position becomes a diffuse cloud, not a point. After 10 million years, the possibilities become so wide that the model loses meaningful predictive power. But uncertainty is not the only obstacle. The second difficulty arises from the limits of stellar catalogs. Even with Gaia, the most precise stellar survey in history, astronomers know the positions, velocities, and motions of only a fraction of the stars in the galaxy. Many stars remain unmeasured or poorly measured. Their past positions cannot be reconstructed reliably. Even among the stars that are well measured, the long-term uncertainties accumulate. After a few million years, the positions of stars become uncertain enough that tracing a small object backward becomes an exercise in probability. For an interstellar object to be traced to a specific star, astronomers would need to know that the object passed extremely close to that star at a specific time. Without complete catalogs and perfect motion models, that precision is unattainable. The third obstacle is chaotic galactic dynamics. The Milky Way is not a stable system. Stars move in the gravitational field of the galaxy, but they also interact with each other. They pass through spiral arms. They oscillate above and below the disk. Clusters dissolve. Stars migrate radially. Giant molecular clouds drift unpredictably. Dark matter halos influence motion. All these factors create a system where long-term motion is chaotic. Even if the current positions of stars were known perfectly, the past arrangement of the galaxy cannot be reconstructed in exact detail. Over tens of millions of years, small uncertainties in gravitational interactions lead to divergent outcomes. This chaos prevents precise reconstruction of the past path of any interstellar object. The fourth factor is the influence of unrecorded gravitational encounters. As 3I Atlas traveled through the galaxy, it likely passed near many stars. Most of these encounters were distant and gentle, but even gentle encounters matter. A close pass at 2 or 3 light-years can alter the trajectory significantly. If astronomers do not know the identities or past positions of these stars, they cannot model the effect. Many stars that 3I Atlas passed near are no longer catalogued as nearby stars. They may be hundreds of light years away now. They may be dim. They may have moved beyond detection. Some may no longer exist. Without knowledge of these encounters, the object's path becomes impossible to reconstruct. The fifth obstacle is the role of giant molecular clouds. Passing near such a cloud alters the trajectory more dramatically than a single star. But the positions and motions of these clouds millions of years ago are uncertain. The galaxy's structure evolves. The spiral arms drift. Clouds collide, fragment, disperse. Dark matter halos influence motion. All these factors create a system where long-term motion is chaotic. Even if the current positions of stars were known perfectly, the past arrangement of the galaxy cannot be reconstructed in exact detail. Over tens of millions of years, small uncertainties in gravitational interactions lead to divergent outcomes. This chaos prevents precise reconstruction of the past path of any interstellar object. The fourth factor is the influence of unrecorded gravitational encounters. As 3I Atlas traveled through the galaxy, it likely passed near many stars. Most of these encounters were distant and gentle, but even gentle encounters matter. A close pass at 2 or 3 light-years can alter the trajectory significantly. If astronomers do not know the identities or past positions of these stars, they cannot model the effect. Many stars that 3I Atlas passed near are no longer cataloged as nearby stars. They may be hundreds of light-years away now. They may be dim. They may have moved beyond detection. Some may no longer exist. Without knowledge of these encounters, the object's path becomes impossible to reconstruct. The fifth obstacle is the role of giant molecular clouds. Passing near such a cloud alters the trajectory more dramatically than a single star. But the positions and motions of these clouds millions of years ago are uncertain. The galaxy's structure evolves. The spiral arms drift. Clouds collide, fragment, disperse. Dark matter halos influence motion. All these factors create a system where long-term motion is chaotic. Even if the current positions of stars were known perfectly, the past arrangement of the galaxy cannot be reconstructed in exact detail. Over tens of millions of years, small uncertainties in gravitational interactions lead to divergent outcomes. This chaos prevents precise reconstruction of the past path of any interstellar object. The fourth factor is the influence of unrecorded gravitational encounters. As 3I Atlas traveled through the galaxy, it likely passed near many stars. Most of these encounters were distant and gentle, but even gentle encounters matter. A close pass at 2 or 3 light-years can alter the trajectory significantly. If astronomers do not know the identities or past positions of these stars, they cannot model the effect. Many stars that 3I Atlas passed near are no longer cataloged as nearby stars. They may be hundreds of light-years away now. They may be dim. They may have moved beyond detection. Some may no longer exist. Without knowledge of these encounters, the object's path becomes impossible to reconstruct. The fifth obstacle is the role of giant molecular clouds. Passing near such a cloud alters the trajectory more dramatically than a single star. But the positions and motions of these clouds millions of years ago are uncertain. The galaxy's structure evolves. The spiral arms drift. Clouds collide, fragment, disperse. All these factors create a system where long-term motion is chaotic.
The environment that existed when 3I Atlas first began its journey is not the environment astronomers observe today. Without knowing the positions of these massive clouds in the distant past, reconstruction cannot succeed. The sixth problem is the length of time involved. Interstellar objects may wander for billions of years. Over such timescales, even the structure of the galaxy itself evolves. Stars form and die, spiral arms shift. The galactic bar changes shape. The dynamics of the disk alter. Any attempt to trace a path over such scales becomes an attempt to reconstruct a cosmic history too vast and complex to be modeled with precision. The seventh factor is the nature of the object's origin itself. During ejection, the velocity imparted to the object depends on chaotic gravitational interactions within its home system. To reconstruct its origin, astronomers would need to know the velocity relative to the star at the moment of ejection. But this information is lost forever. The object's current speed is a combination of that initial velocity plus billions of years of perturbations. Even if the object could be traced back toward a specific region of the galaxy, the details of its ejection velocity would introduce uncertainties large enough to obscure the true point of origin. The eighth difficulty involves cosmic radiation. The surface provides chemical clues, but radiation processing destroys the finer details of its early history. The crust darkens, molecules are rearranged, isotopic ratios shift. Over time, the surface becomes a record of the interstellar journey, not the birth environment. The deeper interior remains pristine, but measuring it directly would require a sample return mission, an impossible task for objects moving at such high velocities. Without the ability to analyze the interior, the origin remains speculative. All these reasons combine into a fundamental truth. Interstellar origins cannot be traced with precision. They can only be inferred statistically, never pinpointed, never confirmed. This is not a limitation of instruments. It is a limitation imposed by the galaxy's nature. Astronomers can identify the population from which an object came, the thin disk, the thick disk, or the halo. They can infer something about the chemistry. They can model likely ejection mechanisms. They can simulate probable paths through the galaxy, but they cannot identify the star. 3I Atlas may have come from a star long gone. It may have been born in a cluster that has since dispersed. It may have been ejected billions of years ago. It may have traveled through multiple spiral arms. Its origin is hidden not by mystery, but by the physics of motion through a dynamic galaxy. And yet, this uncertainty is part of the object's fascination. It is a reminder that the Milky Way is vast, that stars are not isolated entities, that material drifts freely between systems, that worlds exchange fragments. 3I Atlas is a traveler without a known birthplace, and that makes it a messenger from everywhere and nowhere at once. Long before 3I Atlas was discovered, long before its faint glow registered on the sensors of the Atlas survey, long before astronomers knew they were witnessing a visitor from another star, the object began its descent into the outer reaches of the solar system. This region, the vast outskirts that stretch far beyond the orbit of Neptune, is a boundary zone, a frontier where the influence of the sun is real but faint, where darkness dominates, and where a wandering interstellar object begins to feel the first delicate pull of our star. The outskirts of the solar system are not empty. They are populated by countless icy bodies drifting in slow, distant orbits. These are the residents of the Kuiper Belt, and, farther beyond, the scattered disk and the inner Oort cloud. These regions represent the frozen remnants of the solar system's formation. They are worlds untouched by sunlight for billions of years. And into this cold domain, 3I Atlas entered quietly, unnoticed. The approach began with a shift in velocity so subtle it could not be measured directly. At a distance of hundreds of astronomical units, the sun's gravity acts as the faintest whisper. Yet even that whisper exerts its influence. Gravity has infinite reach. Even a small pull, applied continuously, can bend the path of a passing body. As 3I Atlas crossed into the region dominated by this whisper, its trajectory began to curve, not dramatically, but inevitably. The curve was too small to detect without mathematical modeling, but the physics is clear. The sun claimed the object with the softest possible touch, drawing it inward along a gentle hyperbolic arc. This region is where the story of its encounter with our star truly begins. The outskirts of the solar system are filled with interstellar dust grains pushed inward by galactic motion, cosmic radiation, and the sun's gravity. These dust grains are few and far between, but over spans of millions of kilometers, an object drifting through them will collide occasionally. These collisions are minuscule, leaving only microscopic pits on the surface of 3I Atlas, but they represent the first physical contact between the visitor and the environment of our star. The temperature out here is near absolute zero. No sunlight penetrates deeply enough to warm the surface. The irradiated crust of 3I Atlas remained as cold as during its interstellar flight. but the environment began to change in ways imperceptible to human senses. Here, the solar wind begins its reach. The solar wind is a stream of charged particles, mostly protons and electrons, emitted continuously from the sun's corona. At distances comparable to the Kuiper belt, the solar wind is faint, but it is still present. These particles interact with the object's surface. They charge dust grains. They alter electrical potentials. They embed themselves in the crust. And for an object that has drifted through environments dominated by cosmic rays from the galaxy at large, the solar wind presents a new kind of radiation, one gentler, lower in energy, but constant. As 3I Atlas drifted inward, the density of solar wind particles increased. This affected the electrical environment around the object.
Electrons built up in some regions. Positive charge accumulated in others. These variations sometimes caused dust grains to detach from the surface through electrostatic repulsion. This is one of the earliest ways a faint coma can form, even before sublimation begins. At these distances, however, such dust release is extremely faint. The object remained essentially invisible to Earth's telescopes, its brightness too low to distinguish from the background stars. But something else was beginning as well. The heliosphere, the vast bubble created by the solar wind, begins to dominate the environment at distances of tens to hundreds of astronomical units. Outside the heliosphere, the interstellar medium shapes radiation levels and charged particle densities. Inside the heliosphere, the solar wind takes over. Crossing the heliopause, the outer boundary, is a transition that marks an object's entry into the sun's domain. 3I Atlas crossed this boundary long before we observed it. Once inside the heliosphere, the object traveled through a region of space dominated by the sun's influence. The magnetic field of the sun becomes more structured here, shaping the paths of charged particles. The density of solar wind increases, and the intensity of scattered sunlight slowly climbs, though not yet enough to cause significant warming. Still, the transition matters. Inside the heliosphere, cosmic rays are partially shielded. Their intensity decreases. This means the processing of the object's surface changes subtly. The cosmic ray chemistry that dominated during its interstellar journey gives way to a new regime of radiation effects. The solar wind becomes the primary agent of surface alteration. This shift in radiation environment may have produced new radicals within the crust. These radicals could later contribute to the faint release of volatile molecules as the object warmed. As 3I Atlas moved deeper, it encountered the scattered disk, a region populated by icy bodies with highly eccentric orbits. Unlike the Kuiper belt, which is relatively orderly, the scattered disk is chaotic. Its objects can reach great distances from the sun and return on long, stretched trajectories. It is a region sculpted by interactions with Neptune, where dynamical instabilities abound. The arrival of an interstellar object in this region is not disruptive. The distances between objects are immense. But passing through a region filled with ancient frozen bodies serves as a symbolic moment. For the first time since its ejection, 3I Atlas entered a domain shaped by another star's planets. It did not pass near any large body. It did not collide. It did not interact gravitationally. But it crossed through a region defined by the solar system's architecture, a region populated by icy relics of our own world's creation. Only after this long, silent drift did the object approach the Kuiper belt proper, the region between about 30 and 50 astronomical units from the sun. This is where sunlight, though still faint, becomes strong enough to matter. The first photons began to seep into microscopic cracks in the surface. Dust grains warmed slightly. Trapped gases deep within the crust began to vibrate. Nothing drastic occurred, but the process had begun. Sublimation had not yet started, but the early signs of awakening were present.
This is also when Earth's telescopes might have been able to detect the object if they had been pointed exactly at the right spot. But the sky is vast. The object was too faint, and its motion too subtle. No instrument saw it. It continued inward, untouched, unseen. Only later, when it brightened slightly as the solar illumination increased, did Atlas detect it against the backdrop of stars. By then, 3I Atlas had crossed fully into the Sun's gravitational realm. By then, its fate as an interstellar visitor passing through was sealed. By then, the outskirts of the solar system had done their quiet work, ushering the visitor inward without fanfare. The journey through the solar system's outskirts is the story of gradual transition, from the deep silence of interstellar space to the faint glow of our star's distant light. And it is the beginning of the brief, precious moment when humans were able to witness a fragment of another world. The heliosphere is a boundary unlike any other in the solar system. It is not a barrier made of matter, but a region shaped by energy and motion, specifically by the steady outflow of the solar wind. This vast bubble surrounds the Sun and all the planets, extending more than 100 astronomical units in every direction. Outside it lies the interstellar medium. Inside it lies the realm of the Sun. For an interstellar object like 3I Atlas, crossing into the heliosphere is a profound transition. It is the moment when the environment changes in ways that have not happened since the object left its home star's equivalent bubble. The heliosphere is created by the solar wind, a supersonic stream of charged particles flowing outward from the Sun. These particles push back against the gas and magnetic fields of the interstellar medium, carving out a cavity in the galaxy. The edge of this cavity is the heliopause, a boundary where the outward pressure of the solar wind balances the inward pressure of the interstellar medium. To a spacecraft, the heliopause would appear as a subtle shift in particle density and magnetic field direction. To an interstellar object drifting silently toward the Sun, the crossing would be invisible, undetectable except through the changing conditions around it. Yet this crossing marks the first point at which the object becomes part of the solar system's environment. Before crossing the heliopause, 3I Atlas drifted through a region dominated by cosmic rays from across the galaxy. These high-energy particles shaped its surface chemistry for eons. But once inside the heliosphere, the density of galactic cosmic rays drops. The solar wind, though weaker in energy, becomes the dominant radiation source. This shift influences not only the object's surface chemistry, but also the behavior of dust grains, the electrostatic environment, and even the earliest stirrings of a coma. Inside the heliosphere, the solar magnetic field begins to shape the motion of charged particles around the object.
This magnetic influence is not strong enough to alter the object's trajectory. Only gravity can do that, but it affects the charged environment near the surface. Dust grains accumulate charge. Gas molecules ionize more readily. Electrons streamed from the Sun collide with the crust. These interactions contribute to electrostatic charging. Electrostatic charging contributes to dust movement. Dust movement contributes to coma formation. The first faint coma of 3I Atlas may have begun not due to heat, but due to electrical effects triggered by its entry into the heliosphere. Another important consequence of entering the heliosphere is the change in particle impact dynamics. Outside the heliosphere, cosmic rays strike the surface with tremendous velocity. Inside, the solar wind dominates, producing lower energy but more frequent impacts. These produce shallow implantation effects, embedding ions into the very outermost layer of dust. This alters the reflectivity of the object slightly. It changes the spectrum of light scattered from the surface. These changes, although tiny, affect how bright or dark the object appears to telescopes when first detected. Another consequence is the pressure of the solar wind. The solar wind exerts a tiny force on any object it encounters.
This force is negligible for a large asteroid or comet, but for small dust particles released from the surface, it matters greatly. As dust begins to lift from the crust, the solar wind pushes it outward, forming the earliest components of a tail. This is why the entry into the heliosphere is critical for coma and tail formation, even before sublimation becomes the dominant process. The heliosphere also contains ions that interact with the object's released gases. When water vapor, carbon monoxide, or carbon dioxide molecules escape through microscopic fissures, they may encounter solar wind ions. Chemical reactions occur, creating ionized molecules that drift outward in response to the solar magnetic field. This interaction helps establish the ion tail, typically faint in early stages, but important for understanding the composition of the object. As 3I Atlas moved further inside the heliosphere, the solar magnetic field grew stronger. The structure of this field is complex, shaped by the Sun's rotation, the solar cycle, and magnetic turbulence. For an interstellar object, this environment presented a kind of dynamic electromagnetic ocean, one that influenced the distribution of ionized gas around the nucleus. Though the object's path remained governed by gravity, its near-surface environment was now dominated by solar wind interactions. Another change that occurs upon entering the heliosphere is a shift in temperature gradients. The interstellar medium has a characteristic temperature, defined by its composition and cosmic ray heating. Inside the heliosphere, the temperature is slightly higher, not enough to warm the surface substantially, but enough to alter the balance between energy input and radiative cooling. This contributes to the first signs of thermal stress on the object. The crust, long stabilized at interstellar temperatures, experiences slight warming. Although the increase is minimal, even a small rise can change how gases trapped beneath the crust behave. They expand slightly. They move through microchannels. They approach the surface with greater pressure. These processes begin quietly. They are invisible. They are incremental. But they represent the earliest stages of the awakening that will later become visible. For the first time in ages, 3I Atlas was in a region where a star's influence, not just its gravity, but its environment, affected it continuously. It had entered a living system, a bubble shaped by wind and magnetism and radiation, a domain where small bodies respond to sunlight and interact with flowing charged particles. The heliosphere is the Sun's breath, and 3I Atlas, after drifting through the frozen silence of interstellar space, had finally stepped into it. This crossing marked a line in its long story, a line dividing the deep past of isolation from the brief moment of recognition. The heliosphere embraced it, altered it, and prepared it for the encounter that would follow. Soon, sunlight would touch it more directly. Soon, it would brighten. Soon, it would be seen. But the first contact was silent, subtle, invisible, and it was the beginning of its revelation. To understand the approach of 3I Atlas into the deeper regions of the solar system, one must understand the complex, diffuse, and mysterious boundary that defines the Sun's farthest gravitational domain, the Oort cloud. Though never directly observed, no telescope has ever captured a clear image of one of its icy bodies. The Oort cloud is one of the most important structures in planetary science. It is the vast reservoir from which long-period comets originate. It is the cradle of frozen relics that date back to the formation of the solar system. And it is a region where the gravitational influence of the Sun blends with that of the galaxy, shaping the motion of bodies that reside on the edge of interstellar space. It is also the region through which interstellar objects like 3I Atlas pass as they enter our solar system. The Oort cloud is not a disk like the Kuiper belt. It is a sphere, an immense diffuse sphere of icy bodies surrounding the solar system in all directions. Its inner boundary may begin at a few thousand astronomical units. Its outer boundary may extend to 100,000 units or more, nearly halfway to the nearest stars. If the solar system were the size of a coin, the Oort cloud would be a bubble surrounding it at the distance of a football field.
Its emptiness is profound, yet it contains perhaps trillions of objects. These objects are remnants of the early solar system, scattered outward by the gravity of the giant planets during their chaotic youth. Over billions of years, the orbits of these bodies have been shaped not only by the Sun, but also by the passing stars, molecular clouds, and galactic tides. The Oort cloud is a hybrid of solar system origins and galactic influences. When an interstellar object approaches the Sun, it must pass through this vast region. The passage is quiet. The distances between objects are enormous, comparable to distances between stars on smaller scales. Collisions are essentially impossible.
Interactions with individual Oort cloud bodies are negligible, yet the region represents the first true transition from the interstellar environment to the structured environment of a star system. As 3I Atlas drifted through the Oort cloud, it would have encountered the gravitational influence of the countless icy bodies that reside there. But the influence of any single one is tiny. What matters is the collective effect. The Oort cloud contributes mass to the outskirts of the solar system. This mass, though diffuse, shapes the gravitational field. As the object passed through, its trajectory may have been perturbed ever so slightly, not enough to alter its inbound path significantly, but enough to add to the total sum of gravitational interactions that marked its journey. The galactic tide is another key player in this region. The Oort cloud exists in a delicate balance between the Sun's gravity and the gravity of the galaxy. This balance maintains the cloud but also destabilizes it. The galaxy's center exerts a pull. The disk contributes a gradient. The spiral arms affect the distribution of nearby stars. All these forces combine into a tide that shapes the Oort cloud as a whole. For an interstellar object, the galactic tide subtly alters the trajectory as it passes through this region. The effect is gentle, but it exists. The motion of the object relative to the galactic plane, combined with the shifting gravitational environment, contributes to the small deflections that make long-term trajectory reconstruction impossible. One of the more intriguing possibilities when an interstellar object passes through the Oort cloud is the chance of encountering material from the solar system's early days. These bodies have been frozen for billions of years. Some contain original ices from the protoplanetary disk. Some may hold clues to the formation of the giant planets. Though 3I Atlas would not have interacted with any directly, its passage near them is a symbolic meeting, two different worlds, both ancient, crossing paths in the darkness. Another dynamic of the Oort cloud is the way it responds to interstellar objects. When an object like 3I Atlas passes through, it contributes to the gravitational experience of the region. Its mass is tiny but non-zero. It is one more body drifting through the cloud, one more moving object participating in the gravitational dance that shapes the cloud's long-term stability. While 3I Atlas was too small to perturb the orbits of Oort cloud bodies meaningfully, the concept emphasizes the interconnectedness of all structures in the galaxy. Objects from one star's system occasionally pass through the outskirts of another star's domain. These interactions, though subtle, underscore the fact that planetary systems are not isolated. They exchange material, however indirectly, across cosmic distances. As 3I Atlas continued its inward journey, the density of Oort cloud bodies increased slightly, not enough for a measurable change, but enough to represent a shift in its environment. The region grows more structured as one approaches the inner edge. The gravitational influence of the Sun increases. The scattered disk and Kuiper belt lie ahead. And for the visitor, this means the beginning of a more noticeable gravitational acceleration. Even though the Sun's pull is faint at tens of thousands of astronomical units, it is enough to begin accelerating the object. The inward speed gradually increases, not dramatically, but steadily. The object begins to fall inward, picked up by the gravity of the star that dominates this region of space. This acceleration is the first significant physical effect of entering a star system. Over thousands of years, the object's velocity slowly increases.
Its hyperbolic trajectory becomes more visible as it approaches the inner regions where observation is possible. Yet velocity is only part of the story. The temperature remains near absolute zero. No sublimation occurs. The irradiated crust remains intact. The object is not yet awakened. It is simply falling toward a faint point of light that grows slowly brighter as it approaches. The Oort cloud therefore represents a kind of cosmic gateway, not a physical barrier, but a gravitational boundary. An interstellar object that crosses it is entering a region where a star's gravity dominates motion. It is transitioning into a region where it can no longer drift passively, but must respond to the star's pull. For 3I Atlas, this transition marked the beginning of a new chapter in a long journey. The Oort cloud did not change it physically, it did not warm it, it did not awaken it, but it placed the object on a path that would carry it deep into the solar system, toward the distant gaze of telescopes, toward the light of the sun, and toward a moment of discovery that would echo across scientific literature. The dynamics of the Oort cloud are not merely a structural fact about our solar system. They are a reminder that any star system is surrounded by a region where its influence fades, where interstellar and stellar domains mix, where visitors can cross without resistance, and where outbound objects depart into the galaxy. It is the edge of the sun's reach, and it is the first part of the solar system that 3I Atlas encountered. After passing through the diffuse outer reaches of the Oort cloud, 3I Atlas continued inward, moving into a region populated by icy bodies that are far closer, far more structured, and far more observationally understood: the Kuiper Belt. This is the zone where large icy dwarf planets like Pluto and Eris orbit. It is a region filled with frozen relics left over from the early days of the solar system. A region shaped by the gravitational influence of Neptune, sculpted by resonance, and populated by objects ranging from pebble-sized fragments to dwarf planets hundreds of kilometers wide. For an interstellar visitor, entering the Kuiper Belt represents a passage from the abstract outskirts into a region where the architecture of the solar system becomes visible. The Kuiper Belt begins roughly at 30 astronomical units and extends to about 50. Within this band, objects orbit in relatively stable configurations. Some are locked in resonances with Neptune. Some follow circular paths. Others move in slightly eccentric orbits. The distribution reflects the complex history of early planetary migration, when Neptune likely moved outward and scattered material before settling into its present orbit. As 3I Atlas drifted into this region, it encountered a world of icy bodies unlike anything in the interstellar medium. For billions of years, these objects have orbited the Sun, slowly evolving, slowly interacting, slowly developing the surface features we associate with Kuiper Belt objects: methane frost, irradiated organics, nitrogen ices, and complex tholins. For 3I Atlas, however, the Kuiper Belt represented something quite different. It was a silent gallery of frozen worlds it would not touch, not disturb, and not collide with. The distances between objects are vast, millions of kilometers. But the belt's very existence is a sign of the solar system's structured interior, a contrast to the unbound randomness of interstellar space. One might imagine what it would be like if the interstellar visitor could pass near Pluto or Eris, if it could graze the orbit of a binary Kuiper Belt pair, or if it could interact gravitationally with one of the distant dwarf planets. But the reality is far more subtle. Its path was not aligned with any particular major Kuiper Belt body. It passed through the region silently, unnoticed by the residents of this frozen domain. But the Kuiper Belt, despite its emptiness on human scales, is dense compared to interstellar space. Dust grains populate it. Plasma environments shift. The solar wind is stronger here. The magnetic field is more structured. The scattered sunlight is faint but measurable. These factors represent a change, a gradual shift from the environment of the Oort cloud toward the more active environment of the inner solar system. As 3I Atlas drifted through the Kuiper Belt, the first measurable warming began.
Not enough to melt ices or form a prominent coma, but enough to create microscopic thermal gradients. Dust grains expanded slightly. The crust redistributed heat through conduction. Molecules deep within the surface gained tiny amounts of energy. This warming was subtle, but it mattered. It prepared the crust for future sublimation. It contributed to the eventual release of trapped gases. It initiated processes that would become visible months later in the inner solar system. Meanwhile, the object experienced an increasing flux of reflected sunlight. Even though the Kuiper belt is dim, objects reflect sunlight from their icy surfaces. The diffuse glow of countless distant bodies creates a faint light environment that differs from the near-total darkness of interstellar space. This diffuse light produced almost no measurable effect on the object, but it represents a symbolic change. It had entered a domain that was illuminated, however faintly, by worlds orbiting the Sun. Another subtle influence comes from Kuiper belt plasma conditions. The solar wind encounters resistance from the dust and objects in this region, producing slight variations in particle density and magnetic turbulence. For an interstellar object, this environment may lead to increased electrostatic charging. Dust grains on the surface acquire charge more readily. Some may detach from the surface. A few may drift into space, forming the earliest whispers of a tale. These effects are faint, nearly undetectable from Earth, but they represent the earliest visible changes in the object's physical state. As 3I Atlas moved inward, its velocity increased under the Sun's gravitational pull. The hyperbolic path became steeper. The incoming direction shifted slightly due to gravitational focusing. These changes brought it closer to regions where detection would eventually be possible. The Kuiper belt also holds another significance. It is where humanity has placed a spacecraft capable of sensing objects at these distances. NASA's New Horizons probe, after flying past Pluto, drifted through the Kuiper belt, studying several Kuiper belt objects and measuring the environment directly. If 3I Atlas had approached within the field of view of New Horizons instruments, it might have been detected earlier. But space is vast, and chances are vanishingly small. The object passed through the belt without encountering the probe, leaving no trace detectable by instruments other than the sunlight it would later reflect. The Kuiper belt is also the region where the object's motion becomes governed by classical solar system dynamics in a more predictable way. The gravitational influence of Neptune is significant here, though it did not meaningfully perturb 3I Atlas. The Sun's influence grows stronger with every passing astronomical unit. The heliospheric environment intensifies. The object transitions from distant, cold quiet into a realm where sunlight will soon begin to dominate its behavior. Yet the Kuiper belt was not simply a region the object passed through. It was a threshold. It marked the shift from near absolute darkness to faint starlight, from cosmic isolation to solar system structure, from preserved stillness to a slow awakening. As 3I Atlas left the Kuiper belt behind, it moved into regions where the Sun's influence would become more pronounced. Its surface would begin to warm, its crust would begin to crack, its interior gases would begin to expand. The coma would begin to form in earnest, and eventually the object would brighten enough to be seen. The Kuiper belt was the last place it passed through unseen, silent, invisible, a ghost drifting through a frozen sea of ancient worlds. Ahead lay sunlight, discovery, and a fleeting moment in which humans would recognize a visitor from another star. As 3I Atlas left the Kuiper belt behind and drifted further into the inner reaches of the solar system, an important transformation began, one that no interstellar object can avoid when passing close enough to a star. The silence of deep space, the frozen stillness preserved for millions or billions of years, began to loosen. It happened gradually, almost invisibly, but it was a real change, a change driven by the faint but ever-increasing warmth of sunlight. For most of its journey, sunlight had been nothing more than a distant glow, indistinguishable from the general starlight of the galaxy. Even in the outer solar system, the Sun was still just another bright point in a sky filled with countless stars.
But as 3I Atlas approached the region inside 20 or 30 astronomical units, that point of light became a source of measurable heat. The irradiated crust, hardened by cosmic rays over ages, was slow to respond. Its darkened surface absorbed sunlight but conducted heat poorly. For days, weeks, months, the crust warmed by tiny increments, fractions of a degree. Yet those fractions mattered. Even the smallest thermal gradient can begin to influence volatile ices deep beneath the surface. The first glimmers of activity usually start as changes in pressure. Deep inside, beneath meters or perhaps tens of meters of cosmic ray-altered crust, ices remained pristine. Ices that had never been warmed since the object was ejected from its home system. As heat penetrated downward in microscopic amounts, volatile molecules began to vibrate within their crystalline structures. They gained energy. Some transitioned from solid to gas. At these vast distances from the Sun, only the most volatile ices respond: carbon monoxide, nitrogen, and perhaps carbon dioxide. Water remains solid. Methane stays locked in the matrix. But the most delicate ices awaken early, long before the object becomes visible to telescopes. In the early phases, sublimation does not break through the crust. The overlying layers are too thick, too strong. Instead, gases accumulate in tiny pockets, trapped beneath a rigid shell. Pressure grows. The pockets expand. Some fissures widen. Dust grains shift. But nothing is released yet, not visibly. However, the internal structure is changing. If one could travel back in time and observe 3I Atlas during this phase, if one could hover silently in the darkness and examine the object through instruments sensitive enough to detect microscopic movements, one would see subtle signs of awakening. The crust would show fine, shallow cracks forming. Dust grains on the surface might begin to shift under electrostatic forces. A faint halo of charged particles, influenced by the solar wind, might form around the object. But to Earthbound observers, the object was still entirely invisible. The first glimmers of activity continued their slow growth as the object accelerated under the Sun's gravity. Its velocity increased. Its path curved inward. The sunlight grew stronger. The crust warmed further. And eventually, the internal pressure reached a threshold. Gas began escaping through weak points. These weak points were small, nanometer-sized channels, microfractures, or pores left over from ancient radiation damage. Gas seeped through them in microscopic quantities. The molecules moved outward into space. Some carried tiny dust grains with them, grains so small that they floated in the solar wind like motes of smoke. These grains formed a cloud around the object, though far too faint to see. This cloud represented the earliest form of the coma. In this stage, the coma is not a dramatic halo of gas and dust like those seen around bright comets. It is a barely there envelope, a structure detectable only by how it changes the scattering of sunlight in the immediate vicinity of the nucleus. The dust may alter brightness by a fraction of a percent, far below the detection threshold of ground-based surveys at such distances. But the physics had begun. The coma also marks an important internal change. Once gas begins to escape, the pressure under the crust decreases. This causes additional cracks to form. More gas moves upward. The process feeds itself, expanding the pathways for sublimation. The escape of gas also produces a tiny thrust, changing the rotation of the object in imperceptible ways. Over long periods, these microjets can alter the spin axis. For 3I Atlas, any such effects were far too minor to detect from Earth, but they contributed to the evolving behavior of the object. Meanwhile, solar radiation continued to influence the dust surrounding the object. Photons imparted momentum. The faint cloud of dust became elongated in the direction opposite the Sun. The earliest structure of a dust tail was forming, still far too weak to detect, but physically present. The object now existed in a transitional state, no longer dormant, not yet fully awake. somewhere between deep frozen silence and a measurable cometary state. This is the region of space where interstellar comets begin to reveal their true nature. The structure of the crust, the type of volatile ices buried within, and the thickness of the irradiation mantle all play roles. Some interstellar objects may never show visible comet if their surfaces are too hardened. Others may erupt violently if their crusts are thin. 3I Atlas fell somewhere in the middle, active but subdued. Another effect of warming is internal stress. When the outer layers expand from heating while the deeper layers remain cold, mechanical stresses form. These stresses can cause fracturing. Each fracture becomes a gateway for sublimation. Gradually, the internal pressure can overcome the strength of the crust in certain regions. A crack forms, gas rushes out, dust follows. The coma expands. Still, at these distances, such events remain subtle. It takes extensive warming to drive significant sublimation. The sun's heat increases as the object approaches, and the rate of sublimation follows an exponential curve. Therefore, the first stages of activity are barely noticeable, but they matter. They are the beginning of the visible transformation that will eventually announce the object to observers on Earth. By the time 3I Atlas crossed into the region near Saturn's orbit, the coma likely existed in a faint but measurable form. Gas was escaping steadily through numerous microscopic fissures. Dust was being lofted slowly. The halo of escaping material had grown, though still only detectable to the most sensitive telescopic surveys equipped with digital stacking techniques. The object had begun its metamorphosis from a silent wanderer into an active visitor. Another important factor in early activity was rotational heating. As the object rotated, different sides were exposed to sunlight. This produced thermal cycles, day and night periods, that caused repeated expansion and contraction of the crust. These cycles weakened the surface further and opened new fissures. Slowly, the object became more porous.
Slowly, its interior became more connected to the surface. Slowly, the coma grew. All of this went unnoticed by humanity. The telescopes were waiting. The detection networks scanned thousands of square degrees of sky. The surveys collected millions of images. But 3I Atlas remained too dim, too small, too far. Only when it crossed the threshold where sublimation began producing enough dust to brighten the object did the first photons reach Earth's instruments in detectable numbers. Those first glimmers of activity were the foundation for a brief moment of discovery. They were the signs that a distant interstellar traveler, unseen for ages, was beginning to step into the light. There comes a moment in the journey of every comet, whether born in the solar system or in the far reaches of another star system, when the sunlight reaches an intensity that transforms silence into activity. For 3I Atlas, this moment occurred as it approached the region inside the orbit of Saturn. It was here that the once frozen interior began to awaken in earnest, driven by the strengthening light of the sun. The awakening is not dramatic at first. It has no explosive eruption, no sudden jetting, no blazing cometary display. Instead, it begins with a slow, gentle release of the most volatile molecules buried beneath the crust. These molecules, carbon monoxide, carbon dioxide, perhaps nitrogen compounds, respond to even small increases in temperature. They begin to sublimate in volume sufficient to break through the hardened outer layers. The crust of 3I Atlas, darkened by cosmic radiation over millions of years, had become a formidable shield. But even the strongest shield weakens under repeated stress and heat. As the object rotated, sunlight warmed and cooled the surface on daily cycles. These cycles amplified existing fractures. Small cracks widened. New microfissures formed. Eventually, some of these cracks extended deep enough to reach ices that now sat at temperatures warm enough to sublimate. Sublimation begins slowly, but in space, slow processes accumulate. Gas molecules escaped through fissures, carrying dust grains with them. Dust that had been locked within the crust for ages now drifted outward. Dust that had formed through radiation chemistry, dark, fine, carbon-rich material, became suspended in the near-object environment. These grains scattered sunlight, creating a faint haze. This haze grew thicker with time as the object moved inward. From the perspective of an astronomer on Earth, the object was still invisible. The brightness was too faint, but the changes were real. In this stage, the coma began to take shape, not as a dramatic halo, but as a thin layer of dust and gas forming around the nucleus. The solar wind interacted with the earliest escaping gases. Charged particles collided with molecules, ionizing them. These ions then responded to the solar magnetic field, moving outward along predictable paths. The earliest formation of an ion tail, though extremely faint, may have begun here, unseen but physically present. Another effect of the awakening was rotational modulation. As the object warmed unevenly, sublimation rates varied across its surface. Some areas produced more gas than others. This uneven activity created small jets of gas emerging at different rates. These jets imparted torque, altering the object's rotation. Over time, this could shift the spin axis slightly. For an object the size of 3I Atlas, even small jets can have measurable effects. These changes influenced which parts of the surface received sunlight and how heat was distributed. Portions of the crust that had remained stable for millions of years now entered cycles of warming and cooling that forced internal changes. The object became more dynamic, not in motion through space, but in its internal structure and surface processes. As the warming continued, the dust coma thickened. More grains were lifted from the surface. Some grains drifted away immediately, pushed by sunlight. Others lingered, forming a cloud around the nucleus. The density of this cloud increased, becoming sufficient to alter how light escaped from the region around the object. These changes set the stage for detectability. Once the coma grew dense enough, the object's brightness increased. It was no longer merely reflecting sunlight from its surface. It was scattering sunlight through its surrounding dust. This scattering made the object appear larger and brighter than the nucleus alone. Meanwhile, deeper layers of the crust began responding to the increased temperature. Larger-scale fractures formed. Sublimation of carbon monoxide intensified. The internal pressure began to rise in pockets and cavities. Eventually, some of these cavities burst, releasing gas more rapidly. These events, though not explosive, contributed to brief increases in dust production, micro-outbursts that may have produced spikes in brightness on timescales too short for current detection systems. It was during this stage that 3I Atlas transitioned from a dormant traveler to an active cometary body. It became part of a category of objects that awaken slowly under the distant influence of sunlight. Interstellar comets often behave differently from solar system comets. Their surfaces are tougher, their crusts are thicker, their ices are more deeply buried. This was true for 3I Atlas as well. Its activity was recognizable but faint, consistent with an object that had not been warmed in billions of years. Another important factor in the awakening was the increased influence of solar radiation pressure. As the object moved inward, the pressure from sunlight increased. The dust surrounding the object responded to this force. Fine grains moved outward quickly, forming the earliest visible component of a dust tail. Larger grains remained closer, contributing to the inner regions of the coma. These dynamics shaped the early structure of the dust environment, shaping how the object would appear to telescopes once it entered the detectable range. The dust also acted as insulation. Dust grains in the coma could re-radiate heat toward the surface, creating feedback effects that warmed the nucleus further. Though subtle, these effects contributed to the acceleration of activity. Meanwhile, sunlight began to reveal the coloration of the dust. The dust was likely dark, reddish or brown, due to organic molecules formed through cosmic ray exposure. This coloration, though invisible at great distances, would later influence how the object was classified.
By the time the object reached the region near Jupiter's orbit, the coma had grown large enough that the object's brightness increased by several magnitudes. Still faint, but no longer invisible. It became detectable to wide-field surveys under the right conditions. The awakening under distant sunlight was nearly complete. The object had transformed from an unlit shard drifting silently for ages into a faint but active comet. Its behavior now aligned with the physics of sublimation, dust lifting, and solar interaction. It was no longer only a wanderer. It was becoming a participant in the dynamic environment of the inner solar system. This awakening is what allowed humanity to see it. Without these early signs of activity, 3I Atlas might have passed through the solar system entirely undetected, fading back into interstellar darkness. But it did awaken, it did brighten, it did begin to speak through the language of dust and gas. And soon, telescopes on Earth would hear that whisper. Before 3I Atlas could become a subject of scientific discussion and speculation, before it could be classified as an interstellar visitor, before it could be given a name that signified its status as the third discovered object from beyond the Sun, it had to be seen. That moment of first detection, quiet, uncelebrated, unnoticed by most of the world, was the pivot point between anonymity and recognition. It was the moment when an object that had traveled through the galaxy for ages finally became known to humanity. The discovery came from the ATLAS survey, the Asteroid Terrestrial Impact Last Alert System, designed not to find interstellar objects, but to identify objects that might one day collide with Earth. ATLAS scans the sky constantly, wide-field, automated, watching for any point of light that moves in ways inconsistent with the background stars. It was created as a planetary defense system, built to protect the Earth from potential hazards. Yet, like other survey systems, it contributes enormously to the catalog of comets and asteroids, revealing dozens or hundreds each year. Its design is simple. Look at large areas of the sky, scan them frequently, and detect moving objects based on how their brightness and position change across successive images. It is not the most sensitive system. It does not reach as deep as the world's largest telescopes. But its strength lies in its constant vigilance and its ability to catch objects that brighter, more targeted observations might miss. 3I Atlas entered the detectable zone quietly. By the time Atlas first imaged it, the object had already begun producing a faint coma. That coma, though extremely subtle, increased the object's brightness beyond what would be expected for a bare nucleus of its size. That slight brightening made detection possible. Without it, the object might have passed unnoticed, lost to the background. On the night of detection, Atlas was doing what it always does, taking frames of the sky, one after another, then running them through an automated detection pipeline that searches for anything that moves. The system flagged a faint source just above the detection threshold, moving slightly between frames. The displacement was tiny but measurable, enough to identify it as a solar system object or something moving through the solar system. At first, there was nothing remarkable about the detection. The object appeared faint, with no obvious tail. Its motion was slow, suggesting it was distant. The initial classification was simply that it was a new comet or asteroid, one of the routine finds that surveys log each week. Atlas does not know what it sees. It simply records light, compares images, and lets astronomers decide what to do next. A human had to confirm the detection. An astronomer reviewing the flagged candidates noted the faint movement and added the object to the list of new detections to be shared with the Minor Planet Center. From there, the process moved through established channels: initial astrometry, provisional designation, calls for follow-up observations. At this stage, the object was still anonymous, its interstellar nature completely unknown. Even in those first few images, subtle hints were embedded within the data. The brightness did not perfectly match a point source. It was slightly fuzzier, slightly more extended, consistent with a faint coma.
But such subtle signs could be caused by atmospheric distortion, telescope optics, or numerous other factors. No one suspected anything unusual. Only after follow-up observations began did astronomers realize something surprising. The object was brighter than expected for its apparent size. Its brightness changed slightly from night to night. This indicated activity, sublimation, dust production, or surface processes caused by heating. It was behaving like a comet. That discovery shaped how astronomers modeled its orbit. Treating the object as a comet allowed them to consider possible non-gravitational forces, small accelerations caused by outgassing jets. These forces, though tiny, influence the orbit. For long-period comets from the Oort cloud, these effects can be essential for accurate predictions. But in the case of 3I Atlas, even after accounting for non-gravitational forces, something didn't fit. The orbit appeared too open, the eccentricity too high, the velocity too large. It was not bound to the Sun. At first, this conclusion was treated cautiously. Errors in early astrometry can make orbits appear hyperbolic when they are not. Comet C 1980E1, for example, appeared hyperbolic until its orbit was refined. Many comets show eccentricities slightly above 1 when activity interferes with measurements. So astronomers waited, more observations were taken, more positions recorded, the orbit refined with each new set of data. Night after night, the numbers grew clearer. The eccentricity was not slightly above 1, it was significantly above 1, too high for any solar system comet, too high to be a product of planetary scattering. The velocity relative to the Sun was excessive. It retained too much speed even at great distance. Gradually, the community realized what they were looking at. This was not just a comet. This was not a typical new discovery.
This was an interstellar object, the third ever confirmed. Atlas had detected something extraordinary, an object that had come from another star's planetary system, awakened under the distant sunlight of ours, and revealed itself just long enough to be seen. But the discovery meant something more profound. It demonstrated that interstellar objects were not rare outliers, not cosmic accidents. They were common enough that a survey like Atlas, designed for entirely different purposes, could find one simply by continuing to observe the sky. It showed that our solar system is not isolated. It is part of a galaxy filled with wandering relics of other worlds. The detection of 3I Atlas was not just a moment of recognition for a single object. It was a confirmation of a much larger cosmic truth. Interstellar visitors are out there, moving through the galaxy in great numbers. And now humanity had detected another one. Once Atlas detected the object and astronomers began taking follow-up observations, the scientific process entered a phase of uncertainty and confusion. This is common in the early days of a newly discovered object. Data are sparse. Interpretations vary. The object's brightness is unstable. The orbit is poorly constrained. Every new image changes the model slightly. And when something unexpected appears, confusion only grows. For 3I Atlas, confusion began immediately. The earliest observations showed the object to be faint, with a slightly fuzzy appearance, suggestive of a cometary coma. But the fuzziness was subtle. It could have been an imaging artifact. It could have been poor seeing. It could have been a minor processing issue. Astronomers debated quietly among themselves. Was this a comet, or an asteroid with a slightly extended profile, or simply a point source blurred by atmospheric distortion? The brightness variation from night to night complicated matters. Comets brighten as they approach the Sun, but they do so in predictable ways. 3I Atlas brightened, but not quite as expected. The changes were inconsistent with models of typical long-period comets. They were too subdued. Then came the orbit. The first orbit solutions suggested a hyperbolic trajectory, but astronomers know that early orbital solutions are unreliable. Many normal comets appear hyperbolic in the early data.
A slight mismeasurement, a faint coma affecting centroid detection, or non-gravitational forces can all distort initial calculations. But as more observations came in, the hyperbolic nature did not disappear. It became more certain. That created a new problem. If the object was hyperbolic, what kind of hyperbola was it? A hyperbolic caused by planetary scattering, or a hyperbolic caused by interstellar velocity? This distinction mattered enormously. To explore the first possibility, astronomers simulated potential encounters with Jupiter, Saturn, and even Neptune. Could the object have been an Oort cloud comet kicked into a hyperbolic path by a giant planet? Could recent interactions explain its excessive speed? Simulations showed this to be nearly impossible. No recent encounters could impart the required velocity. The geometry was all wrong. The object could not have originated in the solar system. Still, many resisted the interstellar interpretation at first. Interstellar objects are rare. Extraordinary claims require extraordinary evidence. Some suggested that the brightness variations could be confusing the orbital calculations. Others argued that more data were needed before drawing conclusions. Meanwhile, the behavior of the object raised new questions. Its coma was faint. Its activity was subtle. Its brightness curve did not match typical solar system comets. It looked like an object with a hardened irradiation mantle. It looked like something long exposed to cosmic rays. It looked like Oumuamua and Borisov, not identical, but similar in the way interstellar objects tend to be similar. These behavioral clues strengthened the interstellar hypothesis. As astronomers collected more images, they noticed something else unusual. The object's light curve showed irregularities, brightness fluctuations that suggested rotation or surface asymmetry. But these irregularities were small, barely above the noise threshold. Some nights it brightened slightly more than expected. Other nights it dimmed. These variations could be caused by activity, rotation, or dust release. But the faintness made it difficult to distinguish between these possibilities. The early confusion reflected the limits of observation: a faint object, a moving target, a barely detectable coma, sparse data, uncertain models. All these contributed to an atmosphere of cautious excitement. Then came the turning point. The orbit solution stabilized. The excess velocity remained high. The hyperbolic eccentricity remained too great for solar system origins. The direction of approach was inconsistent with any scattering event. The brightness behavior matched expectations for a deeply processed ancient comet. At this point, the confusion began to dissipate. Astronomers realized they were observing something rare and extraordinary, something that required no special pleading, something that fit the data cleanly. 3I Atlas was interstellar, not merely hyperbolic, but decisively so. Not merely unusual, but indicative of a universe where countless frozen objects drift between the stars. Yet the early confusion had served a purpose. It forced astronomers to rule out every alternative. It ensured that the conclusion was based on evidence, not excitement. It demonstrated the difficulty of distinguishing interstellar objects from solar system objects in the earliest stages of observation. And in doing so, it reinforced a deeper truth. Interstellar visitors are subtle. They do not announce themselves with great drama. They arrive faint, quiet, nearly invisible. Only careful study reveals their nature. The early data were confusing because the object itself was a paradox. Active but faint, cometary but subdued, hyperbolic but not too hyperbolic. This subtlety is what makes interstellar objects difficult to detect, and what makes their discovery so scientifically valuable. 3I Atlas slipped into the solar system unnoticed for most of its journey. It awakened slowly. It brightened hesitantly. It revealed its nature reluctantly. But eventually, astronomers understood. The confusion cleared, the data aligned, and the object that Atlas first recorded as a faint smudge of moving light became the third confirmed visitor from the stars.
Once astronomers confirmed that 3I Atlas was not merely hyperbolic, not merely unusual, not merely cometary, but undeniably interstellar, a new and profound question emerged from the observations. If this tiny, faint, reluctant visitor could slip into the solar system almost unnoticed, how many others have already done the same? How many interstellar wanderers passed through before surveys like Atlas existed? How many are passing through right now, invisible in the darkness? How many lie just beyond our current detection threshold, waiting silently to be discovered? It is a question that reshapes the scientific understanding of the solar system's place in the galaxy. Because the answer is simple, startling, and unavoidable. We are surrounded by interstellar objects all the time. But how many? To answer that, astronomers begin by looking at the statistics of detection. The logic is straightforward. If two interstellar objects, Oumuamua and Borisov, were detected within just a few years, and now 3I Atlas adds a third, then the galaxy is not sparse with visitors. Instead, it must be full of them. Detection is rare not because the objects are rare, but because our surveys have only recently become sensitive enough to notice such faint wanderers. Most of them pass unseen. The vast majority are too small, too dark, too inactive, or too distant to be caught by existing telescopes. Imagine trillions of tiny shards, fragments of long-dead planetary systems, drifting through the galaxy like dust motes floating in an immense cosmic shaft of light. Most never come close enough to the sun to awaken. Most remain frozen, unilluminated, unremarkable. Even those that do pass close enough might only brighten slightly, insufficient for detection unless a survey happens to capture them at the perfect moment. To estimate how many interstellar objects pass through the solar system, astronomers rely on a combination of models, population statistics, and the known density of material in the galaxy. The calculations vary, but they all converge on a startling conclusion. The number of interstellar objects drifting through the solar system at any given moment is enormous. One widely accepted estimate suggests that at least one interstellar object larger than a meter passes within Earth's orbit every year. That means that somewhere in the space around us, within the same region traversed by spacecraft, there could be dozens of foreign objects at this very moment, drifting silently, overlooked by telescopes that are not searching deep or fast enough to catch them. Expand that to the region within Jupiter's orbit, and the number grows vastly larger. Expand to the region within Neptune's orbit, and the number increases again. Expand outward to the boundary of the heliosphere, and the population becomes staggering. Some models suggest that millions of interstellar objects, from pebble-sized to city-sized, exist within the reach of the sun's gravity at any given time. They drift through on long, sweeping hyperbolic paths, entering and departing without ever being seen. Consider this. If Oumuamua had been just 20% smaller, we might never have detected it. If Borisov had been slightly less active, it might have remained hidden. If 3I Atlas had not produced even a faint coma, Atlas would never have found it. The fact that we detected 3I Atlas at all suggests that there are countless others just like it, slightly fainter, slightly darker, slightly more distant, that slip by undetected. Another reason many go unseen is their speed. Interstellar objects move swiftly relative to the sun. They cross the inner solar system in months, not years. If a survey does not catch them in that brief window, they disappear forever. And then there is the size distribution. Most interstellar objects are small, fragments of asteroids or comets, broken off during collisions, ejections, or planetary migrations in their home systems. These objects may be meters or tens of meters across. Modern telescopes can detect objects that small only when they are extremely close to Earth, and even then, detection is not guaranteed. The darkness of their surfaces compounds the difficulty. A crust shaped by cosmic radiation becomes pitch black, absorbing most of the sunlight rather than reflecting it. a small dark object against the backdrop of the cosmos becomes nearly invisible. So the number of interstellar objects is enormous, but the number detectable with current technology is tiny. We are not seeing a representative sample. We are seeing only the brightest, most fortunate objects, the ones whose activity reveals them through dust coma or whose size and reflectivity allow detection. The galaxy around us is far busier than it appears. There is another factor to consider. The solar system moves through the galaxy. It plunges through different environments, spiral arms, and star-forming regions. It encounters drifting clouds of debris from other systems. It passes through tidal streams left behind ancient star clusters. At different points in its galactic orbit, the density of interstellar objects around the solar system may increase or decrease. Right now, we might be in an average region, or perhaps even a sparse region. In the past, we may have traveled through areas teeming with debris from young, unstable planetary systems. The Earth may have been hit by interstellar objects throughout its history. Some models suggest that a significant percentage of small meteorites could be interstellar in origin, undetectable as such because the high-speed entry destroys the evidence. Others propose that interstellar dust has been falling on Earth for billions of years. If this is true, then we may have walked unknowingly on fragments of distant worlds. But for larger bodies, the statistics become clearer. The detection of 3 interstellar objects in such a short time indicates that interstellar comets and asteroids are common. The only reason humanity didn't know until recently is that our telescopes were not sensitive enough. And the simplest, most elegant conclusion emerges from all this. Interstellar visitors are not rare. Our ability to detect them is rare. The night sky is full of wanderers. The solar system is full of unseen guests. The galaxy is a vast ocean, and we are only now learning to spot the first few ships passing over the horizon. With this realization, astronomers turn their attention to a new frontier. If the sky holds countless unseen visitors, how do we find them? What instruments will reveal them? What technology will bring the hidden majority into view? The answer lies in the next leap in observational power. The discovery of 3I Atlas, faint, distant, subtle, revealed a crucial truth. The limits of detection, not the scarcity of interstellar objects, determine how many we see. For decades, humanity has detected only the brightest, closest, or most active visitors. The rest pass unseen. But that era is ending. A new generation of telescopes is rising, and with it, the understanding of interstellar objects will transform. The telescope that promises the biggest revolution is the Vera C. Rubin Observatory, housing the LSST, the Legacy Survey of Space and Time. No single instrument has ever been designed to survey the sky with such breadth, speed, and depth. Once operational, LSST will scan the entire visible sky every few nights, capturing billions of sources, tracking their motions, and identifying faint moving objects that current surveys cannot see. To understand what LSST will do, one must first appreciate its design. Its mirror is exceptionally wide. Its camera is one of the largest ever built. Its field of view is enormous, able to capture an area of the sky the size of dozens of full moons in a single exposure. Its sensitivity reaches magnitudes far beyond those of Atlas or Pan-STARRS. And its survey cadence, the frequency with which it revisits the sky, ensures that fast-moving objects will not be missed. LSST will not merely detect interstellar objects. It will reveal a population. For the first time, astronomers will have instruments capable of catching faint intruders at much greater distances, before their coma awaken, before they brighten, before they reach the inner solar system. Objects like 3I Atlas will be discovered earlier, tracked more accurately, and studied more thoroughly. Some models predict that LSST could detect one interstellar object every year. Others predict one every few months. Optimistic projections suggest dozens per year, hundreds over a decade. This is not speculation, it is the logical consequence of improved sensitivity and faster sky coverage. LSST will not be alone. Other telescopes will contribute to this new era. New survey systems, both ground-based and space-based, will fill in the gaps. Infrared observatories will detect dark, cold intruders invisible to optical systems. Radar systems may one day track fast-moving interstellar meteors entering Earth's atmosphere. Even amateur astronomers, equipped with increasingly powerful and affordable instruments, may contribute unexpected discoveries. But LSST remains the centerpiece, the instrument that will change everything. Beyond LSST, next-generation space telescopes will deepen the revolution. NASA's upcoming missions, ESA survey programs, and private telescopes funded by new research initiatives will provide new wavelengths, new sensitivities, and new methods of detecting faint objects. Infrared telescopes will detect warm dust associated with early cometary activity. High-resolution instruments will characterize coma and tails at unprecedented distances. Autonomous sky survey networks will find objects that move too quickly or too faintly for traditional single telescope systems. The rise of machine learning will complement these efforts. Automated algorithms will sift through billions of observations, flagging moving targets that human observers would never notice. Neural networks will identify hyperbolic trajectories in real time. Data pipelines will compare motion patterns against known solar system populations, elevating unusual candidates for rapid follow-up. The combination of wide-field surveys, advanced computational tools, and high-sensitivity imaging will create a detection ecosystem fundamentally different from anything humanity has had before. For interstellar objects, this means something profound. The age of accidental discovery is ending. The age of deliberate detection is beginning. With better telescopes, humanity will not merely stumble upon interstellar visitors by chance. We will expect them. We will anticipate them. We will identify them early, track them precisely, and study them in detail before they depart. This changes the scientific possibilities dramatically. We will be able to measure the activity of objects like 3I Atlas from farther away. We will identify faint coma early. We will track light curves with higher fidelity. We will analyze colors and compositions in greater detail. We will observe hyperbolic trajectories with unmatched precision. We will characterize shapes, rotations, and thermal properties. We might even, within a few decades, intercept one. The idea of sending a spacecraft to an interstellar object has long been considered impractical. These visitors move quickly, and their approach is unpredictable. But a telescope like LSST changes that. Early detection means early planning. Early planning means potential intercept trajectories become feasible. Ambitious mission concepts already exist for rapid response probes, long-duration chasers, or even pre-positioned spacecraft waiting for a suitable target. The future could include the first sample return mission from an object born under another star. All of this, every discovery, every intercept, every measurement, begins with improved detection. 3I Atlas required just enough activity to be seen. Future visitors will not need such luck. The next generation of telescopes will find them regardless. The transformation will be sweeping. The number of known interstellar objects will rise. The diversity of their forms will become clearer. The understanding of planetary system formation across the galaxy will deepen. Humanity is standing at the threshold of a new observational era, one in which the sky will reveal secrets it has always held but never before shown. And the first to benefit from this new age will be the study of interstellar wanderers. Once the realization settled that 3I Atlas was not an isolated curiosity, but instead a member of a vast, unseen population of interstellar wanderers, astronomers began to understand that the discoveries of the past few years represented not the emergence of a rare phenomenon,
but the first droplets of a much larger cosmic rainfall, a rain that has been falling onto our solar system for billions of years, unnoticed and unmeasured, and which is now, thanks to new technologies, beginning to reveal itself with increasing clarity.
The notion that Oumuamua was a once-in-a-century occurrence, that Borisov was an extraordinary stroke of observational fortune, or that 3I Atlas represented a statistical outlier quickly dissolved when scientists began to model the density of interstellar material and the likelihood of detection. The truth, once the numbers were laid out plainly, was overwhelming. We are living in the early moments of what will soon become a flood of detected interstellar visitors, an era in which objects from other stars are identified not every few years, but perhaps every few months or even every few weeks, as our instruments grow more sensitive and our sky surveys more comprehensive. And this concept, this dawning realization that the galaxy has been gifting us a steady flow of messengers from distant systems, and that only now are we learning to see them, has reshaped not only the expectations of astronomers, but also the entire field of planetary science. For it hints that every star that ever formed planets has been shedding fragments into the cosmos, scattering them across the Milky Way like seeds carried by a cosmic wind. One of the most compelling reasons scientists expect a coming flood of discoveries lies in the simple fact that the solar system does not sit still in the galaxy. It orbits the galactic center, circling once every few 100 million years. During this immense journey, the solar system plunges into spiral arms, drifts through zones of dense star formation, sweeps through regions thick with molecular clouds, and passes by clusters of young stars whose planetary systems are still settling into equilibrium. Each of these environments contains debris, billions upon billions of fragments, each the relic of collisions, ejections, disruptions, or gravitational instability in star systems throughout the galaxy. The solar system is not moving through empty space. It is moving through a cosmic river of material, and interstellar objects like 3I Atlas are simply those fragments that happen to cross our own gravitational domain. But another, even more transformative insight emerges when one considers the statistical consequences of our improved detection abilities. For decades, astronomers lacked the tools to see faint, fast-moving objects that enter the solar system on steep hyperbolic trajectories. Most interstellar objects are small, perhaps only tens of meters across, and nearly black, with surfaces darkened by cosmic radiation over unimaginably long spans of time. These objects reflect very little light, making them virtually invisible until they pass close to the sun. And even then, most are too faint to detect. Only objects that either come very near Earth or produce a coma bright enough to amplify their reflectivity can be found by surveys like Atlas or Pan-STARRS. This means that the interstellar objects we have detected so far, Oumuamua, Borisov, and 3I Atlas, represent the very brightest, very largest, or most active members of an enormous hidden population. They are the tip of a submerged mountain, the visible peaks rising above an ocean of darkness, offering only the faintest hint of the mass that lies below the surface. When astronomers simulate the true population based on how seldom such bright peaks are seen, the numbers veer upward into staggering territory. For every interstellar object we detect, there may be tens of thousands passing unnoticed. Some drift through the solar system's outskirts and leave without ever awakening. Others glide through the region inside Jupiter's orbit but remain too small to brighten. And countless more intersect the sun's gravitational sphere but never approach the inner regions where humanity's instruments can find them. The flood is coming not because more interstellar objects are suddenly appearing, but because our capacity to see them is increasing at a pace that far exceeds anything in the past. The Rubin Observatory's LSST will be the catalyst, scanning the sky repeatedly, capturing faint intruders years before they reach perihelion. But LSST is only the beginning. Infrared telescopes in space, proposed and under development, will reveal dark, cold objects that optical surveys miss entirely. Dedicated interstellar object detection algorithms trained on near real-time data streams will catch faint traces of hyperbolic motion that would elude human observers. Networks of automated telescopes will watch the sky continuously, cross-referencing observations from multiple continents. The night sky will no longer be static. It will become a dynamic, constantly updated map of moving objects, each cataloged and classified with unprecedented precision. In such a world, the discovery of 3I Atlas will no longer be a rare event, but a common one of many interstellar visitors cataloged each year. Some of these will be large enough to study in detail, revealing their composition, behavior, and structure. Others will be tiny, mere boulders or ice fragments drifting through the solar system unnoticed except for a handful of tracking points on a digital sky map, their presence known only in data archives. Still others may be extraordinary, fragments of exoplanets shattered during collisions, orphaned moons wandering through interstellar space, or frozen relics from ancient systems that formed before the Sun existed. In time, the flood of discoveries will reveal the diversity of worlds beyond our own, not through the indirect methods of exoplanet transit curves or radial velocity measurements, but through physical samples, drifting freely into our star system, waiting to be studied. Imagine a future in which astronomers receive alerts daily, alerts announcing the discovery of new hyperbolic objects streaking into the solar system. Some may exhibit cometary behavior. Others may look like asteroids. Some may arrive in clusters, suggesting a common origin. Others may show unusual colors or spectral signatures, hinting at exotic material or unique formation environments. Each discovery expands the catalog. Each object becomes a data point in a growing map of galactic debris. Each visitor tells a story of its origin, its ejection, and its long journey through the galaxy. The coming flood will reshape our understanding of the Milky Way. It will blur the boundaries between planetary systems. It will reveal that stars exchange material far more frequently than anyone imagined.
It will show that planetary fragments drift freely, that collisions leave echoes across light years, and that every star contributes to a shared galactic ecosystem. And in this new age of discovery, the solar system will no longer feel isolated. It will become a crossroads, a place where countless ancient travelers pass, carrying with them the histories of worlds we will never see directly. A place where wanderers from other suns brush past ours, just close enough for us to glimpse their presence before they fade back into the depths of interstellar night. The flood is not coming. It has already begun. We are only now learning how to see it. When the first interstellar object, Oumuamua, was discovered in 2017, the scientific community trembled with surprise. Not because astronomers had never theorized such visitors could exist, but because the concept had always hovered in the realm of speculation rather than expectation. Before Oumuamua, the idea of discovering material from another star system drifting through ours felt more like a remote possibility than a practical field of study. After all, if such objects were passing through with any regularity, why had none been seen before? And so, when that first elongated, tumbling shard of cosmic history swept past the Sun and departed in a matter of weeks, the encounter felt like a fleeting miracle, something astonishing but perhaps unique. But then came Borisov, active, cometary, unmistakable in its interstellar speed, and suddenly two miracles had arrived barely 2 years apart. Then came 3I Atlas. With each new discovery, the sense of rarity faded, and a new understanding took its place. The galaxy is filled with interstellar debris, and the solar system is bathed in a steady rain of visitors from other stars. The scientific community realized that the detection of interstellar objects was not a coincidence, but the beginning of a pattern. And patterns, once recognized, become fields. Thus began the birth of a new branch of planetary science, the study of interstellar objects as a discipline in its own right. a field concerned not merely with finding these visitors, but with understanding their origins, compositions, behaviors, and implications for the evolution of planetary systems across the galaxy. The development of this field was not instantaneous. At first, researchers struggled to understand how to categorize these objects. Were they comets? Were they asteroids? Were they something else entirely? Something shaped by the chemistry and dynamics of alien systems? The answer, it turned out, was not simple. The diversity of objects arriving from other stars would likely mirror the diversity of objects within the solar system, but with differences born from foreign formation environments, unfamiliar radiation histories, and long exposure to cosmic forces. Scientists quickly realized that interstellar objects represented something unique, samples of exoplanetary systems delivered directly to our doorstep, requiring no spacecraft, no interstellar missions, no technological leaps. While space agencies were designing dreams of far future probes that could one day journey to nearby star systems on century-long voyages, the galaxy was already offering material from those very systems, drifting freely into our observational reach. With this realization, researchers began organizing conferences, forming working groups, publishing new models, and creating frameworks to classify these objects. Workshops on interstellar bodies began to appear in planetary science meetings. Students pursued doctoral theses on hyperbolic trajectories, cosmic ray processing of small bodies, and the statistical distribution of interstellar debris. What had once been a curiosity became a topic. What had once been a topic became a specialty. The study of interstellar objects became a bridge between multiple fields: astronomy, planetary science, astrochemistry, cosmochemistry, orbital dynamics, exoplanet research, and stellar evolution. Each interstellar visitor became a lens through which scientists could peer into the processes that shape planetary systems elsewhere in the galaxy. Each spectral measurement, each dust analysis, each observation of activity became a data point for understanding worlds we could never visit directly. Soon, theoretical models blossomed. Researchers simulated planetary ejections from sun-like stars, red dwarfs, young systems still enshrouded in gas, and ancient systems nearing the end of their stellar lives. They modeled how fragments drift through the galaxy, how galactic tides shape their paths, how collisions alter their surfaces, and how cosmic radiation transforms their chemistry. They explored how the solar system's motion influences the arrival rate of interstellar objects, and how the structure of the Milky Way determines their distribution. Laboratories began to synthesize materials thought to resemble interstellar ices, simulating the effects of billions of years of cosmic ray exposure. These experiments aim to predict how interstellar objects might behave as they warm near the sun, how their surfaces break down, and how their comas form. The results helped interpret the behavior of objects like 3I Atlas, revealing that cosmic ray-induced crusts can be thick, strong, and insulating, suppressing early activity and shaping how these visitors brighten as they approach the sun. The field grew further when researchers realized that interstellar objects could hold clues to the origins of life. If fragments of planets or protoplanetary disks drift between stars carrying organic molecules formed elsewhere, then the ingredients of life may be exchanged across the galaxy. This possibility, once considered fringe, became a serious topic of research, supported by laboratory evidence, observational data, and theoretical models. Some suggested that interstellar objects might seed planetary systems with complex molecules. Others proposed that our own solar system may have ejected material that once drifted into distant star systems. The essential point was clear. Interstellar objects represent a physical connection between planetary systems, a bridge of matter crossing the vast reaches of space, a reminder that the galaxy is not a collection of isolated islands, but an interconnected ecosystem. As the field matured, mission concepts emerged. Space agencies began to explore the idea of sending probes to interstellar objects, collecting data directly, and analyzing their composition. Some concepts involved fast launch vehicles capable of responding within months to a new detection. Others proposed pre-positioned interceptors waiting on standby in solar orbits, ready to chase down a newly discovered visitor. A few even imagined long-duration missions that would follow interstellar objects far beyond the solar system, studying them for decades. This was no longer science fiction. It was an emerging field, a discipline born from curiosity, shaped by technology, and propelled by the urgent desire to understand our place in the galaxy. From curiosity came questions. From questions came theories. From theories came a new science. Interstellar object research is no longer a novelty. It is a frontier. And 3I Atlas is one of the stones that mark the path into this new terrain. As soon as humanity realized that interstellar objects were not rare anomalies, but frequent messengers drifting through the vastness of the galaxy, it became inevitable that strange theories and exotic ideas would begin to cluster around them, as if drawn in by the same gravitational curiosity that pulls these visitors toward the sun. Every new discovery invited speculation, sometimes grounded, sometimes wild, sometimes hovering at the boundary between science and imagination. And this pattern became especially pronounced after Oumuamua, whose peculiar shape, unusual acceleration, and complete lack of visible cometary activity ignited a whirlwind of hypotheses ranging from the deeply plausible to the utterly fantastical. Scientists, for their part, understood that such speculation was natural. After all, interstellar objects represented the first physical contact humanity had ever had with material originating from another star system. And anything that arrives from the unknown naturally invites questions about what else might be possible. But they also knew that rigorous analysis was necessary to separate the extraordinary from the merely unfamiliar, the sensational from the scientifically meaningful, and the plausible from the impossible. One of the earliest strange theories emerged around the shape of Oumuamua, whose elongated, tumbling form appeared unlike anything previously observed in the solar system. Some argued that natural processes, erosion, fragmentation, rotational flattening, or cosmic ray-induced sculpting could produce such an object, while others suggested more exotic origins, such as the possibility that Oumuamua might be a fragment of a shattered exoplanet, or the remnant of a larger body that had been stripped away over billions of years of interstellar travel. But then came the idea that captured global attention, the suggestion that Oumuamua might be artificial, perhaps a fragment of alien technology, a derelict light sail, or a probe left behind by an advanced civilization. Most scientists dismiss the notion of artificial origin as unnecessary, reminding the public that extraordinary claims require extraordinary evidence. And in the case of Oumuamua, the available evidence was far from conclusive. Yet the idea persisted, not because it was likely, but because the object's behavior was so unfamiliar, and because humans are naturally inclined to fill the gaps in their understanding with stories that feel as large as the mysteries they encounter. The universe is vast. Alien worlds exist in the thousands, and the possibility of life elsewhere is real enough that imagination will always rush into the spaces where certainty has not yet taken root. When 2I Borisov arrived, it brought clarity rather than confusion. Borisov behaved like a perfectly normal comet, bright, active, producing dust and gas in ways that matched classical cometary physics. This confirmed that interstellar comets could behave just like solar system comets, allowing scientists to anchor their expectations. But it also encouraged new speculation. If Borisov behaved so normally, and Oumuamua behaved so strangely, then perhaps interstellar objects exist in multiple categories, some resembling our familiar cometary bodies, and others containing materials or structures shaped by alien processes. By the time 3I Atlas appeared, the appetite for strange theories was stronger than ever. Some argued that its faintness and subtle behavior could indicate that it was composed of exotic ices never found in the solar system.
Others suggested that its subdued activity hinted at a crust so deeply processed by cosmic radiation that its surface chemistry might differ drastically from any comet known on Earth. A few proposed that its trajectory might indicate an origin in an old stellar population, possibly even a star that had long since ceased fusion, implying that the object could be older than the Sun itself. Inevitably, the more imaginative speculations returned as well. Could interstellar objects be fragments of Dyson spheres or megastructures? Could they be debris from extraterrestrial collisions on inhabited worlds? Could some be relic probes wandering through the galaxy, long inactive but still bearing traces of engineering? Could they serve as natural couriers of organic material, seeding life from system to system? Most of these ideas are unsupported, but not all fall into the category of fantasy. The concept known as panspermia, the transfer of life-bearing molecules between worlds, has been studied seriously for decades. Although the idea that fully formed organisms could survive interstellar journeys is considered highly unlikely, the possibility that complex organic molecules might endure such journeys is supported by laboratory experiments. Some interstellar dust contains organic compounds. Some meteorites on Earth contain amino acids formed in space. The notion that interstellar objects might carry the building blocks of life is not bizarre. It is consistent with chemical evidence and theoretical models. Still, scientists must tread carefully. It is easy to allow the extraordinary nature of a visitor from another star to inflate expectations into territory where evidence cannot follow. For every hypothesis about exotic ices or alien collisions, there must be data, spectral analysis, light curve measurements, coma composition, non-gravitational forces, and orbital histories. In the case of 3I Atlas, the evidence supports a natural origin. It behaves like a comet with a strong radiation mantle, consistent with a long interstellar journey. But the public fascination around such objects is shaped as much by what is not yet known as by what is known. The allure of strange theories highlights an important truth. Interstellar objects represent the intersection of science and wonder, where knowledge touches the edge of the unknown and imagination rushes in to fill the absence of certainty. When 2I Borisov arrived, it brought clarity rather than confusion. Borisov behaved like a perfectly normal comet, bright, active, producing dust and gas in ways that matched classical cometary physics. This confirmed that interstellar comets could behave just like solar system comets, allowing scientists to anchor their expectations. But it also encouraged new speculation. If Borisov behaved so normally and Oumuamua behaved so strangely, then perhaps interstellar objects exist in multiple categories, some resembling our familiar cometary bodies and others containing materials or structures shaped by alien processes. By the time 3I Atlas appeared, the appetite for strange theories was stronger than ever. Some argued that its faintness and subtle behavior could indicate that it was composed of exotic ices never found in the solar system. Others suggested that its subdued activity hinted at a crust so deeply processed by cosmic radiation that its surface chemistry might differ drastically from any comet known on Earth. A few proposed that its trajectory might indicate an origin in an old stellar population, possibly even a star that had long since ceased fusion, implying that the object could be older than the Sun itself. Inevitably, the more imaginative speculations returned as well. Could interstellar objects be fragments of Dyson spheres or megastructures? Could they be debris from extraterrestrial collisions on inhabited worlds? Could some be relic probes wandering through the galaxy, long inactive but still bearing traces of engineering? Could they serve as natural couriers of organic material, seeding life from system to system? Most of these ideas are unsupported, but not all fall into the category of fantasy.
The concept known as panspermia, the transfer of life-bearing molecules between worlds, has been studied seriously for decades. Although the idea that fully formed organisms could survive interstellar journeys is considered highly unlikely, the possibility that complex organic molecules might endure such journeys is supported by laboratory experiments. Some interstellar dust contains organic compounds. Some meteorites on Earth contain amino acids formed in space. The notion that interstellar objects might carry the building blocks of life is not bizarre. It is consistent with chemical evidence and theoretical models. Still, scientists must tread carefully. It is easy to allow the extraordinary nature of a visitor from another star to inflate expectations into territory where evidence cannot follow. For every hypothesis about exotic ices or alien collisions, there must be data, spectral analysis, light curve measurements, coma composition, non-gravitational forces, and orbital histories. In the case of 3I Atlas, the evidence supports a natural origin. It behaves like a comet with a strong radiation mantle, consistent with a long interstellar journey. But the public fascination around such objects is shaped as much by what is not yet known as by what is known. The allure of strange theories highlights an important...
The challenge for the public is to welcome the wonder while understanding the rigor that science demands. The scientific value of exploring exotic ideas lies not in indulging them, but in using them to expand the boundaries of inquiry. Many discoveries in the history of astronomy began as speculations that seemed unlikely at first. Black holes, exoplanets, neutron stars, gravitational waves. Sometimes strange ideas become science. Sometimes they remain fiction. But the border between them is where progress often begins. Interstellar objects sit precisely on this boundary. Fragments of distant systems, shaped by unknown environments, bearing unknown chemistries, arriving at unpredictable times, and behaving in ways that sometimes mirror our expectations and sometimes confound them. The strange theories they inspire are not threats to scientific understanding. They are invitations to explore more deeply, to test hypotheses, to refine models, and to acknowledge how much we still do not know about the galaxy that surrounds us. 3I Atlas, like its predecessors, sparked both grounded inquiry and wild speculation. And in doing so, it illuminated one of the most important lessons of this new field: that openness to unusual ideas, tempered by the discipline of evidence, is essential for navigating the frontier of interstellar research. The strange theories remind us that the universe is vast beyond comprehension. The scientific analysis reminds us that only through careful study can we understand it. Thus, interstellar objects occupy a unique place in human curiosity. They belong to science, but they invite imagination. They demand evidence, but they stir wonder. They are physical, measurable, and real, yet they whisper of unknown worlds in ways that no other objects can. Whenever an unfamiliar object enters the solar system, especially one from beyond the gravitational embrace of the Sun, a profound and often heated debate emerges, one that stretches across scientific communities and spills into public discourse. Is the object entirely natural, shaped by the same cosmic forces that sculpt comets and asteroids everywhere? Or does it bear even the faintest possibility of non-natural origin? An artifact of engineering, perhaps? Or a relic of alien technology? Or something crafted by intelligence rather than by geology and gravity alone? This debate is not simply a fascination with the idea of extraterrestrial life. It is born from the recognition that interstellar objects, by their very nature, have the potential to surprise us in ways no familiar solar system body can. Part of what fuels the debate is the novelty of the objects themselves. Humanity has spent centuries cataloging solar system comets and asteroids, developing a deep understanding of their shapes, behaviors, and compositions.
When something arrives that does not conform to those expectations, when it brightens differently, spins differently, accelerates slightly under non-gravitational forces, or appears to lack a coma despite being heated by the sun, scientists must evaluate whether their models are incomplete or whether the object represents something fundamentally different. Oumuamua became the center of this debate because its behavior did not align neatly with any known category. It appeared elongated or possibly disc-like, spun chaotically, and exhibited an unexpected acceleration that could not be attributed to a visible coma. Scientists proposed natural explanations: hydrogen outgassing, incredibly volatile ices, radiation pressure acting on a thin structure, but the absence of direct evidence kept the door slightly open for more exotic interpretations. Not because they were likely, but because the data did not eliminate them completely, and science is obligated to consider any possibility that remains consistent with observation. Borisov, in contrast, silenced most non-natural speculation by behaving exactly like a comet should. Its coma, tail, outgassing, and breakup were textbook examples of natural cometary physics. No one seriously suggested non-natural origins because nothing warranted such a leap. And this contrast between Oumuamua and Borisov shaped the next stage of the debate. Some interstellar objects will look familiar, while others may not, and it is the unfamiliar ones that challenge scientific assumptions. When 3I Atlas arrived, the debate reignited at a quieter level. It was cometary but subdued, active but weakly. Its brightness curve was irregular but not extraordinary. It showed hyperbolic motion without strange accelerations. It produced dust but not dramatically. If Oumuamua was perplexing and Borisov was obvious, then 3I Atlas occupied the middle ground. Interesting, but not anomalous enough to raise alarms or ignite sensational theories. Still, the natural versus non-natural discussion is not driven solely by anomalies. It is driven by a deeper question. How would we recognize an artificial interstellar object if one truly appeared? Would it show non-gravitational propulsion? Would it reflect light in non-random patterns? Would its shape defy geological explanation? Would it exhibit behaviors inconsistent with sublimation or radiative forces? Would it break apart in ways unlike natural fragmentation? Or would it remain silent and inert, indistinguishable from a natural asteroid until closer inspection revealed some hidden structure? These questions are not fringe, they are part of legitimate scientific inquiry, because if artificial objects exist in the galaxy, and we cannot rule out the possibility, then interstellar visitors are one of the few ways we might detect them without traveling to other stars. Scientists therefore discuss such possibilities not because they expect them, but because they must be prepared to identify them should they ever appear. But the foundation of the debate always returns to one principle. Natural explanations must be exhausted before non-natural ones are invoked. The universe is rich with physical processes that can produce surprising results. Long exposure to cosmic rays can sculpt surfaces into unusual shapes. Sublimation of exotic ices can create unexpected accelerations. Fragmentation during ejection from a distant star system can produce bodies that appear unnaturally thin, elongated, or flat. And the sheer diversity of planetary systems means that objects unlike anything in the solar system may be entirely natural elsewhere. Thus, scientists approach each interstellar visitor with caution. They examine the orbit, the light curve, the activity, the spectrum, the reflectivity, the thermal properties, and the dynamical history. They consider every model: cometary outgassing, radiation pressure, tidal disruption, rotational breakup, hydrogen sublimation, thermal fracturing, and cosmic ray damage.
Only once all natural explanations have been rigorously tested and found lacking would non-natural origins become a serious scientific consideration. The debate itself, however, serves a valuable purpose. It sharpens the reasoning of researchers. It forces hypotheses to be precise. It compels models to account for all observed behavior. It elevates the quality of analysis. And it ensures that the scientific community remains vigilant, open to extraordinary discoveries while grounded in established principles. Interstellar objects thus exist at the crossroads of curiosity and caution. They invite speculation about alien civilizations, yet demand disciplined evaluation. They fuel imaginative ideas, yet ultimately lead to deeper understanding of natural cosmic processes. The balance between these two impulses, wonder and skepticism, is what drives the field forward. In the case of 3I Atlas, the evidence points overwhelmingly toward a natural origin, shaped by processes familiar to cometary physics but influenced by the unique environment of interstellar space. There is no need to invoke artificial constructs or non-natural origins. Yet the debate itself remains relevant, for it prepares humanity for the day when a visitor arrives that cannot be explained easily, whose behavior resists classification, and whose nature forces scientists to confront possibilities far beyond anything seen before. Until that day comes, the natural versus non-natural debate will continue to weave through the study of interstellar objects, shaping how we interpret new arrivals, how we refine our models, and how we prepare ourselves, scientifically and philosophically, for whatever the galaxy may send next. Every interstellar visitor that has passed through our solar system, whether detected in our time or simply inferred through the statistical lens of astronomical modeling, has left behind a set of lessons, some obvious and immediate, others subtle and unfolding only as scientists revisit data, refine theories, and reconsider assumptions they once thought secure. These lessons do not stand apart as isolated insights. Instead, they weave together into a larger understanding of how planetary systems form, evolve, interact, and eventually shed fragments that drift into the cosmic sea, carrying with them the unmistakable signatures of their origins. As such, Oumuamua, Borisov, and 3I Atlas are not merely three isolated data points in the vastness of galactic history. They are the vanguard of a new narrative, a trilogy that reveals the diversity, complexity, and unpredictability of interstellar debris in a galaxy where no planetary system exists in true isolation. The first major lesson emerges from Oumuamua, whose enigmatic nature forced astronomers to confront the reality that their mental catalog of possible natural objects was incomplete. Its elongated shape, its non-gravitational acceleration, its silence in thermal spectra, and its lack of detectable outgassing shattered the comfortable assumption that all small interstellar bodies would behave similarly to solar system comets. Instead, Oumuamua taught us that the galaxy contains objects whose surfaces may be shaped by processes alien to our local environment. Cosmic rays baking away volatiles, intense stellar winds stripping layers of material, tidal disruptions shredding larger bodies into thin, elongated fragments, and unknown collisions sculpting geometries that no solar system survey had ever revealed. This realization was humbling. The universe contains more variation than regional experience had allowed, and our understanding must expand accordingly. The second lesson came from Borisov, which demonstrated with startling clarity that not all interstellar objects would be strange or exceptional. Borisov behaved like a classical comet in nearly every measurable way. Its coma formed predictably. Its tail responded to solar radiation in familiar patterns. Its dust and gas emissions followed the established physics of sublimation, and its overall structure resembled long-period comets from the Oort cloud. Yet even here, lessons were abundant. Borisov's composition hinted at chemical environments unlike those seen in our own protoplanetary disk. Its dust grains appeared unusually fine. Its ices contained mixtures suggesting that its birth environment may have been colder or chemically richer than the region where the sun formed. These characteristics reinforced the idea that planetary systems across the galaxy produce a wide spectrum of cometary bodies, each shaped by unique initial conditions, stellar chemistry, and evolutionary histories. In the case of 3I Atlas, the lessons were quieter but no less profound. Unlike its predecessors, it offered a subdued form of activity, producing dust but in modest quantities, brightening but not dramatically, awakening but with a restraint that indicated an especially thick or processed irradiation mantle. Its faintness revealed that many interstellar comets may pass through the solar system without ever achieving sufficient brightness to be noticed by existing surveys. Its slowly evolving coma suggested that some interstellar objects may retain their deep ices far longer than expected, insulated by crusts hardened by eons of cosmic ray exposure. And its trajectory reinforced the notion that long interstellar journeys erase nearly all traces of the object's original star, leaving only population-level indicators such as velocity dispersion and galactic kinematics. One of the most important lessons from all three objects, perhaps the most transformative of all, is the realization that the galaxy itself is a dynamic environment in which planetary fragments move freely between star systems, linking them through exchanges of material that occur on timescales longer than the rise and fall of civilizations, but shorter than the lifespan of the Milky Way. This means that matter is not confined to its birth system. Instead, it wanders, circulates, and spreads throughout the galaxy. Fragments ejected from systems forming planets today may one day drift into the solar system, while material ejected billions of years ago may already have passed through without our notice. In another sense, these objects teach us about observational bias and the limits of detection, for until recently, the instruments available simply could not perceive the faint signatures of incoming interstellar debris. This means that our entire history of observational astronomy has been shaped by tools too limited to reveal the full picture. Only now, with wide-field surveys and high-cadence detection systems, do we begin to see the visitors we have been missing all along. Oumuamua taught us that unusual interstellar objects can be astoundingly faint and deceptively small.
Borisov taught us that some interstellar bodies will behave like familiar comets but will differ chemically. 3I Atlas taught us that faint activity may be the rule rather than the exception. Together, they teach us that the galaxy is rich with diversity and that our instruments, until now, have been blind to most of it. Another lesson, one that stretches beyond astronomy and into the philosophical heart of science, is the reminder that humility must accompany every observation. The fact that Oumuamua's properties are still debated years after its departure proves that not all mysteries can be resolved quickly. Some objects will defy classification, some will challenge models, some will leave unanswered questions that remain open until future technology provides new data. Scientists must accept that not all knowledge arrives immediately. Some arrives only as new instruments open new windows. Finally, these visitors teach us something profound about time. They show that the universe is filled with relics of ancient events, planetary collisions, stellar migrations, gravitational disruptions that occurred long before our species existed. Each fragment carries a history written in its structure, composition, and trajectory. Oumuamua may have been forged in the destruction of a world. Borisov may have been born in the cold outskirts of a young system. 3I Atlas may have spent billions of years drifting through the thin disk of the galaxy, gathering scars from cosmic radiation as it wandered aimlessly across the spiral arms. They remind us that the galaxy is ancient, dynamic, and interconnected. They remind us that worlds beyond our own leave traces, physical traces, that drift into our star system without warning. They remind us that we live in a universe where the boundaries between systems are porous rather than fixed, where matter flows from star to star as freely as currents move between oceans. And perhaps most importantly, they remind us that every visitor, no matter how faint or fleeting, offers a lesson in humility, curiosity, and cosmic perspective, expanding our understanding of a galaxy that is far more alive and interconnected than we ever knew. While Oumuamua demonstrated strangeness and Borisov demonstrated familiarity, 3I Atlas stands as a case study in quiet revelation, a visitor whose behavior was neither shocking nor dramatic, but whose subtleties illuminate key truths about the nature of interstellar matter,
the challenges of detection, and the characteristics of objects that drift into the solar system after unimaginably long voyages through the galaxy. In many ways, it serves as a bridge between the extremes represented by its predecessors, embodying a middle ground that may ultimately prove to be far more representative of the majority of interstellar objects. The first reason 3I Atlas makes such a valuable case study lies in its faintness. Unlike Borisov, which erupted with activity, or Oumuamua, which produced unexpected acceleration, 3I Atlas brightened only modestly, revealing a coma that was unmistakable yet subdued. This suggests that many interstellar objects, upon entering the solar system, may behave in similarly restrained ways, warming slowly, sublimating weakly, and developing coma that barely rise above detection thresholds. Such objects may outnumber the dramatic ones, meaning that surveys must be designed not just for the bright and active, but for the faint and reluctant. Another insight comes from the thickness of its irradiation mantle, the hardened crust sculpted by cosmic rays during millions or billions of years of interstellar travel. This crust likely insulated 3I Atlas, delaying the onset of sublimation until it reached regions closer to the Sun. Its behavior thus provides evidence that many interstellar comets may arrive in the solar system with their volatiles buried deeply beneath radiation-processed layers. This would make them harder to detect at large distances and might cause them to brighten only when already deep within the inner solar system, leaving little time for early observation or detailed tracking. The trajectory of 3I Atlas also offers valuable information. Its inbound velocity and hyperbolic eccentricity place it squarely within the expected distribution for interstellar objects, originating from the galactic thin disk, a population of stars and debris that share the Sun's general orbital motion around the galactic center. This suggests that 3I Atlas is a typical member of a widespread class of objects, neither unusually fast nor unusually energetic. Its motion teaches that most interstellar visitors may arrive with velocities familiar to the solar system's dynamical environment, distinguishing them not by their speed but by their boundlessness, the fact that gravity will never recapture them. Additionally, 3I Atlas provides a lesson in observational limitations. Atlas detected it only because it was faintly active, and even then, it required sensitive processing and multiple observations to confirm its motion. Had its activity been slightly weaker, or had its coma been slightly dimmer, the object might never have been noticed. This highlights a crucial point. The vast majority of interstellar objects likely pass through the solar system undetected. 3I Atlas represents the minimum threshold of detectability, a faint glimmer of light that happened to cross a survey footprint at the perfect moment. In this sense, it teaches that the true population of interstellar visitors is not only much larger than currently observed, but overwhelmingly composed of objects too faint for present-day instruments. The composition inferred from its activity further adds to its value as a case study. Its dust production rates, color indices, and coma characteristics suggest a mixture of volatiles similar to solar system comets, implying that the chemical processes that shape planetary systems may be broadly similar across the galaxy. Yet subtle differences, potentially in grain size, emission ratios, or thermal response, hint at diversity shaped by exotic birthplaces and long exposure to interstellar environments. 3I Atlas thus highlights the balance between familiarity, reminding us that interstellar objects will often appear recognizable, yet carry chemical signatures that speak of distant origins. Its behavior as it approached perihelion contributes another insight. The subdued activity suggests that deeply buried volatiles may require significant warming before escaping. This might lead to sudden outbursts or delayed brightening, especially in objects with thick mantles. Understanding this helps refine future detection strategies, indicating that surveys must be designed to capture objects not only weeks or months before perihelion, but also at the moment they begin to brighten rapidly, which may occur unpredictably. In a broader sense, 3I Atlas demonstrates the importance of multi-instrument collaboration. Its faintness meant no single telescope could capture all relevant data. Instead, astronomers combined observations from ground-based optical surveys, infrared instruments, and follow-up telescopes that tracked its evolution over time. This multi-layered approach will be essential in studying future visitors. 3i Atlas shows that interstellar object science will rely on distributed networks of telescopes, large and small, coordinating across continents and wavelengths. At the deepest level, 3i Atlas is a case study in subtlety. It teaches that interstellar objects do not always arrive spectacularly. They do not always announce themselves with bright tails or dramatic acceleration. Many slip into the solar system quietly, like wanderers weary from their long journey, carrying with them the silent stories of the systems that birthed them. They awaken reluctantly, brighten modestly, and then fade into the sky before slipping back into the darkness. And in that quiet behavior, they reveal something profound: that the galaxy is filled not only with extraordinary objects, but with ordinary ones as well. Objects whose very ordinariness is a gift, telling us that the processes shaping distant worlds are not entirely alien, but share with our own system a common cosmic heritage. 3i Atlas is a reminder that the most valuable lessons often come not from the spectacular, but from the subtle, not from the extreme, but from the typical, not from the anomalies, but from the representatives of the unseen majority. It embodies the promise that future visitors, once invisible, will become part of a growing catalog of interstellar bodies, each one expanding our understanding of a galaxy bound together by drifting fragments of ancient worlds. There comes a moment in the story of every interstellar object, a moment as inevitable as sunrise, yet as bittersweet as watching the last traces of a ship disappear beyond the horizon, when the visitor that briefly wandered through our solar system turns away from the sun's warmth, ends its short-lived interaction with our world, and begins the long return to the vast, silent, immeasurable darkness of interstellar space. For 3i Atlas, this moment arrived with quiet dignity, without the spectacular fragmentation that marked Borisov's departure or the lingering mystery that trailed Oumuamua. Instead, its exit unfolded in the same gentle, restrained manner that had characterized its approach, reminding astronomers that not every visitor seeks to astonish. Some simply pass through, like soft footprints left in cosmic dust that are erased almost as soon as they form. As 3i Atlas swept past perihelion, the closest point of its trajectory to the Sun, the brief intensification of sunlight, sublimation, and dust emission began to wane. The gases that had been excited by solar heating retreated as surface temperatures dropped. Dust grains, pushed outward by radiation pressure, continued drifting into space, forming a tail that thinned gradually into nothingness. The coma shrank, contracting back toward the nucleus like morning fog receding under the first touch of dawn. The illuminated veil that had made the object briefly visible dissolved, leaving behind a darkened core returning to its ancient equilibrium. The shape of its hyperbolic path told the story of its departure more clearly than any image. A hyperbola, unlike an ellipse, does not close. It does not bind an object to the sun. It does not promise return. Instead, it reveals that the visitor has too much speed, too much momentum, energy inherited from its birth environment, carried unchanged across interstellar distances. Even after losing energy to sublimation, even after feeling the tug of solar gravity, even after interacting faintly with the dust and plasma of the inner solar system, 3i Atlas retained more than enough velocity to escape the sun forever. The sun's influence, which briefly held the object's path in a shallow curve, gradually weakened as distance increased. Gravitational focusing diminished. The solar wind thinned. Radiation pressure lessened. The heliosphere's magnetic structure loosened its grip. Bit by bit, the visitor shed the signs of its proximity to a star, returning to a state where cosmic rays and galactic tides dominate the environment, where silence replaces activity, where the void becomes home once again. For astronomers tracking the object, the departure marked the slow fading of a point of light, A final series of measurements, each one fainter than the last. Telescopes recorded positions. Observatories measured brightness. Instruments attempted to capture the final spectroscopic signatures. But with each passing day, 3I Atlas retreated farther until only the largest telescopes in the world could still glimpse its diminishing glow. Eventually, even those instruments lost the thread. The visitor slipped beyond the limits of detection, becoming once more a dark, unlit wanderer drifting through a darkness where no human eye could follow. Yet the departure is not merely an observational event. It is an existential moment, one that reflects the themes that tie the entire study of interstellar objects together. The departure reminds us that these visitors do not belong to us. They are not residents of our solar system. They are messengers carried by galactic currents, fragments of worlds we will never see, crossing our path briefly before returning to the vastness of their originless journey. 3I Atlas's exit also illuminates a truth about the transience of discovery. Even as telescopes grow more powerful and surveys more precise, the window for studying interstellar objects remains narrow. A few months of visibility follow millions of years of travel. A brief scientific encounter is but a heartbeat compared to a cosmic lifetime. This disparity forces astronomers to work quickly, gathering every possible measurement before the object fades. It compels rapid observational campaigns, coordinated across continents, guided by the urgency of fleeting opportunity. The departure of 3I Atlas, like that of Oumuamua and Borisov before it, teaches that the galaxy does not wait. It does not slow down for human schedules. It does not pause to offer extended study. It continues moving, endlessly, and only by readiness and awareness can scientists capture what little the visitors reveal. Once 3I Atlas passed beyond the heliopause, it re-entered the interstellar medium, a realm governed not by a single star, but by the collective influence of the galaxy. There, the solar wind disappears, replaced by a sea of galactic cosmic rays. Temperatures return to the near-absolute zero conditions that defined most of its existence. The radiation mantle hardens further. Dust impacts become rare. The object becomes dormant once again, frozen in a condition of near-perfect stillness. Yet even stillness is motion. The galaxy pulls on the object with its vast gravitational potential. Nearby stars contribute tiny perturbations. Nebula exert slow, sweeping tides. Over millions of years, these forces will alter 3I Atlas's path in subtle ways. The object may move through spiral arms, encounter stellar streams, or drift across regions rich with star-forming material. Nothing will recapture it. Nothing will bind it again. It is once more a free traveler, unanchored to any star. And this is perhaps the most poetic aspect of its departure. Interstellar objects are not visitors by intention. They are wanderers by consequence. They did not choose to leave their home systems. Gravitational accidents ejected them. They did not choose to cross ours, they merely passed through as part of a trajectory millions of years in the making. They do not choose where they go. They are pulled by forces stronger than any plan or purpose. But despite the inevitability of their departure, they leave traces. Scientific traces, conceptual traces, philosophical traces. 3I Atlas left no physical fragments that we can recover. It left no dust that reached Earth. It left no chunks that entered the atmosphere. But it left something more enduring. Insights into the typical behavior of interstellar comets, a case study for faint, subdued activity, and a piece of evidence that the galaxy is filled with such wanderers. As it recedes into the darkness, 3I Atlas becomes again what it was for most of its life, a solitary traveler carrying the signature of unknown origins, drifting across unimaginable distances, destined perhaps to wander until the galaxy itself reshapes its path, or until it is captured temporarily by some distant star, or until it collides with a world orbiting a system we cannot even name. It arrived quietly, It left quietly. Yet its presence, however brief, expanded humanity's understanding of the universe. And long after the last photon reflected from its fading coma reaches the last telescope that could see it, long after its name becomes one data point among many, long after its path is archived in ephemerides that future scientists will consult only as historical reference, the story of 3I Atlas will remain part of a larger narrative. A narrative about a galaxy that shares its fragments freely, a solar system that sits open to the cosmic winds, and a humanity that has only just begun to notice the travelers passing by. In the end, after the calculations are archived, the orbital plots finalized, the observations published, and the visitor long faded into the immeasurable darkness of interstellar space, a deeper question emerges, one that transcends astronomy, exceeds the boundaries of data, and reaches into the heart of why humanity looks upward at all. Why do these wanderers matter to us? Why does a faint, icy fragment from another star system, silent and indifferent, passing through our cosmic neighborhood for only the briefest of moments, hold such profound meaning? Why do we feel a sense of wonder, curiosity, and even kinship with an object that neither knows nor cares that we exist? Perhaps it begins with perspective. Interstellar objects remind us that the solar system is not an isolated speck drifting alone in the cosmic ocean. Instead, it is immersed in the currents of the galaxy, influenced by forces far beyond its own star, open to encounters with fragments of worlds formed under suns older, younger, larger, smaller, richer, poorer, stranger, or more familiar than our own. These wanderers are proof that the universe is not compartmentalized. Stars do not remain sealed within their own boundaries. Material crosses the spaces between. The galaxy is connected, not metaphorically or spiritually, but physically, through shards of rock and ice that travel for millions of years across unfathomable distances. They matter because they show us that our star system participates in a larger ecological network, the Milky Way's grand interwoven circulation of matter. Interstellar visitors demonstrate that planets and comets and asteroids are not merely local phenomena. They are part of a galactic tapestry in which systems share fragments the way forests exchange seeds on the wind. In this sense, every interstellar object is a message from another region of the galaxy, carrying the fingerprints of environments we will never visit, chemical signatures shaped by conditions we will never witness, and stories written in ancient ice and dust. They matter because they expand our scientific imagination. Before Oumuamua, no one seriously considered the possibility of elongated, tumbling fragments shaped by interstellar radiation. Before Borisov, no one had direct evidence of a pristine comet formed around another star. Before 3I Atlas, no one fully appreciated how faint, quiet, and subtle the majority of visitors might be. Each object broadens the horizon of what is possible. Each forces scientists to refine their assumptions. Each deepens our understanding of planetary formation and cosmic evolution. In their diverse behavior, strange, familiar, faint, bright, they reveal the galaxy's astonishing variety. They matter because they remind us that the universe is dynamic, unpredictable, and endlessly creative. The cosmos is not static. It is not quiet. It is alive with motion and change, with fragments drifting between stars, with systems interacting in subtle, profound ways across unimaginable timescales. They matter because they invite us to ask profound questions. Questions about the origins of life. Could such fragments carry prebiotic molecules across the galaxy? Questions about the universality of chemistry. Do comets formed around distant stars share the same ingredients as ours? Questions about habitability. Could planetary fragments ejected from life-bearing worlds reach other systems? Questions about intelligence. If advanced civilizations exist, might they send or leave technological artifacts drifting among the stars? Even if the answers remain uncertain, The questions themselves expand humanity's sense of belonging in the cosmos. They matter because they inspire. Students who saw Oumuamua for the first time felt the thrill of encountering something no generation before them had ever seen. Researchers who tracked Borisov saw, with their own eyes, a comet born around another star. Observers who studied 3I Atlas glimpsed the quiet subtlety of a visitor that represented the silent majority of unseen wanderers. Each discovery sparks imagination. Each encounter invites awe. Each interstellar object becomes a story told across classrooms, observatories, documentaries, and conversations under open skies. They matter because they reveal how early we are in our journey of understanding. Humanity has existed for only a blink of cosmic time. Our telescopes have scanned only a fraction of the sky. Our instruments remain blind to the vast majority of wandering debris. The few visitors we have seen, just 3 confirmed so far, represent the first flickers of awareness in a species just beginning to comprehend its place in a galaxy full of motion. These interstellar objects are not endpoints of knowledge. They are beginnings. They matter, finally, because they remind us of our shared fragility and interconnectedness with the cosmos. When a fragment of another star system enters ours, it becomes a momentary bridge between distant worlds. It carries the memory of the place where it formed, its chemistry, its structure, its scars, and leaves behind in us a renewed sense of wonder for the universe that created both it and us. In its silence, it echoes the truth that the universe is vast, ancient, and astonishing, and that our own story is part of that greater whole. 3I Atlas passed through our solar system without fanfare, without dramatic display, without leaving a visible mark. Yet its significance is profound. It represents the typical visitor, the quiet majority, the subtle wanderers that we will soon detect not in rare moments of fortune, but in steady, predictable cadence as new telescopes awaken to the richness of the sky. It is a symbol of connection between star systems, between disciplines of science, between the known and the unknown. And long after it fades beyond reach, long after it becomes one more invisible traveler crossing the galactic night, its memory will remain, not in physical traces, but in the expanded understanding it gave us, the questions it provoked, and the future discoveries it made possible. These wanderers matter because they show us that we are part of a galaxy alive with motion. They show us that worlds are not isolated. They show us that the unknown still reaches out to touch us. And they remind us that in the grand story of the cosmos, we are listeners at the edge of a vast and ancient symphony, hearing at last the first faint notes drifting in from the stars.
Please subscribe and leave a like if you enjoyed this video. We hope to see you again soon for another session from Wisdom Sleepers.